Okay.
Hi, can you hear me?
Yeah, we can hear you.
I have some issues. I never use this like I tried it before, so I tried to install it and it was too bad. Shall I start?
Hello. So, probably network is simple.
Hello. Hi. Can you?
You're not audible.
Hello.
Hello. Hello.
Can you hear me? Hi. I think I can hear you, but you can hear me well.
Yeah, we can hear you now. We can hear you now. But probably because there was some network problem or something. We can hear you now. We can hear you. Okay.
Okay. So shall we start?
Yeah. We can start. Okay. Just give me 1 minute.
Okay.
Introduction. Just give me. Okay. Thank you. Yeah, I think we have started our streaming on YouTube. So here is our first talk, and it is delivered by Krishnendu NV, and she is from ICTS Bangalore, and her area of research is gravitational wave data analysis and parameter inference, black hole physics, test of general relativity using gravitational waves. So, okay, the stage is yours. Thank you.
Thank you very much. I think I have to give some permission to share my screen. Let me.
Okay. Let me check. Okay, just one minute.
Do you see my screen?
Yeah, we can see your screen.
Okay, thanks. Let me to full screen. Okay. Thank you so much for having me here, and thank you so much for the nice introduction. The today's topic, I'm talking about the inferring the properties of binary black holes from gravitational waves. And just one thing to the organizers and also everybody. So if you have any questions, stop me anywhere you want. And also to the organizers, I've arranged the slides in such a way that we can stop at any point whenever I exceed the time or something. I'm very sorry about the initial trouble. So please stop me if I'm exceeding the time or going outside of the schedule. And I've also given my email ID here. So if you don't have enough time to discuss something, or if you want to continue talking about something, you can always approach me private using my email ID, or contact me in any other means. So let's without any further delay, let's start. And yeah, I wish to thank you all again, and we can start. So today I will be talking about. I'm planning to talk about a couple of things, but as I mentioned earlier, we don't have to go through all these topics. We can also stop in the middle, or whenever we exceed, or we want to have some discussions, we can take it slow. So the first thing we will talk about compact binary coalescence and the associated gravitational emission. So I hope we all have seen many interesting discussions about the detection of gravitational waves through the last couple. I mean, it started from 2015 and have been evolving through last couple of years. And we hope we do have mainly three gravitational detectors. We will discuss the details about the current and future gravitational detectors a bit, and then we will discuss also about the catalog of gravitational events we have been discussing through the ground-based gravitational detectors LIGO and Virgo, starting from 2015 till the end of the last observing that run. That was the third observing run of the ground-based detectors. Then I also have plans to talk about the prospects of parameter inference and their future implications. What I mean here is once you have a detected gravitational binary system, we want to know what are the parameters characterizing the binary. So we will have a short discussion about how do we measure certain parameters, like the what are the masses of the system and what where are they coming from, what distance it is, and what is the location of the source, etc. So, the main idea is that we are talking about a binary system. They are emitting gravitational waves, and we talk about the what how do the gravitational waveform models look like, and how do we detect them, how do we construct our detectors, and why the detection happens, and what are the implications in terms of fundamental physics and astrophysics, and whatever other science we can do with these detected signals. So we may all have seen this discussion about gravitational waves, very pedagogical definition. For gravitational waves are propagating oscillations of the gravitational field. They can be thought of as ripples in space-time, as shown in this GIF image. This was first proposed by Einstein in 1916 as part of the general theory of relativity, and one can solve Einstein's field equations and get wave solutions, and those we recently also detected. So before that, those were all textbook, and there were no before detections where they were only predictions, but now we know that they exist, and we can also infer properties. And like electromagnetic waves, in Einstein's theory of gravity, gravitational waves are also transverse in nature, and they also propagate at the same speed as that of light. We also talk a little bit details about their source. So where do they come from, right? So what are the sources of gravitational waves, and can we make our own detector at home, for instance, right? So what are the possibilities of having astrophysical sources and as well as some terrestrial?
Robiti. Krishna ma'am, somehow your speaker has turned off. We are not, you are not audible to us.
Okay. Yeah, I was the.
Yes, now you are audible.
Mm. Do you see the slides?
No, that's the problem, and yeah, probably the presenting was stopped in the middle of summer.
Do you see my slides?
No, we don't see your slides for times.
I see. Let me do it again then.
Yeah,
The,
please.
the slides had popped up for a few seconds, then they went away. So
Yeah.
You didn't hear me at all, is it? Shall I start from the beginning?
Yeah, you can. Yeah.
Uh, okay. Sorry. Okay. Just speak if you don't hear me, okay? Because when I put the screen, the full screen mode, I also don't see the. I was not looking at the chat, so that's why I didn't. I missed the message. So if you don't hear me, just tell me, okay? Can you hear me now?
Yeah, we can hear now.
Shall we proceed? So, okay, let me just start from the beginning, okay? Just speak up if you don't hear me. I think that's better. So, today I will be talking about. Okay, so today we will be talking about this inferring the properties of binary black holes from gravitational waves. So if you haven't heard me before, I'll just repeat this. So I also given my email ID here, and you can also contact me personally if you have any questions or comments. Since we are running out of time, I'll just go through quickly. So. I'll be talking about compact binary clusters and the associated gravitational emission.
Excuse me, ma'am.
Yes.
Your slide is not visible.
Yes.
Yeah, you should stop presenting, and then you should again present. Probably that will work.
Can you see now?
No, ma'am.
Do you see it now? It's showing me presenting actually.
No, ma'am, it hasn't appeared till now also.
Sorry, what?
It hasn't appeared till now also.
You can send the slide to some of the organizers if possible, because
Yeah, I'll do that. I'll just send it to Sanjay and then.
Okay, let me try presenting once that I want to test that if it is our problem or not.
Yeah, I'm just sending. Okay, give me a second. I will just send it. It's not working now. Also, right? Just showing me presenting.
No, it's not visible.
Okay, I had sent it to Sanjay. So is Sanjay also in the audience somewhere?
Yeah. Okay, I'm checking.
Could you please open it? Yeah.
It's visible now.
It's visible now. It's visible now.
I am not sure. Okay, my side is it? It's my screen. You see?
Yes, ma'am.
I'm not sharing now. This is, uh, anyway, then let's go. Go ahead. Okay, Sanjay, you also have a copyright. So if there is some problem, we can also switch to yours. Okay. So what I wanted to say was we will be talking about compact binary coalescence and their associated gravitational emission, and we also talk a little bit about current and future gravitational detectors. And then so the main thing here is we have this compact binary sources which are detectable by the laser interferometric gravitational detectors placed on Earth. And we have been seeing many actually, around 90 gravitational events from 2015 through these ground-based detectors. Sorry. And we also talk a little bit about this latest gravitational transient catalog and their properties. And we also discuss a bit about prospects of parameter inference and future and their future implications. That part, if you have time, we'll come to that. So as we all know, we have seen we see many different types of definitions for gravitational waves, but many common and pedagogical they are propagating oscillations of gravitational field. They can be thought of ripples in spacetime. So you have some high relativistic phenomena happening, and the perturbations travel through the spacetime. And that's what we see as gravitational waves. So this small animation shown here for that, and the gravitational waves are proposed as a consequence of Einstein's general theory of relativity in 1916. That means you can take Einstein field equations and solve them, and to get wave-like solutions corresponding to gravitational waves for any massive object. And gravitational waves also share certain properties or have certain properties are similar to almost same as electromagnetic waves in Einstein's theory of gravity. Especially, they are transverse in nature, and they also propagate at the same speed as that of light, as electromagnetic waves. So, where are they coming from, or what are the sources of gravitational waves? We have multiple sources, but we will just go through some of them and to see why the compact binary coalescence are very important. So first of all, you have this. So imagine a star, right? So there is a supernova explosion. A star is exploding. That will create a lot of. This is a very high relativistic phenomenon. Will create huge impact in space-time, and that you can see as burst signals. So these are called short duration gravitational signals. They are the burst class gravitational sources. They are mainly the major sources for such gravitational wave sources are core collapse supernovae, and the gravitational waveform would also look like this. So you have there is nothing initially, but when the star explodes, there's a drastic change, and as a consequence, you see a wave emission at a very short duration of time here, as shown here. And you also have very long duration signals. For instance, you have a pulsar which is emitting, and it has a mountain on top of it, and it is rotating, and this rotation can produce gravitational waves, as shown in this figure. They are at the same, for a long duration, they are of the same frequency as shown in this figure. They are called continuous or continuous gravitational sources. They are mostly long duration sources. And we also have gravitational waves coming from the stochastic they call the stochastic gravitational background coming from the Big Bang itself. So we can see the early signatures of early universe itself through gravitational waves. And so in principle, any source with a non-zero time varying quadrupole moment will produce gravitational waves. And what we know is that binary coalescence, which are the ones we detect from the detectors, are ideal sources of gravitational waves. So among all various different sources, we are most interested in the compact binary coalescences. So we will talk a little more about compact binary coalescence and why they are more important, or why are we more interested in them. So what are we talking about? You have sorry. You have two objects spiraling around each other, and one, as they in spiral, they come closer due to the gravitational attraction, and as they come closer, they inspire faster and they merge to form a new object. That is the dynamics of a compact binary system. And if you look into the waveform model, they will be like, initially they are with small amplitude and less frequent. Now as you approach towards the merger, you have more the amplitude increases and also the frequency of the wave increases. And the important thing is anything can produce gravitational waves, as I mentioned earlier, but compact systems or systems where the matter is densely packed are very interesting, or they are the main sources because they can. So that we will come to in a moment. That what are the typical strain amplitudes of gravitational waves produced by different sources. So to explain a little more about the compactness, what I've shown here in this picture is an image coming from Fermi Gamma Ray Telescope of a binary pulsar system, and which is which contains the heaviest neutron star so far, and is also located a few thousand light years away from us in the Milky Way, and it's also the fastest pulsar observed to date. And what are the properties? So the neutron star in this binary system has a mass of around 2.3 solar masses and a radius of 10 kilometers, and the time period is 1.4 milliseconds. And what does it mean is the entire mass. So the density, to see how the density of neutron stars are. If you imagine putting the entire mass of Earth in a particular radius, that will be like 150 meters. So that is how dense a neutron star is. That means these are compact stars and they're very dense objects, and that's why we are very interested in those sources. And in the in spiral merger ring down dynamics, that is, you have this binary system which are far apart and they merge to form a new object. One can broadly classify these three regions of binary dynamics into three. One is the in spiral dynamics, where they are far apart, where you can use certain perturbative methods like post-Newtonian theory to solve Einstein's field equations. And when they come closer and closer, which is called the merger phase, where it's the highly relativistic regime where one cannot solve Einstein's equations either perturbatively or analytically. So one needs to use numerical relativity techniques or solve Einstein's equations on a computer. That's why we say it usually. And then you end up in the ring down regime, which is also where once the merged compact object formed, they emit again gravitational waves and tie out to come to a from a perturbed state to a stable state. For instance, a short. So if in the case of, if it's a black hole formed, it's just like a short-scale black hole is formed. So there are three things to note here to study the dynamics of this phenomenon or this physical system where you have two objects using Einstein's theory of relativity. One divide the three regimes, this dynamics into three regimes: in spiral, merge, running down, and one can use post-electronic theory, numerical relativity techniques, and black hole perturbation theory methods to study this dynamics. And to know about the system more, one needs to also use accurate and efficient waveform models, which is very important both for detecting the signals as well as inferring the parameters of this binary systems. So just to show you things which we already explained. So the two dots in this enemy are two black holes, which are real objects which were observed in the LIGO detectors on September 14, 2015. And as you can see, now they are in the spiral region. Yeah, they merged to form the new object. And you can also see the perturbations what we showed in the previous picture about this, the stretching and squeezing of the space-time. And the entire phenomenon where the amplitude, right? So the amplitude and the frequency, both of them are increasing, which is called the chirping of gravitational waves. Now, there are a couple of things here. So in general theory of relativity, we can identify two independent components for the metric. That means that can be translated into two physical degrees of freedom for the wave itself. That is identified as the plus and cross polarization modes. So that means if you take a ring of particles, how their relative motion would change when a gravitational wave passes through them perpendicularly. There can be two possibilities. They can move in a plus way, in a cross way, but these are the plus and cross polarization. But as in electromagnetic waves, it's also possible to create linear combinations, and one can have circularly or elliptically polarized light. Gravitational waves as well. Now, the important thing is the second figure. Once you have this ring of particles and gravitational wave passes perpendicular to it, there will be a motion. I mean, if you just intuitively demonstrate it, so at a position from x to x plus delta x, and if the amplitude of the signal, the strain amplitude of the gravitational strain, if it's of the order of delta x by x, then only you can measure them, right? So there should be a minimum value of delta x by x so that you can see some observable effects on your detector. So that's why we need to have the gravitational strain in a particular way, so that you cannot. So any source, I mean, any quadrupole variation can produce gravitational waves, but detecting them is a tricky thing because you need to have at least you need to have a strain which is at least measurable in your detector. Now, let's take this binary example. If you have two objects with a mass of around 1.4 times the solar mass, I would just tell you this is this is a way of measuring the masses in the astrophysics community. So we always measure in terms of solar masses. So if you have two objects in the binary system with a mass around 1.4 times the solar mass, and their distance is 10 to the power 6 light years. Now we can calculate what would be the strain, which is of the order of 10 to the minus 21, and also the gravitational luminosity, which is not very important here. But the important thing I wanted to mention here is that can we also consider terrestrial sources? So, for example, we can also calculate the quadrupole moment created by a cylindrical bar or mass 1 kilogram and length 1 meter, and which is rotating with 1 per second, the frequency of 1 per second. The strain is 10 to the minus 53. So, what can we measure, say, delta x by x of the order of 10 to the minus 53, which is impossible, right? Even if you increase the mass to say 1 ton or say 10 to 3 times or 10 to the 4 times, the strain is not going to change. So it's very difficult to construct terrestrial sources. I mean, it's not possible. Now let's go back to a very interesting thing which happened in 1993, where this Hulse and Taylor got Nobel Prize for their detection of a binary pulsar. But where they were observing the pulses from a pulsar system in a binary. but what they found was the period was changing systematically, and they were investigating, and they found a periastral shift of the orbit, which was due to the orbit shrink, or which that was observed for decades of they started around 1975 and they continued till uh, uh, early 2000. What they found was the observed periastral shift of the orbit, or the shrinkage of the orbit, was exactly matching with Einstein's predictions of gravitational waves. So that means if in the binary system, if that was emitting gravitational waves, the orbit should shrink, and that shrinkage coming from the theory was matching with what they observed. And this was a discovery, and they got Nobel Prize for this. And the committee announced that this is the Nobel Prize was given to these two gentlemen for the discovery of a new type of pulsar, a discovery that has opened up new possibilities for the study of gravitation. So this was the beginning of, I would say, this was an indirect evidence for gravitational waves, and was the beginning of, many people started working on gravitational waves because thinking that there's a possibility of detection, and we might see interesting phenomena. And in 2017, these three people got again in this. I mean, it's the beauty is that the 1993 was for indirect gravitational detection, but here it was given for the real detection of gravitational waves through LIGO-Virgo detectors. So this detection was happening at the two LIGO detectors, but the Virgo joined later to the observation campaign in 2017. So just to demonstrate the how the detectors work, it's based on Michelson's interferometric tech. So it's basically Michelson interferometer, and you can see the stretching and squeezing of space-time. So you have a laser beam going, and it is splitted from the beam splitter, going both the arms of the detector, and coming back to the beam splitter, and there will be an interference pattern created. So the detectors are way that there is a interference created all the time. Now, this is a locking condition of the detector, but when a gravitational wave passes through the detector, the arm, as we demonstrated earlier, there is a stretching and squeezing of the arm length, and which changes this interference pattern and creates a which creates the change in interference pattern. The shape shift can be measured through a photo detector, and this is actually measured as the gravitational wave. So that's how we measure it. But the detector configuration is a bit complicated, but I think we can skip. But currently we have multiple detectors on Earth. We have two LIGO detectors in the US. One Virgo, it's called Virgo, it's in Italy, and Geo and Kagra. There are two other small scale detectors. Geo is a 600-meter arm length detector, and there is also a Kagra detector. And the future is very exciting for Indian community. Also, we also have this LIGO India coming up soon. And just to add this, currently we are getting these events from observations from LIGO Virgo detectors, but the other detectors will also join the detector configuration very soon. So this is the each palette here describe one gravitational detection, and you as you can see, starting from first observing run in 2015 September until now March 2021, we have seen around more than 90 gravitational significant detections of gravitational waves, as I illustrated here. So here each dot, so you have three dots, two of them corresponds to the inspiraling system, and the third one is a merged object. Just to demonstrate the cumulative detection, the rate of how many events we detected. So on the y-axis, you see number of detections, so cumulative number of detections. So we passed, say, 50, we got around 50 detections by the end of O3A. O3A and O3B are two parts of the third observing run. And so by the time the detectors were having this effective days of observations of around 600 days. And there was also two detectors, Kagra and Geo. They were also observing at the time. but they did in the so only 2 weeks of end of O3, but they didn't find any significant detectors. And we also have future detectors coming up, not just the ground-based detectors. We also have detectors planned in the space, which is called LISA, and you can see some details here. But let me pause here. So I think, see, I don't want to disturb the the time of the conference. So you can maybe we can stop here, and I can take any questions, and then you can, I think, continue with the other talks. But you can definitely contact me if you have any questions or any problems. Is that a good idea? What do you think, Sanjay?
Excuse me, ma'am.
So we have a
So I
question
will
here.
type my I will type my email ID here. So my email ID is this. Yeah. So I think Sanjay already has my slides, right? So would that be enough, Sanjay? Or do you want me to put it somewhere else?
Yeah, I have your slide.
I guess Sunshine will be able to convey, right?
Yeah, sure. Okay.
Okay, then I guess we can move on to the next next speaker. Thank you so much, ma'am. Thank you so much for your enlightening speech. I guess many will be really benefited by this. So yeah, we can move on to the next talk here. Our next speaker is Mr. Debashish Sadhuka. He's from the University of Edinburgh, UK, and his field of research is in the realm of quantum information, a very hot topic nowadays. What he'll be talking on is the simulation of long-range systems with NISQ era quantum computers. So, Mr. Debashish Sadhuka, if you can start your talk. Sir, I think you're muted.
Okay. You can hear me now?
Yeah, we can hear you.
Okay, great. Thanks for the nice introductions. And so you can see the screen, right?
Yes.
Okay, so so thanks Sanchan and all the organizers for reaching out to me, and it's really nice to see like so many enthusiastic minds. So as Aleka says, that it's really a hot topic nowadays. I'm happy to talk about it. So basically, what I'll talk about is how to simulate many-body systems, complex many-body systems with the current quantum hardware that we have. So for the past few decades, actually, so there has been a tremendous advancement in from academia, from industry, which led us to the now available current generation quantum hardwares. But the thing is that the quantum computers that we have right now, so they are of limited size and also very error prone, and which kind of limits its ability, and hence the name NISQ, and which stands for noisy intermediate scale quantum computers. So these are quantum computers like of the order of 50 to 100 qubits, or even let's say 500 qubits nowadays, but they are not fault tolerant. So you can like they are not like our computers where you have error corrections. So you don't have like we don't have physical overhead to support the error correction. So they are really noisy in that sense. So although like the quantum computer is a very even 50 qubit quantum computer is a very powerful tool, but that will not change the world right away, because at least for the commercial applications which kind of hope for new discoveries like new drug discoveries or efficient finance solutions. So at least, but if not commercial applications, they are what they're good for right now. So this is kind of the specific topic that I'll kind of indulge in. So basically, with the current computer, like quantum computers that we have, we can mimic or simulate certain complex many-body systems for which we don't have any solutions or only had approximate solutions, and we cannot really simulate even with our best possible classical computers. So these are the kind of things that we're trying to achieve here. So that's with these NISQ era hardwares. Okay, so I'll not, for this talk, I'll not really go into deep technical details, but at least you should be able to get the idea how the things are done, what are the problems, how you should overcome this, and what the end of the story is. And in the meantime, if you have any questions, just stop me and ask. So whatever I'll discuss, you can find mostly in this reference. If I get some time, I'll probably discuss this paper as well. Okay. So the recent progress in various disciplines of physics has established our ability to control quantum effects in quantum devices, and thus paving the way for near-future quantum technologies. Now, one of the key resources of efficient quantum technology is to prepare preparation of a quantum state in a well-controlled initial state, and then optimize the adiabatic control to an interesting final state. Now, both of which are very crucial features to adiabatic quantum computations. Now, to demonstrate quantum supremacy, that is to perform any information processing task with non-classical or superclassical efficiency, the important features we should look for in any quantum device is how to efficiently prepare a target state. Second, how to protect the state from environmental decoherence or any disturbance for at least over the duration of my task. And third, we should be able to manipulate the state, the entanglement content of the state, so that it could be used for that particular task. Now, I'll briefly focus only on the first part here, not the second part. So I'll describe how to efficiently prepare a target state in a quantum device that we have access to. Now, in an ideal adiabatic quantum state preparation, a quantum state is first initialized in the ground state of some initial Hamiltonian, let's say Hi. And this step is simple in the sense it is easy to prepare. For example, this could be the Bose-Einstein condensate in a cold atomic setup. And then you kind of optimize the adiabatic control and slowly evolve the state from Hi to HF. And the ground state of HF is interesting because it contains solutions to some hard compressor problem. That is what we want to reach HF. Now it's hard, it's the sense that it is difficult to compute on a classical computer. Now for the first part of the talk, I'll mainly first describe how with the different architecture you realize the first task, how the initialize a quantum system in its ground state. So specifically, what systems we are talking about here? We are talking about long-range systems. So unlike the prototypical short-range one, which are well studied, here the systems are end-to-end connected. That means each subpart of the systems are connected to all other. Now, how they are connected? So they are connected. So in this picture, so they are connected via these connections, and the thickness of these connectors are kind of the strength of the connections, strength of the interaction strength. Now, the nearer the spins, the stronger the strengths are, but the distant spins are very feebly connected. And we quantify that strength by this algebraic decay, where this Jij kind of is 1 over the distance to the power alpha. Now, you could imagine that if you put this alpha to be, let's say, 0, then this Jij is 1 for all I and j, right? So then you have a end-to-end connected long-length systems where all interaction strengths are small, which is a very non-local regime. On the other hand, if you put this alpha to be infinite, then this Jij is 1 except only for when I equal to j plus 1 or something like this. So except when except for the nearest neighbors, all other kind of connectors are 0. So you can see that if you increase alpha from 0 towards infinity, so you'll go from highly non-local end-to-end long-length systems to a nearest neighbor system. So now these kind of systems are already natural in cold atomic setups like trapped ion. So how do you prepare this? You basically trap several class of bunch of atoms, and you put some laser field over it. So what happens? The ions' internal degrees of freedom, together with the external atomic field, external optical field, can generate a effective magnetic field, which is kind of showing here. So this is generated by this internal degrees of freedom of these ions, and then the strong dipole moment of the applied laser beam drive the effective spin-spin interactions. And effectively, you can simulate such systems like in a cold atomic setups. Now, these kind of setups in cold atomic setups, these long-length systems are really natural, and it is really difficult to prepare an nearest neighbor interactions, which is typical in our theoretical studies. So, so this is an experiment from Chris Monroe's group in Maryland. So what they did, they wanted to study spontaneous magnetizations in Ising model, but they couldn't do it for the nearest neighbor Ising models. But what they could do, they prepared a Jij profile something like this, but make this alpha to be high enough so that it could mimic a nearest neighbor Ising model. So here in this talk, we are focusing on the other questions. So we are trying to look at other quantum computers where we have access to not really such analog Hamiltonian, but some gates. So we are specifically looking at Google, IBM, or Rigetti, and where we can apply a bunch of gates and then try to generate such long-range Hamiltonians. But the problem here is like, so for each interactions, you need to apply some 2-qubit gates. And for a long-range interactions, you need to apply at least order of n factorial number of 2-qubit gates. And as I told you before, that right now the computers are not really fault tolerant and they're prone to errors. And the more gate you apply, the more noise you introduce in the circuit. And therefore, if you apply many gates, you will end up with some meaningless output, which will not be the actual results, which we are trying to avoid. So usually, how is the procedure? How do you simulate long-range or any many-body systems? So basically so for example, if we try to simulate something like this Ising Hamiltonian, something like this, so what you try to do, you you apply in two layers, where for one layer you apply these interactions, and for the other you apply the magnetic field, and then you apply with some variational parameters, gamma and alpha, and over several iterations you kind of optimize these parameters. So you kind of solve an optimization problem, so using a quantum variational algorithm, and the most popular one is this QAOA, quantum approximate optimization algorithm. You try to optimize these parameters gammas and alphas over several iterations, and you kind of prepare your like after many iterations you reach close to the ground state of the edge. Now, so I have been really working with this the Rigetti's architecture Aspen 12, which was the first commercial quantum computer built in the UK. And so what I was trying to do, I was trying to simulate such a system in these hardwares. Now let's look at the properties of this hardware. So this is the layout. So this is a 32 qubit quantum computer, and you have the layout is like 8 octagons. And here what you can see is the fidelity of the single qubit gates. And by fidelity, I mean how pure they are, how correct they are. So, and the deeper the color, the more correct they are. So as you can see that like most of the gates are really good, except few, for example, 14, 16, but like most of them are good. But it's really become crappy when it comes to 2 qubit gates. So here you see like there are very like there are few blue colors, and like more of them are more of Eolis, which is like there are percentages 19%, and it could go even to 30%. So the 2 qubit gate is not so good. And as I said before, so the 2 qubit gates for this kind of realizations would scales up exponentially with n, which we're trying to avoid. So the question we ask here, so if we limit somehow the number of 2 qubit gates, that means if we limit the number of interaction terms in this true long range Ising model, can we still mimic the quantum correlations of the true long range model? So this is the question we're trying to address here. Okay, so any questions so far? I couldn't see any of you. Okay, so let me go ahead. So firstly, why quantum correlations? Why quantum correlations are important? Why we should look for it? So because they are the resource in any quantum information processing task. So for example, in quantum communications, for example, in long distance communications, so far we have satellite communications around 1,000 kilometers, probably not really between Agra and Edinburgh, but close enough. And then over several years, we know that with dense coding or quantum teleportation or quantum cryptography, so they are the useful resource. And also with the recent advancement of quantum via quantum repeaters, quantum internet, or quantum network in general, so these entangled states are kind of the resource. So these many-body states, the ground state of the many-body Hamiltonians, could also be used as a resource. So this could be one motivation for it. So this is why you are interested in the quantum correlations of the ground state of the Hamiltonian. So now there are like a plethora of quantum correlations measures, and they have a clear hierarchy of the correlation present in the systems. So for example, so first of course is the classical one, then the one with less correlate is discordant. Entangled one is more like held more correlations than the discordant ones. Over it is steerable, and then non-local quantum correlation is the strongest one. So we kind of divide into two different parts, for example. So one could be information theoretic one, another could be entanglement and separability one. So in this talk, I'll not really talk about the information theoretic one. I'll talk about only the entanglement separability measures, which are closely related to entanglement somehow. And we'll also focus only on the bipartite correlations, not really on the multipartite ones. So basically, if for example, in our case, if I have like many body systems that have, but by the virtue of the name, it's many bodies, so there are several parts, not really bipartite ones. But I'll just forget about all other parts. I'll just concentrate on two particular qubits, two particular spins, A and B, and I'll talk about how these two are correlated. Okay, so let me give some definitions of entanglement. So probably all of you are familiar with some notion of entanglement, but let me try in my way. So entanglement is a purely quantum mechanical quantity, and it doesn't really have a classical analog. But let me try to give a closest possible classical analog here. So for example, if let's say you have a quantum book and it has, let's say, 100 pages. Now each page of the book is the subsystems of the quantum system. Now, if it is not really a classical quantum book, so in a traditional book, you kind of read one page and then you know 1% of the book's content. And as you go over and over the pages, you will like know like one more percentage of the book. And when you read full, like finish the book, you will have all the informations of the book. But what if it's quantum mechanical? If the book is quantum mechanical, so if you read only a single page, then even if you kind of finish all the pages one by one, then even then you will have very limited or very no information at all about the book, because the information of the book is encoded not really on individual pages, but on how the pages are correlated. So this is the difference like between classical correlations and quantum correlations. So the information is not really encoded in the individual system, in any one or any all of them. They're encoded in how they are correlated. So let me let's oversimplify it a bit. So for example, let's say if we have the book has only 2 pages, let's say A and B, the page name, and so each page also has only a single bit of information. So it can be either 0 or 1. And because it's quantum mechanical and superposition is allowed, so you can have like A0 plus B1, and similarly for the page B. Now, in general, when you cannot write the book in this form of A tensor B, so that then it's entangled. So for example, the singlet states, you cannot write it in this particular form, so it must be entangled. And how do you quantify that? So it's very easy for this because it's a pure state. So we know that for the entire system, the disorderness is 0. So if you measure, like quantify the entropy of the whole systems is 0. So the disorder in one particular subsystem will give you the correlation, the entanglement of between A and B. So for pure state, it's easy that you can just find out about the entropy and it's all. But what about the state is mixed? So in that case, we kind of borrowed the idea from here to here, but just transform in the mixed state form. So if you can write something like a state something like this, so then it's a separable one. And if you cannot write, then it's entangled. And how do you quantify it? And one example is the Warner state that you can write. So the von Neumann entropy cannot be used here because this is a mixed state. So the von Neumann entropy of rho AB is not really 0. So what could you do? So these two persons, Perez and Horodetzky, so they came up with the idea of a partial transpositions. See this. if if the rho is a entire state, then if we take a transpose of the full transpose of this, this rho still stay a physical state. That means all of its eigenvalue remains positive. However, if you have a state of this form, let's say, and you take a partial transpositions only one subpart. Now, if it is a separable one, has this kind of form, so then this partial transpositions is a full transpose of the subsystem, right? So since it's a full transposition, so then all of its eigenvalue remains positive. But if it is not of if you cannot write in this kind of form, so then it's not a full transpositions, and it will generate some negative eigenvalue over the partial transpositions, because this is not really a physical operation there. So then what they did, so they kind of use these negative eigenvalues of the partial transpose state as a quantifier of the entanglement. So this is known as logarithmic negativity. So for a mixed state, so we can use this. So this is particularly useful in our cases because in our case we have many subsystems. We concentrate only on two parts and forget about all others. So that means let's say we have 5 particles. So it's a pure state of between 5 parties. Then I'm only considering entanglement between 1 and 3. So I trace out all my other subsystems 2, 4, and 5, and I end up with a mixed state between 1 and 3, and I work with this rho 1, 3. Okay. So now we know how to calculate entanglement, and so let's come back. So we are interested in mimicking ground state of the long-range Hamiltonian. I mean, mimicking the quantum correlations of the ground state. Okay, so there are several intuitions. Okay, it's a little bit quick. So first one is entanglement area law. So if you have n particle or n qubit, n spins, so then the Hilbert space is 2 to the power n, right? And then the ground state could be any state in this 2 to the power n Hilbert space. But what people notice that the ground state of this kind of short-range Hamiltonians, are not really any random states. So there are some special states which we call as area law states, which is very small subspace over the large 2 to the power n state. And why area law? So if you increase, let's say your system size is, the whole system is B, and you somehow put a boundary between A and B, and the entanglement as you increase A goes as delta A as the area. So in that sense, it's area law states. So we can only look for these states which will be useful for us. So this is kind of a hint, at least for short-range systems, and you can prove there. So the ground states are not really multi-party entangled, or there is not really long-range entangled, because there is an area law between the entanglement. So this is the first clue. But this was only for the short-range systems. We are talking about long-range systems, how this holds here. Now, this doesn't really hold here, but we know over the years there are several works which kind of built on the technology of these area law states, which is known as matrix product states, and they work well also for these long-range systems. So these systems, at least except some regime, cannot really mimic have non-local, non-area law states, the ground states. So this is the first clue. So the second clue here, so the entanglement, unlike classical correlations, cannot be shared arbitrarily. So entanglement is like a civil world, a person could be married to, or a guy can be married to a girl only once and no other girl. So it's a very strange property of quantum correlations. For example, in classical correlations, let's say correlations along z directions. So if you have a Ising spin and you have a very strong magnetic field in Z direction, so then all of them are Z aligned, and then you have Z correlations between all of the pairs 1. But for entanglement, no matter how non-local they are, how non-local interactions present, you cannot really have maximal entangled states between all pairs. So just for this scenario, let's say you have three parties here, A, B, and C. So there are two possible scenarios here. Either A and B could be maximally entangled, and they will not share any quantum correlations with C, and there would be A could be maximally entangled with C, and they cannot share anything with B. So I'm assuming A to be the nodal player here. Of course, like you can exchange A for B or C. But what happens if it is not maximally entangled? So then also it's the same case, but they have some restrictions over this via these relations. Now, if you just translate this from 3-party to many-party to n-party, so this relations becomes here, and this kind of puts the restrictions on the long-range entanglement present in systems. So there are two strong intuitions which kind of suggest that even we have a true long-range systems, will not be able to have a true long-range order entanglement. So this is the first clue. Okay. So now we sort of resort to an actual Hamiltonian, what we're trying to simulate. So this is the Hamiltonian, which is very close to the Ising Hamiltonian, but we have some cluster sigma z term here to make it solvable actually, so that we can cross check with exact solutions. So look closely here. So this Hamiltonian has like n parties. So this is a magnetic field. This is the interaction term, and when z is equal to n, so then it's a true long-range Hamiltonian. But when z equal to 1, that means there are only one term present. So that means there is only nearest neighbor interactions. So this family of Hamiltonian actually contains Hamiltonians, which is from nearest neighbor to next nearest neighbors to all. Okay. So now, when you solve this actually and check the entanglement behavior, we first see that when alpha is more than 2, so then you don't really need this. So this z is actually the number of pairing term that we are considering, number of 2 qubit gates that you are considering. So when z is 1, so that means for each pair you are considering only one interactions, only one 2 qubit gate, and for 2 is 2 factorial, something like this. So what we see that when alpha is more than 2, so ZC of the order of 1 is enough. So it is expected because we know that for alpha more than 2, it's somehow very close to the Ising university class. Okay, so next comes to the intermediate regime, which is a regime where classical correlations are algebraically decaying. So the classical correlations are even away from the critical point are algebraic. They always have a diverging correlation length. So in this case, we see that, well, if you have like z of the order of 10, it's always enough. So for example, if you see this from 5 to 20, so it's more or less mimicking the ground state. So this is kind of good thing, like for at least in this regime, although they are non-local, so you can really mimic them with finite number of interactions. And lastly, the strong non-local regime, where we see that, well, the entanglement content is very low here, but you need at least all the interactions to have the exact behavior. And the explanation may lie in this analysis of this monogamy score. So monogamy score is the same formula here. We're just taking the difference of this inequality. So as you can see, when alpha is very large, like more than 2, so then it's kind of mostly flat after 1. So that kind of suggests that it's very close to the nearest neighbor Hamiltonian. But when alpha is in between 1 to 2, so then kind of it decays first a bit, and then becomes a shallow decay after 10, and then after 100 it becomes almost flat, which kind of agrees with our findings that ZC is of the order of 10, or of the order of 10. And finally, for non-local regime alpha equal to 0.5, we'll see that so it's kind of having algebraic decay. There is no flatness here, and which also agrees with our results that no ZC except n is enough. Okay, so that kind of concludes my first part. I think I'll stop here. So basically, so the message is here is that so with a few neighbor interaction is often sufficient to faithfully mimic the quantum correlations of the ground state, and you don't really need all-to-all connections to simulate here, except in a non-local regime. When alpha is less than 1, then you cannot really do anything. Okay, I think I'll stop here. I'll take some questions. Anybody?
Thank you, sir. I guess we don't have any questions.
But okay, so do I have something? I can like talk a bit more, but
you actually have. I mean, you are allotted till I guess 11:20, so you can speak a little more.
Okay, just let me know whenever it's the time.
Yeah, absolutely. We'll inform you. Thank you.
Okay. Okay, so good. Okay, so then the question comes that I talked earlier. So what happens so this is the bare generation of the ground state, but what happens that I don't have access to all possible gates, and I cannot really generate the target ground state right now. And basically, so here, so I kind of generated HI, but I want to go via some evolution, some HF. So this is kind of an easy process. So this is the main motivation of adiabatic quantum computations. How do you do that? So you can easily do that, except when there is a critical point between HI and HF. So unfortunately, if HI and HF are separated by a critical point, then what happens that because the energy gap vanishes, the kind of adiabaticity breaks down at this point. So this is the rate at which, so when you first start the evolutions, let's say epsilon is your tuning parameters, and then you start it at t equal to minus infinity, which is very far from the critical point. At first, it's kind of mimics the evolved state kind of mimics the ground state, but as you reach the critical point, the transition rate at which the instantaneous ground state adjusts itself to its ground state kind of becomes higher than the energy gap. And as a result of that, at some point it kind of breaks the adiabaticity and end up with some defects. So basically you can, so this is known as quantum Kibel-Zebek mechanisms, and what you can do, to find the number of defects after the quench, it basically you can show that it depends how slow or how steep you are going towards the critical point. For example, if you have this tau to be very large, that means if you go very slowly, so that you will end up with very few defects, as you can see from these relations. And so this basically depends on these universal parameters z and nu, which are the critical exponents. And this depends on the specific model you are dealing with. But the general scenario is if you have tau large, that means you're going slow. That means you will end up with very few defects. If tau is very small, that is you are going very fast. That means you will generate many defects. But however, it's like no matter how slow you go, you cannot really bypass the defects. So it will be few defects, but you'll encounter some defect at least. So we're looking for ways to bypass this scenario. So let's say we are looking out for some real life example. So let's say we have a glass of water and we want to move it quickly from point A to point B. If you move it quickly from point A to point B, so then let's say at velocity v, certain water will get spilled, and the spilled amount of water is our equivalent to defects, which we are precisely trying to avoid. So what you usually do in a real life situation? So what you'll do, probably all of you know this. So you kind of tilt the glass a bit and then quickly move from A to B, and even with velocity v, but then as you tilt it, you kind of avoided the spilling. So our approach is exactly the same. We kind of exploit geometry in this quench to avoid these defects. How this works here, let's say this is our spins, and we have a magnetic field here, and the magnetic field is first uniform, let's say. So let's first question about homogeneous quench. So that means all the spins here, spin 1 to n, experience the same magnetic field. So it goes something like this. We start with very high magnetic field, goes to 0, and at h equal to 1, it's the critical point. And because all of them kind of experience the same thing, you end up with some defects. This is the case of defects. This is what you are trying to avoid. So what you can do, you can kind of exploit the geometry and implement some inhomogeneous quench. So once again, the quench starts from left. And so what happens? So the inhomogeneous front moves in this kind of way from left to right. So spin 1 first get exposed to the critical point, and then spin 2, and so on. So now when spin 1 get exposed to the critical point, it kind of excites the quasi-particles, right? And these quasi-particles will have some velocities, and these velocities, the maximum velocities, are bounded above by this v hat. This is the kz velocity. And if the velocity of the inhomogeneous front v is smaller than the v hat, then the quasi-particles can inform, like quasi-particles which are excited by site 1 can reach site 2 before the inhomogeneous front reaches there. So it can bias its choice to take this one. However, if v hat is larger, if v hat is smaller and v is larger, then like this is effectively a homogeneous quench. It's like inhomogeneity is too slow to be relevant. So the only possible scenario here, if v hat is somehow bigger. So in that case, like site 1 first bias site 2 to take its orientation, site 2 will then again bias site 3, and so on, and you will end up with some inhomogeneous quench. Yes.
Sir, I'm extremely sorry to interrupt you.
Yeah, sorry. So I think you get the idea here. Like
yes, sir. Like we have like comments here like that read that the explanations of the quantum correlations was indeed very interesting. People have really liked your talk, it seems.
Mm-hmm. Good.
So yeah, thanks a lot, and I guess your email ID will be made public, so people will be able to contact you, I guess.
Sure.
If there are problems. So thanks a lot, sir, for your excellent talk, and thank you for sparing your time for us.
No problem. Yeah.
So,
And don't call me sir. Just call me Devashish or Devashish.
okay, Devashish Da. Okay, fine. Thank you so much, Devashish Da. Okay, thank you for your talk. So we'll now move on to our next speaker. Our next speaker is basically a senior from RKM Narendrapur. We are very proud to have him here. He is Shatanik Bhattacharya from TIFR Mumbai. His domain of research is in the field of astrophysics, and the topic on which he'll be talking about is the music that shows magnets buried in old stars. Now, personally, I'm very curious to learn about this. So, Shatanik Da, it's your show.
Hello, am I audible, visible, everything?
Yes, you're audible and visible. Yeah.
So I'll start sharing my screen then. It's visible, right?
Yeah.
Okay. So, good morning or afternoon. Okay, it's still morning. Yeah, so good morning, everyone. I'm Shatanik Bhattacharya. I currently work in the group of Astro-seismology and Heliosismology at Department of Astronomy and Astrophysics, TIFR. So today, for the Young Physicists Meet 2022, I'll be presenting on stellar music to see magnets buried in red giant stars. So here's a brief outline of the talk. So first, I'll discuss what astroseismology is, because I'm very sure most of you haven't even heard of this term. Then I'll discuss the basics of the theory, the observables in this case, and how they're analyzed and studied. Then we'll discuss the fossil magnetic fields which are buried inside red giant stars. So these are remnant of magnetic fields which were formed during the stellar evolution process, primarily in the main sequence phase, the longest phase in the evolution of a star. For example, our sun is currently in the main sequence star, right in the middle of its main sequence phase. So the magnetic fields which are formed in this phase are stored and captured in the core as they evolve towards their red giant stage. Now, then I'll discuss how rotational and magnetic perturbations impact the signal, the observables. And finally, we'll move on to discuss some interesting results, some computational and some very recently done observational techniques. And finally, I'll discuss the work very brief. I'll discuss the work our group has been doing, and we'll then conclude. So let's say hello to astroseismology. So astroseismology is primarily the study of stellar quakes. So it's so basically a standard star is in its equilibrium position, but due to some stochastic processes, turbulence inside, nuclear heat transfer processes, etc., what happens that they perturb the equilibrium state, and because of that, vibrations are generated. Now it's very similar to the concept of perturbing a glass of water. Let's say if you have had a glass of water, you tweak it, you hit it gently, then you'll see some standing waves forming. Obviously, they dissipate due to loss of energy and all. But if there was a constant pump of energy inside, then they would have reached a standing wave phase, right? So a same thing happens in a three-dimensional structure of a star. So there also some standing waves are formed, and they have very specific frequencies which are dependent upon the interior, the stellar interior. So basically, this is one of the very few techniques, or probably the only technique by which you can actually explore various different types of parameters in real time to the depths of the star. So this was first studied in theory for the sun using standard perturbation to the hydrodynamic equations, and later it was also observed using observational techniques, primarily photometric techniques. So it was observed that they have a peak oscillation frequency of 5 minutes. Sorry, period of 5 minutes. So that was a very stark observation, and that does tell us about the mean density of the sun throughout. So later it was this observation has also been done for other stars like other stars in the nearby like in the vicinity of our solar system. So they were primarily observed by the COROT telescope, the co-rotation and transiting exoplanet telescope. Then there was this a Kepler telescope which got decommissioned just 2 or 3 years back. It has probably provided us with the best data till date for analysis. Then we also have a new telescope which had come up 2 years back. It's known as TESS, the Transiting Exoplanet Survey Satellite. It also has a good amount of data, but those are specifically for very bright stars and very bright stars, and that too in the very close vicinity of our solar system. Unlike Kepler, which had greater scope of detection. So other stars are observed primarily via two techniques. One is the high resolution photometry. So photometry is primarily the technique of capturing the light in a particular optical filter range, and the number of photons falling onto a CCD camera. I hope you guys know what a CCD camera is. So it's a solid state device which actually counts the number of photons falling into it in a time interval. It captures that count and stores it in your data bank. So what you finally compute in photometry is the time series. So you capture a number of photons, let's say in 20 seconds, then you store that data somewhere and you go for the next 20-second observation and so on, and you store your counts. And the other technique is a high resolution spectroscopy. So spectroscopy is a very common technique where you use the concept of dispersion and you observe the lines, the absorption or the emission lines of a star. Now in case of stars which are far away, what you get is the disintegrated lights spectrum. And over there, what you study for astroseismology is how those specific absorption and emission lines move in time. So these are the two basic techniques by which they are studied. So now I'll get into the theoretical part. We are done with the observational thing. Now we'll get into the theoretical part. So the first few assumptions we take into consideration is that the star is spherically symmetric and isotropic. Then it's that so the star is not rotating about any axis of its own. And a third assumption is that it has no magnetic field or anything inside. It's just a stable ball of gas where you now perturb the equilibrium parameters, let's say pressure, density, your local chemical composition and everything, and you incorporate these perturbations into the equilibrium condition in the coupled ideal hydrodynamic equations, pardon me, not M.H.D. in case of non-magnetic stars. The magnetic field becomes zero there. So after very cumbersome long calculations, where you reach is that you have an, okay, just a minute. Is my pointer visible now?
Yes.
Okay, cool. So what we finally yield is an eigenvalue equation. And as you can see, there are some particular eigenvalues and some particular eigenvectors, right? So this is just the density profile. You can just bring the density over here, and so this perturbant term over densities, eigenvalues and eigenvectors are what you calculate. So the eigenvalues are basically related to the allowed oscillation standing wave frequencies. So not all frequencies are allowed. The ones which help us solve these eigenvalue equations are basically the solution. Okay. Sorry for that. Yeah. So your eigenvectors tend to have this form. So there are three quantum numbers n, l, and m. This is the very elementary spherical harmonics, the very common spherical harmonics, because somewhere in this equation you tend to obtain the associated Legendre equation. So yeah, so these are the different eigenvectors you obtain. This is the radial component, which goes as the spherical, which is proportional to the spherical harmonics in the angular and the azimuthal part. And you have the horizontal component, which is proportional to the horizontal derivative of the spherical harmonics in the azimuthal and the polar directions. So your final vector for oscillation is a linear combination of all these possible eigenvectors, and hence we sum over these n, l, m. I don't think this GIF is working, so I'll let it pass. Yeah, so how much time do I have? Okay, I have enough time. So now we'll discuss what the observables in our case are and how they're analyzed. So as I mentioned earlier, we have these time series data from photometry. So I'll be discussing photometry specifically because I personally don't work much in spectroscopy, number one. Number two is that spectroscopic studies are hard to do, very hard to do, because of there are like in the interstellar medium is present. There are changes over there. There are turbulences over there as well, which need to be accounted for. The instruments are not well like constructed for this purpose. But very honestly, if we had equal signal to noise ratio from both photometry and spectroscopic data, then spectroscopic data tends to contain much more information than the photometric counterpart. But still, just because it's easier to do photometry and you can actually calculate these time series, people actually do time series calculation for exoplanet surveys. So the telescopes I had mentioned earlier, the Korea, the Kepler, as well as the TESS telescopes, all three of them are primarily exoplanet survey telescopes. But because for exoplanet, so what happens in exoplanet detection by transit method is that as planet passes through the disk of a star, what you see are the fluctuations. So as long as no planet passes through the star, you keep measuring, you'll find that there are fluctuations in the luminosity of the star itself, which reflects in the time series data. Right. So now what we compute is an equivalent of the Fourier transform of this time series data, the modulus squared of the Fourier transform of this time series data, and it's known as the power spectrum. So Fourier transform can be done simply for continuous signals, and for discrete yet equally spaced points. In that case, you can use techniques like fast Fourier transforms and all. Excuse me. But you can't use fast Fourier transform in case of unequally sampled data. So as you can see, there are some gaps in between when the telescope was shut off, or there might have been a time, there tends to be a time where the object you want to look at is eclipsed by Earth or Sun or any other planetary bodies, etc. So because these are unequally spaced, what you tend to compute is known as a Lomb-Scargel periodogram. It's a complex word, but yeah, it's an equivalent of the Fourier transform of the time series. So as you can see, there are specific peaks over here. I guess it's clear, it's visible to you all. So there are a few peaks here, equally spaced, and as you can see, they have been marked with specific colors. So over here, the colors tend to indicate your L values, the YLM, which I discussed earlier. So these colors indicate the L values for different N. So this belongs to one batch of N. These three belong to one batch of N. And observationally, for stars outside our solar system, we are unable to measure more than L equal to. In very few cases or excellent high signal to noise ratio cases, you tend to see L equals 3, but not in most cases. So, so over here you get to see the L equal 1. This is the L equal 2, the green one, and the red indicates the L equal 0 modes. And these belong to different sets of N. So, yeah. There are many other parameters, like I don't think you can read it over here. So this is known as the nu max. So nu max is the frequency. So it's the inverse of the time period at which you tend to observe the maximum oscillations, which in case of our sun tends to be 1/5 minutes, right? And there is this thing known as delta nu, which is the spacing between two L equal 1 or two L, more specifically two L equal 0 things. So you'll find that all these red lines are almost equally spaced. They are not exactly equally spaced, but almost equally spaced. And they are very good diagnostics for the variation of sound speed throughout the star. So, and people have found that this nu max, like where this spectrum peaks and these intervals are very well correlated. So if you can measure one, you tend to measure the other one very well. So the power spectrum, as I mentioned, shows peaks at allowed frequencies. Now for a given n, which is a radial order, which indicates radial oscillations, and an angular degree L, which belongs to the spherical harmonics, all values of m in an unperturbed case tend to lie at the same frequency, which we'll refer to as nu NL. Right, and this will be a very useful thing for the next part of the talk. So now this diagram, so I'll talk about it in short. So what happens that there are two types of oscillations which are allowed in different kind of places. So a star can have a radiative zone where no convection takes place, but all the heat is dissipated via radiation by random walk of photons over the star's volume. And there are some spaces where the temperature gradient is so large that photons are the mean free path is small, so the photons are unable to carry it. So what helps in transferring the heat is known as convection, which tends to happen in a jar where you heat water and so on and so forth. So yeah, so this line, this bold line, tends to indicate the place where the star is radiative, right? So in the first around 70% of the star, our sun is radiative. So this is the solar. Please disregard these terms. These are very complicated terms. The Lamb frequency and the Brand-Weissala frequency. So what they indicate is that you see these dotted lines, and you can note this bold line, right? So all G type of modes. So there are specifically two types of modes: G types of oscillating modes and P type of oscillating modes. I won't get into details, but in the radiative zone, G modes are dominant, whereas in the convective part, so in case of sun is the outer 30% of outer 30% radius. So over there, convection is predominant, and hence the P mode counterparts are very visible. So any excuse me. So for L equal 1, so these are L values. So for L equal 1, those modes which are either on the right hand side of both this bold line and this dotted line, they are measured, and the other frequencies, as you can see, are trapped inside. So for the sun, we don't usually get any G counterpart because the oscillation modes in this cavity cannot leak out to the outer parts. There is some probability, it's a huge observational challenge. Our group is working on that as well right now. Other members of my group, not me. So what happens is that the oscillation modes decay over this length, and then they get coupled to the P modes in the outer part. But this thing is not the transfer of the inertia of this mode to the outer mode is very small, and hence they have almost negligible contributions. But we are trying to use AI techniques in order to detect such leaking of modes. Even though minute, we are trying to identify these leaked modes and all. So this is the solar spectrum. It's a very beautiful spectrum. This was measured by the Golf Observatory. And yeah, so as you can see, there's a beautiful peak. These are very well spaced. So for sun, we can measure L values, the spherical harmonic cell values up to 200, 250 as well. I think more, I'm not very well acquainted with the helioseismic counterpart. Tend to work more on the astroseismology, where observation limits us to only L equals 0, 1, and 2 modes. Right? So these are the P modes in a Kepler-like star. So over here, the best you can see is L equals 3 modes. These are very small notches over here, right? And there are L equal 1 modes adjacent to L equal 3, and there are L equal 0 and L equal 2 modes very closely spaced. So this is for a star, a very good star known as the 16 Cygni. It tends to have a binary companion and exoplanets as well. So now this is a particular model profile for the same lamp frequencies and the Brandweiser frequency, this blue region, and the lamp frequencies, which are these S corresponding to L equal 1 and L equal 2. So now you see that this has reduced to the order of 0.5 or so. So this line indicates where your maximum power of oscillation is observed, the new max. So you tend to observe only in this vicinity, let's say. So what happens, this thickness here is so small that the modes which were trapped over here for the sun now can tunnel through, and they can couple to the outer oscillatory P modes. So what happens, inner information now tends to leak out very slowly into the very different number of modes which tend to be visible at the surface, because only the P modes which are in the outer part actually come up to the surface and show their presence. So now for red giant, so RGB is basically red giant brown stars. Red giant brown stars, as I mentioned earlier, are very evolved stars which have gone past the main sequence phase, and I'll discuss them in further details later. So this helps us to study a lot of physical properties, like how angular momentum is transferred in from the core to the envelope, and these are bizarre observations, bizarre studies, so which actually contribute a lot to stellar evolution theory. Next, yeah, so this is the power spectrum for a certain red giant star, whose data was collected by Kepler. So what you now observe is that you don't have a single L equal 1 mode. Now what happens, there are L equal 1 modes which were trapped inside the radiative core, and now they couple with each other, and what they do is that they mix and split a single mode into multiple parts. So it was basically one like this. Now due to coupling from the inner core, what happens is that this splits, and now you tend to observe a forest of L equal 1 modes which are coupled to the inner part. You don't have to like understand much about these stuff. I can explain if you want, given time. So yeah, so these are very important elements which actually give us information about the interior of the star. Also L equal 2, L equal 3 modes couple as well, but upon coupling and splitting, their amplitudes, so what happens is that an amplitude divides into 4 parts, because the total power of the mode has to be constant, right? So the L equal 2 and 3 are already very small. So if they are coupled and split with the injection from the inner cavity, the mixed mode, their power goes down by a factor of 5, 6 and more, and hence that gets lost in the noise part of your signal. So yeah, here I've mentioned a little about red giant stars. So they have an inert helium core, they have hydrogen burning in a shell. So this hydrogen burning thing is very prominent over here. So basically hydrogen fusion happens in a very small shell, in a very small radius around the core. So hydrogen is fused in a shell, the mean molecular mass rises, the core contracts heats. So this is the evolutionary phase of the red giant. So they have a very deep convective envelope. So as you have seen for the sun, only the last 30% was the last 30% radius showed convection. Whereas for a red giant branch star, almost the outer 90% of the star is convective, and only the inner 10% radius is where you can your core is actually radiative. And so because it's so closely packed over there, the inner modes can couple to the outer convective regions modes, and the information tends to leak out. So this diagram actually shows how in the main sequence phase the magnetic field is generated via dynamo processes and all. And as it runs out of nuclear fuel, so what happens is that this convective envelope deepens from the surface, it comes down towards the center, and the whole magnetic field which was diffused inside the star, it gets more compact. So the blue lines indicate the poloidal component of the magnetic field. So basically it's like a bar magnet, equivalent to a bar magnet. But there is something, this brown ring, which indicates the toroidal counterpart. So what happens is that your magnetic field lines go about like this. So it's basically a circular magnet which has been attached end to end, right? So now this thing is an axis symmetric phenomenon. So if you change your angle phi, it doesn't change much. This is a basic assumption which is taken into account because there are much more complex theories, but their contributions to data is almost negligible. Even the contribution due to the toroidal counterpart is negligible. I won't discuss that in much details because it has a hell lot of theory. So yeah, so these are for less than 1.1 solar mass stars, and this is for stars which have a mass of more than 1.1 solar mass. So as they evolve, this is known as the subgiant phase, which is an intermediate between the main sequence and the red giant phase of a star. So as this convective envelope deepens, the whole magnet is compressed into the core, right? And the magnetic field tends to have such a profile. So these are the magnetic field components in the radial direction, in the azimuthal, in the polar direction, and in the azimuthal direction. So this azimuthal thing indicates our toroidal stuff, which I have shown earlier in using a brown ring over here. So you can see that the rest poloidal counterpart has a much larger magnitude, and also it turns out that even if you had an equal magnitude of toroidal field, the contribution to the signal would have been much smaller than the same magnitude of poloidal field. So this happens in the radiative core. This is not the surface. So the surface extends much beyond this. So this is almost the top 10%. So the innermost 10% of a red giant star, and it's zero all along till the core, till the surface. So most of the magnetic field is trapped inside. So now back to some theory. We have discussed a lot about the interior stellar structure. So magnetic field has, so we use a next order of perturbation to the system, which comes from the Lorentz stresses, right? It's because of a Lorentz force. You consider that not much charge is present, but a decent amount of charge is present. Let's say lambda square contribution, perturbation contribution to it. So you accommodate for the so the tension, the stress, which so not mental health wise, but physically, there are terms which are known as shear, stress, and tension, etc. So these are the terms which accommodate for those. And yeah, so the way in which they impact, so what happens, your L equal 1, let's say, was like this, with all m equals 0, m equals plus minus 1 coinciding at the same space. Okay, can you guys see me along with the slides? Because I tend to use a lot of hands and fingers and so on. So
yes, you can be seen, absolutely.
Okay, cool. So what happens, all m equals plus minus 1 and 0 tend to be together unless there is some perturbation, and like magnetic or rotational or other large scale flow perturbations also. So what happens, excuse me, so what happens upon magnetic perturbation is that this splits like this is the m equals 0, this is the m equals plus minus 1. So all three of them shift, but the m equal 1 tends to shift, I guess, more, yeah, which is prominent over here, that the m equals plus minus 1 for this is for l equal 1 and this is for l equal 2. So for L equal 1, the plus minus m part tend to shift more towards higher frequencies. So this is a positive shift. And the m equals 0, 1 shows some shift as well. But it's not as large as m equals plus minus 1. So you tend to see the shift in the frequencies, and you see a symmetric and asymmetric splitting. It's not that it's splitting like this, which happens for Zeeman effect and so on. It's the same perturbation technique which you use over there, just that it's a quantum counterpart. This is a classical counterpart. You account for transfer of modes, quantum tunneling and classical tunneling of modes are very similar. We use the JWKB approximation as you did in quantum mechanics. So the underlying physics is pretty much elementary master's level thing. So what happens is that these are split asymmetrically, and these frequencies tend to shift as well. And for L equals plus minus 2, what you notice is that the M equals 0 mode, so there are 5 frequencies now, right? Because L equal 2 has M from minus 2 to plus 2. So the M equal plus minus 2 shift this way, the L equal 1 shift further, and the M equal 1 shifts even more further away, right? So this is the contribution due to magnetic perturbation. I am not going into the calculations because, yeah, I don't have much time, number one. Yeah. So now there is perturbation due to rotation as well, and the splittings due to rotation. So they come from Coriolis effect and change of reference frame. Your frame of reference, the star is rotating. You go into the co-rotating frame. Then you compute the Coriolis effect, and then you come back to your frame of reference. So all these terms are taken into consideration, and you find that now the splitting of the modes is symmetric. So the M equals plus minus 1 tend to shift like this. For L equals 2, all 5 modes shift like this, right? So when you use both magnetic and rotational perturbations, right, what you see is a splitting like this, which goes to negative values at larger frequencies, and which tend to take positive values at lower frequencies, and there's a crossover because somewhere it was positive, then for the same M there is, so for magnetic perturbation it had moved towards right, but because it was a negative M value, because both positive M and negative M both move together towards the right, now because of rotation they further split like this. So that's the thing you observe. That's where this zero crossing happens. Each mode, each splitting becomes like they tend to cross each other, so on and so forth. So that was the net splitting due to rotation and convection. By theory modeling, you have codes like MESA, Gyre, and so on and so forth, which help you calculate, like model a star. You put in your magnetic field into your system where you have calculated the eigenvalue problem for the same, and so on and so forth. Then this is the trend you get theoretically and via modeling. Now these are some observations. This has been recently published by Lee et al. In their Nature paper around a few months back. So you can see that there are asymmetries over here, right? The modes are not equally spaced. This gap is smaller than this one, this gap is smaller than this one, this gap is smaller than this one, and is the same frequency power spectrum which has been split into different parts. So basically it's like you had a long tube, you cut them into pieces and you stack one piece above the other. So you see that there is asymmetry in red giant star power spectrum, and it has been very well studied, I guess, but there are controversies as well which we are trying to address, because we aren't in some way satisfied with the study they have done, and we are going through another different approach where there is no approximation. We tend to do a generalized study. It's a very long theory, very many formulas, formulae and all which have to be taken into account. So this is for a particular star, and they have done the study for 3 different stars where they have calculated the square, the RMS of the radial component of the magnetic field using these asymmetric splitting components. And these you don't have to like understand what this is, because these are very specific to the age of a red giant star. And this a is a parameter which they have taken into account, is how the magnetic field axis, the symmetry, the axis around which the magnetic field is symmetric, is oriented with respect to the rotational thing. So there are a few more terms which are taken into account, so on and so forth. And these are the approximated, these are the first study of internal core magnetic fields which have been published ever. So I'll try and wrap up. I have a minute or two, I guess. Yeah, so what we are doing is that we are using a much generalized theory where no approximation is taken into account. So they have neglected a few terms in the perturbation equation as well. They have said that this might not contribute much, but we are working on that to see if there is some deviation from the same, and so on and so forth. So what we do is we calculate the sensitivity of different components of different regions in the star to the local magnetic field. So it might be that I slap someone, that person is not so sensitive, he won't react much. Okay, so if you hit a person on the back of his head, if he has a tight, let's say, a tighter neck, then he won't respond much. But a person with a lighter neck will tend to respond much more to the same perturbation or the same slap you give on the back of his head. So that's what we compute in our approach. And then we incorporate different models of magnetic field configurations, and we compute the splittings corresponding to them. We have some results which are in some limits equal to what they had found in the earlier theory, and some deviations as well. We are still working on it. So nothing conclusive right now. So yeah. So we conclude that magnetic field and rotational profiles in evolved stars where the core information can be propagated to the outer parts of the star are detectable via astroseismic methods. There are splittings which are symmetric for rotational but not symmetric for the magnetic perturbation, and different topologies of magnetic fields yield different variation in the splittings. So here are a few primary references. There are many more, but I haven't included all their theory. So this was the oldest paper which discusses magnetic field perturbation, and this is the paper we are referring to and working on. We have done a good amount of work on using this. This is the very recent paper, Nature paper, very well taken by the community, and these are few other papers which show the splittings, the modeling and splitting. Finally, I would like to acknowledge my guide, Professor Shravan Hanasoge, my like seniors, Mr. Srijan Bhatidas of Princeton University and Mr. Siddharth Danpal of TIFA Mumbai. I would like to thank my family, my peers, and my seniors, mentors, as well as juniors who have taken so much time out of their very busy schedules and doing this for people who want to actually come into this line. So clap for all of you for taking up this initiative, and thank you. Any questions? I don't think I have much time, but still I can.
Thank you, Shaunanikda. I don't think we have any questions, but then your talk has received a lot of appreciation, I mean, here and there. And I had a junior telling me that, a junior means he's from B.Sc, telling me that he actually understood some of your words. So thank you for bringing it down to the level of us. And you have really done an excellent job in that. And thank you for taking out time from your, again, busy schedule. And thank you again for the appreciation that you gave to us at last. So we are very moved by this gesture. So thanks a lot.
They're good. Good luck to all of you.
Thank you so much, Shatanigda.
Yeah.
Okay.
I quit now.
Yes.
Good luck with the rest of your talk. Sorry, I won't be able to stay for longer.
It's okay. Thank you for taking out time. Yeah.
Right. Good luck.
Okay. So okay, we'll move on now. But before we move on to the next talk, we would like to make a slight detour. Okay, so I understand we should have done this before, but then hello and welcome to the Young Physicists Meet. So first of all, we are extremely sorry, okay, for our initial hiccups. We lost much of our time initially for the inconvenience caused. Now we would like to introduce ourselves. Again, it seems kind of odd at the middle now, but you know how it is. So basically, we are a group of students who graduated from Ramakrishna Mission Residential College, Narendrapur in 2021. Now, this is a small informal conference that we have conducted. Most of the speakers that you see here have been students at RKM Narendrapur. We have also invited distinguished PhDs and postdocs from esteemed institutions, both from India as well as abroad, as you'll see. Now, the object of the conference has been a little different. It has mostly been as a source, to groom the researchers of tomorrow, and in order to just provide them a window, a peek into the state-of-the-art research that's happening nowadays in various esteemed institutions. Now, the talks, as we have requested our speakers, the talks have been tuned down to the level of the M.Sc students and the PhD first yearites. I would like to thank all the speakers for attending this meeting. Thank you all the attendees who have been here. Thank you for your interests in this conference. The speakers have actually made from their extremely busy schedules, as you guys must be knowing how difficult and time-consuming PhDs and research is. So. This is our initiative from this side. I hope you all enjoy this conference. We will now like to move on to our next speaker. I would like to introduce the next speaker, Mr. Hiranmoy Das from IISc Bangalore. His field of research is Condensed Matter Physics, and he will be talking on a brief introduction to something known as toric code. I'm really interested to know about this. So Hiranmoy Das, sir, the stage is yours.
Yeah, I think you guys can see me, right? And hear me as well.
Yes, you are visible.
Oh, fine. Okay, so let me share my screen. Can you see my screen?
Yeah.
Hello?
Yes, your screen is visible, yeah.
So the cover page should be visible, right? Okay. Can anyone respond? I can't hear anything.
Yes, you are visible.
Okay, sure. Okay, so as it has been introduced that I'll be talking about a brief introduction of the toric code. Introduction to application of this quantum computers. He talked about how we can simulate many body systems using quantum computers, and this talk is also about quantum computers, but not using quantum computers, but to build one. So as you know, this guy Sundar Pichai, he is Google CEO, and fancy object that he is standing beside is called quantum computer. So what is the benefit of this quantum computer? So as you know that our computers, modern computers that works with bits, that is 0 and 1. But then quantum computers has advantage over these classical computers because they can use linear combination of 0 and 1. So they can use this linear superposition principle of quantum mechanics to perform tasks parallelly. So that is the advantage. But then when you go to build one quantum computer, you will realize that these qubits are very sensitive. Because when in principle we talk about these qubits and all, we always assume that they are kind of in isolated environment. They are not talking to anybody, but that is not correct. So they will always interact with their environments, and because of that, there will be noise in the system. So that is the main challenge in building quantum computers, and that's why even though this is very fancy object, the thing that you can see in the picture, it has only 53 qubits, which is very less if you compare with your computer, which has some GBs of memory and TBs of this hard drive and all. So then to reach there, we need to solve this problem of stable qubits. So then the question is then, can we build a stable qubit? And that is the whole point of this talk. So now these problems are very old. So when in past days, people used to communicate using normal bits, then there were also problems. If you are encoding some information, or if you are sending some bit to a distant place, there can be some noise in between, and the person who is receiving this noise, receiving that data, might get a wrong message, right? So how do you tackle this problem? So the way to tackle this problem is, I mean, if you think about it, there is one simple way. So instead of sending one bit, you send 4 copies of that bit. Okay. So if one bit is affected, still you have 3 bits to get a correct result. So the same idea is applied here, and it is quite old idea. So people have applied these things in classical things, and these are called error correcting codes. This is called code because there are a lot of qubits or bits, but they code for one particular bit. Okay. So Hamming was the pioneer of this field, and the code he implemented was called 7/4 code. As you can see, it was discovered in 1950s. But then how do you do this in quantum computation? Because in quantum mechanics, as you know, there is something called no cloning theorem, which says that you can't make, if you are given a qubit, you can't make multiple copies of that without knowing what the qubit state is. So then there is some clever technique which is discovered by Peter Shor, which is called Shor code. So he used quantum gates to perform this kind of task, and so that thing is a bit complicated, and there are several versions of that which people came up with later. But then this Alexei Kitaev in 2003, he asked a different question. He said that whether we can do something at the physical level. By physical level, I mean when you think about your hard disk or something similar, then you see that those storage devices are also storing informations, and they're quite stable. If you store something, if you save an image now, you can see the image even after 1 year or 2 years. So how is that happening? Why are they very stable? If you think about that, you will see that those storage devices use these ferromagnets. So what happens if one spin gets flipped in this ferromagnetic domain, then the rest of the spins are telling that spin to flip again and come to its natural position. So that is the idea. Like if you can make a system, make a kind of qubit where if some noise happens, it will be corrected automatically by the system, then you are done, right? So that is the motivation of this toric code. And I think by now you know why this is called code, because we'll be using multiple qubits to code one qubit. So that is the idea. Now, to see how that works, we start with square lattice with periodic boundary condition. Okay, and then on the edge, on the bonds, we put some spins degrees of freedom. Then once we do that, so I have drawn only 3 spins, but you can imagine that all these bonds have similar spins. Then we can define something called star operators, AS, which is product of these spins. So let's say star operator at this vertex is basically product of this spin, this spin, this spin, and this spin. So by spin I mean this Pauli operator, sigma x operators. Similarly, we can define something called Placket operator or flux operator, BP, which will be product of sigma z operator of these bonds. I guess you guys can see my cursor, right? Hello?
Yeah, it's visible.
Yeah, cursor is visible, right? Okay, fine. So yeah. So then once we have defined these things, now you have a spin system, right? There should be some Hamiltonian which will govern the spin system, and that Hamiltonian will be given in terms of these 2 operators. So what does it say? It says that that this Hamiltonian is sum over all such star operators of this all these vertices, and sum over all these Placket operators of all these vertices. Okay, with some weightage, of course, H and J. So once you have this Hamiltonian, you can see that this AS1, so let's say at this vertex it is AS1, at this vertex it is AS2. Then if you check the commutation relation, you will see that they commute. Similarly, 2 Placket operators also commute, and something which is not very, so these guys commute because you can see they are made up of sigma x operators, right? So when you take sigma x operators and then you take the commutation relation, you know that they will commute with each other. And similarly for sigma j's operator. But when you take commutation of AS and BP, that also commutes. And it commutes because if you bring, so here you can see that these spins are different, so they will obviously commute. But even if you put this square here, they will kind of cross at 2 points or even number of points. That's why the commutation relation here will give you -1. Here it will give you again -1. So -1 of -1 will give you plus same thing. So in that sense, you will get the same state. So basically, the gist is this operators commute with itself. So you can so they commute with Hamiltonian also, and you can write the simultaneous eigenstate of this Hamiltonian AS1 on BP. So then, as this AS or BP are only product of this sigma x operator or sigma z operators, their eigenvalues will be +1 or -1, the product of these operators. So then AS, when act on psi, one eigenstate, will have plus psi or minus psi, and similar case will happen for BP. So the ground state can now, it is easy to imagine, it will be just positive eigenstate of this AS operator and BP operator for all A's and P. Here A's and P are basically these vertices. So at each of these vertices you measure, you basically apply this star operator or this Placket operator, you will get +1 eigenvalue. So that is the ground state. Now why are these things interesting? That will be revealed later, but let us before that let us look at the excited state of this system. How will you get excited state? Okay, so far do you have any question?
So you are only considering the nearest neighbors, right? I mean, for the star operator, you are not taking anything on the center.
Yeah, so for star operator at this vertex, I can define star operator at each of this vertex. So star operator at this vertex is basically product of this, and this sigma operators. Okay.
So it's basically just an alternative. Yeah, so it's basically just an alternative representation of some sort of Ising model.
Not really Ising model, because in Ising model you have nearest neighbor. So first of all, there is one difference. The spins are residing on this edges and not on the vertices. And the second thing is when they are acting. So this guy is not acting with this one. Okay. And also the Hamiltonian is a bit different. Okay, but then there is something called transverse field Ising model where you can map these things. So for now, just take them as product of these bonds, sigma x of these bonds. That's all. Okay. Yes. Any other question?
Okay, Hiranmay, what is H and J here?
H and J are basically the string. So you have these AS operators and BP operators.
I mean, this is not any kind of hopping.
No, this is not hopping.
I'm trying to understand how the Hamiltonian is constructed by what is H actually.
Okay. So the idea is that I'm starting with some spins, degrees of freedom, but they are not necessarily physical spin. So I'm using them as this kind of object. So then I am defining this AS operator. Okay. So this is, it's not like I'm starting with some physical system and then I'm working on them. I'm starting with a model. So if I have these spin degrees of freedom on the bonds, and if I define these star operators like this, then if I define BP operators like this, and then I write the Hamiltonian of this system like this. So it's like a theoretical construct. It's not not that kind of physical system that I have to start with. So then the question is, if I define these things, then what interesting physics comes out from this?
Okay.
So that is the question we're kind of looking at. Okay. Okay, but the operators are clear, right?
Yeah.
Okay. Thank you. Okay. So now the ground state, as I have said, is basically eigenstate of this AS and BP operators. And when the system is at ground state, if you apply AS or BP operator at any vertex on this bond, so there is a spin, as you remember. Now what will happen? So what this sigma JZ operator does, it rotates the spin in sigma x basis. So let's say the spin was in the x positive direction, then it will be in the x negative direction after application. So what that means is that when I apply AS operator here, then one of the spin is flipped. So these spins are not flipped. So there will be change in sign. Similarly, when I apply this AS operator here, these spins are fixed, but this spin has flipped. So then what that means is that AS operator at here and AS operator at here will have negative eigenvalue, -1. So okay. So that you can imagine as two particles, two excitations to be precise. It will be E0, where E0 is the ground state energy, plus 4H. H is the same H. Now what happens? You apply sigma JZ operator again, but at this place. So when you do that, you will see that at this vertex, both of the spins are flipped. So there is no, so that negative sign that was coming is no more there. But the negative sign is shifted here, because if you look at this vertex, you will see that these spins are not altered, but this spins is altered. So now this vertex will have negative eigenvalue of As. So the process is like you created two particles, two excitations at these two vertices, and by applying this operator again, you moved the particle from one place to another. And you can do that like after, if you apply these operators again and again, but at different positions. If you do that, you will basically move the excitations from one place to another. Now, what you are doing, you are applying sigma GZ operator. So basically, and then again I run this, then you will basically create two particles and move them here. Now these two particles are different. These two excitations are different because as you have, as you remember, the Hamiltonian, one is this BP, one is given by this BP, another is given by this AS. So they will have different energy and they will be different particles. So we call this red kind of particles, or particles that I have shown using red dot, as E-type particle, and that has been written here as subscript. And this other kind of particles are called M-type of particles. Now they're similar to this electric charge and magnetic charge. So yeah, but that is not very clear here, over here, so we won't talk about it. So then I guess this is clear, right? So far, is it clear?
Yeah.
Okay. So so now our next task is to move this particle around and play with it. So we can move this particle like this, and then we can bring these particles at the same position, and then we'll see that they fuse together. So it's like they annihilated together. So then, if you look at this state, it seems that okay, maybe we are still in excited state, but no. Since there are no excitations in this state, we again went back to the ground state. So the energy is now E0 by this if we apply this thing, these operators. And the reason is that you can contract this loop to is around one placket, and you can see that if all these spins are flipped, if you apply placket operator over here, you will see that all spins are flipped simultaneously. So -1 power 4 will give you 1. So there is no change. Again, when you apply the star operators in any of this vertex, you will see that they have even number of -1. So basically nothing has changed. So you are again at ground state. But then these are not in class. To play with those excitations, and you will see that you will get a loop, right? Now, the really interesting thing is you can't contract this loop because you are on the surface of the torus. So when that kind of thing happens, some really cool stuff emerges, and this is the place where topology comes into picture. Okay, so now we can so like similar thing that we did just few minutes ago, we can do here also. We can define a loop operator, which is basically product of bunch of this sigma z operator. So sigma z along these lines and product of that. When you add this operator, you basically create two excitations over here, let's say, and then you move them around this torus and fuse them together. Now the thing is, you will again get ground state. But is that ground state unique? And my claim is that when you do this thing, when you perform this task, you will get a ground state, but a different ground state that you started with from the ground state you started with. Similar thing you can do with this M type of particle. Here blue loop is for this E type of particle. Here you can do in this direction, and you can think of them as this loop as rubber band. If you get a rubber band and if you put it like this around this torus, you see that you can't remove it, you can't contract it, right? And that is the reason why we are getting these cool stuffs. So we can do these things. Now, okay, so here are two definitions that we need to remember. This XE operator is called Wilson loop operator, which I just explained, that it is basically product of this sigma X sigma Z operators along this loop, sorry. And YE was this product of sigma X operators along this. Sorry, there's a typo here. So once you have defined all these things, you can now look at these objects. You will see that XE and XM will commute, and XE will commute with Hamiltonian because they are a bunch of the sigma Z operators, and here they are sigma X operators. They'll commute with H. So basically what it says that we can write simultaneous eigenstate of XE and XM of this loop operators. And let's say we denote those states as AB, where A is the eigenstate of XE operator. If you start with this ground state and you apply XE operator, you will get ground state, A times ground state. So that A is basically denoting one level. And same thing you can do with XM, where XM will give you B eigenstate. Now you know that A and B can be +1 or -1. So using these things, you can get 4 kind of different representations. Now let us do something. So as you can see here, that XM and YE. So what we started? So XC is this. XM would be same loop but of red color, and that will denote the product of sigma X operator. Here I can, so this XM is basically M type of particle you are creating, then moving around this torus and fusing them. YE is basically you are creating E type of particle, moving them around and fusing them. Now here the order matters. If you are doing it in the opposite order, then you will get a negative sign because they don't commute, these operators. I'm not going into the algebras because it will make you feel bored. So just take my words for it. You can work this out. So what we can do, we can apply YE operator on this state AB. Let's say we started with AB, and then we can apply XM and check what value it is giving us, because you can see that XM will tell us which ground state we are at. So if we apply YE operator on AB, that is basically you are creating 2 E-type particles and moving them around this torus and then fusing them. Then we get -B of this state, which says that after applying this YE, we have reached a different ground state which is of opposite sign, right? And you can play this game with all this combination. So the gist is that by doing all this creation of 2 particles and fusing them on the other side of the torus will give you 4 different degenerate states, degenerate ground states. Like as I have represented them as with A, comma B, you can say they will be -1, -1, -1, -1, and so on. The cool stuff is that this thing can be mapped to this 2-qubit state, like 0, 0, 0, 1, 1, 0, 1, 1. Now we are back to this quantum computation game. Now you might ask, that what is the advantage of doing all these things, because it's just complicated things, right? You could have worked with spins and things were much easier there. But then we started with spin system, we do a lot of things, and then we got this ground states. But the advantage is in the topological nature of these systems. So as you have seen that when we worked with this kind of systems, this kind of loop, we created two particles and fused them together, nothing happened. So these sigma j z operators, you can think of them as noise that is coming to the system, noise that is coming to the qubit. But then it won't affect the system unless you apply that noise along these loops, and that is very rare because noise are usually random. So that is basically applying sigma j operator here, in random places, not along these lines, not along a particular lines, because sigma jz operator along these lines will have very less probability. So basically you will require really great conspiracy to kind of change your ground state if you are at one ground state. So that is the reason why these kind of states are quite stable. And this is called toric code, because as you have kind of understood that we started with a lot of spins, and each of these spins has capability of acting as qubit. But then instead of taking them as qubit, what we did, we took the ground state of this system and we declared that those are the qubits. So basically we have coded the entire system as 2 qubit system. That's why it is called code. And since because of periodic boundary condition it is on the surface of torus, that's why it is called toric code. Now this idea is really cool, but then there are some issues with this kind of protected qubits. These are called okay. So one thing is that even if you are at this state, you need to read the qubit state, right? So how do you read them? As you have seen that when we apply this AS operator or Wilson loop operators on this system, we get +1 or -1, and from there you can get what is that thing. But then that will require global measurement. You have to put some operators at every state to measure that thing. So that is kind of difficult, and we still don't know how to implement these things in experiments. Another thing is that so this might look very kind of stable, but then you have to remember that we so far talked about 0 temperatures, but at finite temperature you have these excitations. There will be finite possibility that there will be excitations in the system, and because of that, when one excitation happens, and let's say somehow it went to the other side of the torus and fused together, then the qubit state will be flipped. It will be changed. Now you might say that, okay, I'll start with large system so that the chance of fusing together is very small. Then there is another problem. The problem is when you have these excitations, and remember these excitations can move freely without any energy cost. So what will happen is that there will be the entropy of the system will increase. And if you remember that this free energy is basically E minus Ts, right? So if you put T non-zero, then this large entropy will tell the system that you generate a lot of excitations, because although there is some energy cost, you will get entropy. You will gain entropy. So you will basically minimize the free energy, and that's how there will be a lot of excitation in the system, and there will be chance that they will fuse together to give rise to different ground state. So that is one problem. So this won't work at finite temperature, but this was preliminary ideas. So we can't think that they will be perfect, and there are efforts going on towards that direction. So another thing that this system gave rise to are called abelian anyons. So what are these anyons? So anyons are basically here in this system, this red and black, these kind of particles are called basically anyons, and for a reason. So the reason is the following. When you work with bosons or fermions, you will see that when you exchange these particles, you will get either a positive sign or negative sign. Either nothing happens or you get a negative sign overall. But then there are particles, basically quasi-particles in the condensed matter systems, where you exchange these particles, and instead of getting +1 or -1, you can get something in between, like e power I phi. And that phi can be any angle, depending on the microscopic system. Sorry.
Hello.
Is there a question?
I'm extremely sorry to interrupt you. No. I mean, as we are running short of time, can you please wrap it up within 5 to 7 minutes?
Yeah, sure. There is nothing much in here.
Yeah.
Okay,
thank you.
Fine. Thank you for reminding. Okay, so these are the reason why this is called anyon, because it can take any phase, and that E and M type particles that we just saw, they are also anyons, because you can see if you exchange them once and then again you exchange them, you end up with a negative sign if you don't exchange them. So, but then this system is a bit trivial because it just introduces a phase. But there are hope, because there are non-abelian anyons also, where by exchanging, the exchange is not that trivial. You won't get one phase only. You might get an unitary operator evolution. So those things can be utilized to give you quantum computation, because in quantum computation, what we do, we start with qubits and then we apply unitary operator on them, which acts as gates. The same thing you can do with anyons, because there is this U will act as some gate, and there are some clever technique by which you can manipulate these things. So that gives rise to a new field called topological quantum computation. The idea is the following: you start with this system, like what you did with toric code, then you get the excitations, you create these anyons, then you take one anyon, or depending on the gate implementation, you take these anyons and move them around one another to perform some gate. So something very clever happens here. Then finally you fuse them together and look at where you have reached, what is the final state. So that will tell you what. So that will basically same as performing some computation in quantum computation language. So that is stuff, and there are a lot of progress happening in this field. There are people are searching for Majorana fermions, as you might have heard, because Majorana fermions kind of shows this non-abelian statistics. So there are really cool stuff going on in the field. So you can explore these things. Okay, all right. These are the references I have used. So this reference, if anyone is interested in this field, I'll refer to this particular paper by this Kitaev and Lauman. So this is quite pedagogical, and you can learn. Thank you.
Thanks
Is there any question?
I have one question, just a small question.
Yeah, sure.
If you have, let's say, a lattice structure which has higher genus, so
higher
genus, like large number of holes rather than just one.
Okay, correct.
So would that give rise to multi-qubit system, like more than two?
Nice, very nice question. Yeah, actually, it will happen. So if I go back to this this torus, you can see that we are getting this 4-qubit system because there are two possibilities in fusing them, two non-trivial possibilities. When you have multiple geners, you can get more such kind of loops, more Wilson operators. So that will give you multi-qubit system. Indeed, yes. That will give you multi-qubit system.
Okay. Thank you.
Okay. Thank you guys for organizing this really nice conference. Okay, I hope you will continue these things.
Yeah, sure. Thank you so much, Hiranmayda. I mean, you actually introduced us to a very new concept and in a very fundamental manner. And thank you for that. It was really interesting. Thanks for taking out from your schedule. I mean, it must be busy out there. So, okay.
It's December, not that busy, but yeah, it's really cool.
Yeah, I mean, that's the thing. Thank you so much. So
yeah, thank you guys. Also.
Yeah. So we'll move on to our next speaker. Our next speaker is again our senior from RKM Narendrapur. He is Saurabh Manna. He is presently a PhD student at IIT Madras, and he is working in the field of quantum computation. The talk that he'll be presenting today will be on the strengths of quantum computers. I guess that's a very new trending topic of today. So let's go on with it.
Yeah, thanks for the introduction. First of all, can you hear me?
Yeah.
Hello.
Yes, absolutely. We can hear you. Yeah.
Okay. Let me share my screen.
Yeah.
Are you all able to see the screen?
Yeah, we can.
Yeah, thanks for the confirmation. Okay, so first of all, thank you for inviting me in this talk. Like all the students are from junior, seniors, and juniors are there. So it's nice to be present here. So, and first, good afternoon, everyone. So actually, yeah. So title I would give the talk as strength of the quantum computer. Like, so both are right. That the idea is the equivalent. Like, what is the advantage can we get from the quantum computer? Like, if we have a quantum computer, what is the advantage that we get from the classical one? Okay, so that's the idea. So yeah. Okay, let me make it full screen. How to do? Okay. So yeah, we all know that like everything in the nature is made of quantum. Like if you go take a tiny amount of particle or dust or leave anything you take, so everything made of atom or molecule. So and all are follow the laws of quantum mechanics. So in that way we can say that everything is quantum. Like underlying thing of everything that happening now and that will happen in future, everything depend on the follow the laws of quantum mechanics. So in our school days we read about photosynthesis, right? So what happen in photosynthesis? So trees take light, like mainly chlorophyll, take sunlight and water and carbon dioxide input and give two output like the sucrose and oxygen and some amino acid. So and all this process is done within daytime, like within the 12 hour or something. Now let's give you a task that we want to simulate all these phenomena of this in our computer that we are regularly use, like our laptop or desktop. So if you try to simulate all these things using this classical computer, it's not possible because your computer will take long. Some case your computer will take some very long time, or some case if your memory is not enough to perform all this computation, so you will be stuck. You cannot perform this. But nature does this very well. Like within 12 hours, it is done of everything. So the key. Okay. Yeah. So the key thing nature uses is the quantum mechanics. So the beauty is the quantum mechanics used by the nature to perform this kind of complicated concept very fast. So if quantum mechanics does this very fast or very efficiently, so why don't you use in your computation? Like why don't you use quantum mechanics in your computation? Yeah, so that's why the idea of quantum computation born. So okay, sorry. Yeah. Yeah, this way. So the one thing is that, so the idea is we have a machine which will follow the laws of quantum mechanics and give the output which will be physically realizable. So that machine you are calling as a quantum computer. And my today's talk will be depend upon how this quantum computer work and how it will be. What is the future work we can do? Where is okay? Sorry. Where is it now? So where is the current stage of our quantum computer? Yeah. Sorry for the mistake that I did. Sorry. Yeah. So near to 1981, if I near to 1981. So in a conference meeting in MIT, so people are talking about reversible computing. Like, is there any way to perform some gate in reversible way? Like if we take an example of an AND gate, so what it did, it take 2 input and give 1 output. And now if you want to backward direction, so you get only 1 information, but you are giving 2 information. So there is something is missing in your output result. So this is all these things are not reversible. So now if we take more and more NAND gate, so you will be, you definitely can say you cannot go reverse one. So at that meeting, Einstein stood up and say that, I have a one theory that which is reversible. So so his idea is to use quantum mechanics to use computation. So basically we can say that Feynman is the pioneer of quantum computing, today's quantum computing. So okay, so in our classical computer we use 0 and 1 as few of our previous talk we saw that Q bit or something, and which is different from our classical bit like 0 and 1. So what is Q bit actually? So to understand Q bit, let's take a Hamiltonian system, which is a spin-half system. So spin-half system is a 2 level, like spin up and spin down. So here I am denoting, if you see my cursor, so 0 as a minus half or the lower energy state, and plus half is our excited state. So now the total state of the system will be the superposition of these two. This is by the laws of quantum mechanics, and this alpha and beta must follow the normal one condition, like mod square of these two, and sum will give the identity. So to preserve the probability. Now this alpha and beta both must be less than 1. The mod will be less than 1. From this relation it is clear, but there may be some page. So we can model this alpha and beta in this way, that so this alpha we can say as some parameter, so which parameter to write alpha and beta. So let's say your alpha is cos theta by 2 and sin theta by 2, and we add a phase here, it is I phi. Now so there are 2 parameter, so theta and phi are the 2 parameter. So this theta and 2 phi are the 2 parameter. So we can say that we can perform a 2-dimensional surface. So here is the surface is the surface of a sphere, which is a 2 parameter, and dimension is also 2, like dimension of the surface of the sphere. Yeah. So here theta means the angle about the z-axis, and the phi means the azimuthal angle, the same as we use in our polar coordinate system. But the difference is here we use theta by 2 instead of theta. Like all these states 0 and 1 are orthogonal, and our theta will be from 0 to phi. So to make that sense, so we use theta as instead of theta, use theta by 2. Like if you put theta equal to phi, you will go to 0 state. You will go to theta equal to 0 means, theta equal to 0 means 0 state, this one. And if you put phi, that means the downward direction, this is the 1 state. Okay. So in this psi is called our qubit. So qubit means the state of a quantum 2-level system. So it may be a spin-half system, in maybe in other system with having 2 level, like atom of 2 energy state. So that can be thought as a qubit. So as bit like 0 and 1 are the basic ingredient of classical computer, here we use quantum computer as a play that same role in our quantum computer. So let's take two parameter for classical case and the two quantum system, two qubit system, like two identical spin half system. Here in the previous case, we take single qubit system. So now we are taking two qubit system to understand what are the advantages in it. So if you take two qubit system, like two identical spin half system, so we can get that the total the Hilbert space dimension will be 2 to the power 2. 2 square is 4. So so you can write the basis in terms of each individual subsystem. So yeah, so these are the bases 0, 0, 0, 1 and 1, 0, 1, 1. So all this part is all you know, right? So now we use the logic here, like, so let's take 2 qubit and let's take 2 classical bit. So here A and B are my two parameter which will play the role of classical bit. Like A can be 0 or 1 and B also can take 0 and 1. So yeah, and another on the other side of quantum case, we take 2 qubit. Like, so if you write the state of a 2 qubit, so it will be superposition of all these bases. So here you are getting alpha, beta, gamma, delta. So look, you take 2 qubit and get 4 parameter. But in classical case, 2 qubit gets 2 parameter. Yeah, 2 bit means 2 parameter. Yes. So for you are taking 2 qubit, you get 2 times more. You can store 2 times more information by taking 2 qubit instead of taking 2 classical bit. So now if you take n number of qubits which is equivalent, so like if you store information, if you need n qubit to store some information, and if you want to store same amount of information by using your classical bit, you need 2 to the power n number of classical bit. So from that comparison you can understand that. So if let's say for numeric, so let's say n equal to 300, so you have 300 qubit and you store some information by using all the 300 qubit. So now if you want to save or store the same amount of information, so for that reason you 2 to the power 300, which is near to 10 to the power 90 or something, 90, yeah, 90 or something, yeah. So you need that much of classical bit. So we can imagine that it's a very huge numbers. But in quantum case, you require very few of them. So this is the thing. Yeah. So now, so we understand what is qubit and how it can store more information than classical bit. Now let's say we have qubit and how it performs. And is there the advantage, like, so if we use more and more qubit and is it equivalent to computationally faster or something, or how do we use in a processor? So we have qubit, let's say Q1 and Q2. So by mistake is a typo. This is not Q1, this is Q2. And this FX box is a quantum processor which take 2 qubit as input and also give it output as output. Give also output. And on the other hand, this is a picture of classical computer. So here we make all the thing parallel. Like, so if we have 2 qubit, that means we need 2 to the power 2, means 4 classical bit to perform the same operation. And what we did, so here we have 4 processor, and all the four processor work together to perform the same operation. So again, here is also one comparison. So here you are using only one quantum processor to perform the some operation, and the same operation, same task can be done by a classical computer where you need 4. So from that comparison also you can understand that your quantum processor or qubit give the more advantage here. So this is the comparison I told previously. Like if you have n equal to 300 and classically it will be equivalent to 10 to the 90 order. Okay, so let's take an example to combine this idea of using qubit and quantum processor. So let's take this square box is our quantum processor, and here we are taking 2 input Q1 and Q2. So 2 qubit means 2 system. So let's say your first system is in 0 state and your second system is in 1 state. Okay, and you want to perform you want to get output which is a Bell state. So you want to get this output. Okay, so what you will do, so I don't go to details how you do, like you need to use, I just use the gate that are required to perform this thing. One is Hadamard and CNOT. If you don't know, don't just leave it. Like the idea is, the main important idea is, so there is some circuit inside that processor. If you give 2 input, it will produce a Bell state psi plus. Now this is an plot which is this what is called the Bell state is prepared, is done in a real quantum computer, like I think is a 5-bit quantum computer in IBM. So in the left hand side are the 4 state, like the base is 0 0 0 1 1 0 and 1 1. So ideally it will be one coefficient at 0 0 and same coefficient at, but equal weightage coefficient in both bases 0 0 and 1 1. But if we see that the output of your result, so it's near 2.5 and it's below 0.5, but there is a non-zero probability of getting 0 1 and 1 0. So we'll come to that part later. But till now this is pretty much okay. Like we'll come to where this error is happening here, and we'll come later. So this is the result, which is this result is performed in a quantum computer of IBM. Okay, and this work is not done by me. Actually, I take from online source. If you Google it, you also can find it, and it's not very hard to simulate also. Yeah. Okay, so now let's play a game. So I give you a task, like I give you a number which is a semi-prime number. Semi-prime number means it is a multiplication of 2 prime number. Okay, so our game is, I'll give you one semi-prime number. You need to tell the 2 prime number. So here I give you 15. So it's very easy, right? So the two prime factor are 5 and 3. Now let's increase the difficulty level. So let's I give you that number 9991. So what is the prime factor of these two? It is hard from the previous one, right? So also you can do it analytically, like if you need to spend more and more time to perform this. So this is a multiplication of 103 and 97. Now I increase difficulty much more. So let's say this is your number. This is a semi-prime number. I told you that this is a semi-prime number, and you need to find the 2 prime factor. Now, in analytically, you cannot. It is not possible to do this problem. So you can take the advantage of the computer you have. So if you use that, yeah, you can easily get it, but it will take some time. So this is the 2 prime number. So this is, you can understand, this is a very large prime number. This is also a very large prime number, and so it is taking time because these 2 prime number are very large. So that's why to decouple these two things, it's taking time. Now go to some extreme level difficulty. Like let's say I give you the semi-prime number of order of 10 to the power 200. So if you perform like same game, like you need to find out 2 prime factor of by using your classical computer, anything that you have till now, it will take near to 1,000 years or something. So basically you cannot do by your classical computer anything. You cannot break this semi-prime number order of 10 to the power 200 by using a classical computer or anything. So there is one point you can think that we have something which cannot be break by our human also and the computer. So we can use this as our security protocol. So this idea is used in this prime factorization is used in RSA encryption. Like you have a public key. Public key means some people give you the semi-prime number, like multiplication of 2 prime, the answer of the multiplication of 2 prime number, and the customer or the owner have the key. Key means the one of the prime number of your 2 prime number. So if you have 1 prime number, now it's very easy. Like you just divide the semi-prime number and get the other number. You get the 2 factor. So otherwise, if the prime number is very large, so by any chance you cannot, there is no way to find the two factor in a finite time. So now if you have a key like 1 prime number, you can open the lock, like you can decrypt that information that are encrypted by this RSA encryption. Now, so till now we say that we cannot break the RSA encryption, but in near to 1994, Peter showed that if we have quantum computer and by using source algorithm, we can factorize the prime number within a day, like within a polynomial time. Like in the previous case, which I said near to the 1000 year, it can be done within a 1 day. So it's pretty fast. So actually you can perform you can perform the factorization. Yeah. So this give a this give a very, so at 1994 it gave a very good amount of, what can you say, attention to this quantum computation field, like some company, Google, IBM or other. It'll take more attention to it. So yeah. So now you are asking that we have quantum computer, which we performed in the previous slide. Like this, I say that this is a result of a quantum computer, and we are saying that if we have quantum computer, we can break the encryption. So how can we use that encryption till now? Like encryption is our online payment, like credit card payment or any other online transaction, or if you place RSA encryption use, and we are saying that we can break it by quantum computer and source algorithm. So why this is not happening till now? Why we are not stopping to make payment? So the thing is that, so to perform source algorithm, you need a sufficient amount of qubit. We are not able to reach at that level. So yeah, so your credit card payment and your online transactions are safe till now. Okay. So as we said previously, that we cannot so now the trivial question arises that why you cannot reach at that level of a large number of qubit. What are the restrictions that are making? So to point out this one, so we need some idea of entanglement. Someone also in previous talk someone defined entanglement. Not yeah. Let me define it simply just 2 lines. So let's take a two system, like 2 bipartite system, and let's take phi 1 and phi 2 be the state of individual system. Now, if we write these 2 systems in a tensor product way, or this is in this way, the tensor product of phi 1 and phi 2. So this is called the product state, and if you cannot write this state, total state of a system in terms of tensor product, so you can say that your state is entangled. This is a rough way of saying that entanglement. There's some other way to define rigorously the what is entanglement, but this is a rough idea, you can say. Okay, so how this entanglement affect in your restricting? So how this in entanglement affect to increase your more and more qubit? Okay, so every time you take a system, it must have a surroundings environment. So what happens is that the system, it contains some of the qubit. So this qubit interact with your environment. So what happens? The state of a system is now become entangled. Like entangled means, so because of this interaction, this state of a system become entangled with the environment because of the interaction of the environment and system. If the system is isolated, then there will be no entanglement. But this is not possible. Like if you have some isolated system where you cannot perform anything, any measurement or anything. So how can we use that one? So you must have an environment there. So what happened is that, so I say you about the block sphere. So this is called the block sphere. Like state of a system can be represented on a sphere, which is called the block sphere. So now if system and environment interact with each other, the state will not remain on the surface. Like this is all the it will be inside the sphere. So if you take all the possible state, it will no longer remain a sphere. It will become ellipse, or sometime it become a circle of lower radius lower than 1. So that kind of error appear. That kind of error appear when the system is interact with the environment. Okay. So this is a pretty much idea about quantum computer and why it is restricting us to go to use our source algorithm to break the encryption. And so let's go to my core field of research, like the field I am working on. So I am working on this entanglement of system with the environment. Like, so this is called the so your system has some information, like your system is in one state. So when it become entangled with the environment, like some of the information of your system go to the environment because of the entanglement. So what happened? System interact with your environment and it become entangled with this environment. Then your information inside the system leak to the environment. So we can similarly thought that your information is stored in your system and somehow at time evolve, it become decay surroundings. So this effect is called scrambling. So I'm mainly working on this scrambling part, like information scrambling, like what I said. So let's say we have one system, let's say system 1 is your system, and the system 2 is your environment you can thought of, and you have, let's say, 2 operator. Like operator means here in quantum mechanics we use observable as operator. So let's say green color is a one operator and this blue one, not pink, pink is another operator. So now if we evolve, like because of the interaction, what happened that this operator will get a support of the whole system itself and it go to the other system also because of that coupling. Coupling means there's interaction. So that's why saying this spring kind of thing. So this is not a spring, like coupling, they represent it as a coupling. So this is called the scrambling. Like if you saw the lower figure, so this was a pink initially. As time evolve, it become scrambled throughout the space. Okay, so this scrambling phenomena depend on many things, like what is the diamond, like if your system is regular, this information scrambling or information spreading will depend upon that. If your system is regular, then information scrambling will be slower, and information, if it is chaotic, it will be exponentially fast. So all this, that means for different kind of system, you can see this paper by Urul Lakshminarayan and Ravi Prakash. Those are our colleague. So you can, for more details, you can see this paper for in this topic of scrambling. And now recently we are focusing on this type of system, like behavior of the system. Let's say your both system, instead of taking all the bath as an environment, let's take a two single system. So I talk about this environment interaction. Environment interaction means there are a lot of systems are there around surrounding your system, main system. Now let's first take a simplest case of it. Like say you take two systems which are connected to each other, and take various conditions, like what happened to this one is chaotic, another is regular, and one is chaotic, one is mixed. And let's say the other combination like mixed and regular, mixed and mixed. So how this information scrambling happen? How can you resist it? Or how this behavior can affect you in your scrambling part? That part we are currently focusing on. So if you are interested, you can ask in this topic if you want more details about it. Okay. So till now, what we discussed. So how I show that how quantum information store more information than classical bit, like 2 to the power n number of classical bit equivalent to n number of qubit. Now, so that if we have a good quantum computer of many bit, we need source algorithm and we have source algorithm. So using that, we can perform, we can get speed up in prime number factorization, and but all these things are restricting. All these things cannot happen till now is because of that error happening in your quantum computation. Like each step, one error may be added. So yeah, so you are not getting the output result that we are expecting, and the main part that error is occurring is because of the scrambling, but like entanglement with the environment or interaction which causes the scrambling part. So all these are restricting to us. Yeah, thank you for the attention, and this was pretty much.
Thank you so much, Manada. There's one question. I mean, you can see in the chats as well. Like it goes something like, do we have to calculate the 0 cross 1 by tensor multiplication by knowing matrix form of 0 and 1? So that's the question.
We have to calculate. Yeah, you were asking about how to calculate this one. Like if you are having like 0, 1, 1 state, you have another one is you have a matrix form it. You want to calculate or something. What can you say? Can you say in a speaker? It will be clear. Hi, Somadip.
Shomadip Ghosh, are you there? I think he's not there. Although what I feel is that like he wants to understand whether if we know the matrix form of 0 and 1 states, I mean from there do we do that tensor multiplication and thereby we calculate? Is that the method? I think.
Yeah, that way you can do that. Like so, that is a one approach. Like you are okay. So you are talking about two approach. Like one way that you are rigorously calculate the matrix form it. Like when you are writing matrix form means you are going to the abstract space to some known space. Like you have some basis or something. But when you are using directly the Dirac notation, that is abstract thing. So if you can, both way you can do that. But for some cases, some like Dirac case maybe give you advantage, and another case maybe that matrix representation give you advantage. Yeah, both way you can do that. Like if you think of that harmonic oscillator problem, so we solve it by ladder operator method. So here we don't use any matrix from there. So by use Dirac notation, abstract notation, we do all the thing. And you can also perform by choosing some basis. Let's say you are choosing some, you can do some basis like position, like the differential equation we solve, that is actually done in the position basis. So we actually doing the same kind of operation, like taking the basis into account. Yeah. Hope it is clear, right?
I guess it's clear to the anyway this will be there on YouTube, so it's okay. So yeah, thank you so much, Manada, for this amazing speech. Thank you for taking out your time, and we really feel proud as Narendrapur alumni to see you sharing such interesting talks. So it's a privilege for us.
I also feel proud to be present here.
Yeah, thank you so much. I mean, it's been a long time since I saw you. So yeah.
Oh.
Okay, so
can
this
you
is
turn on your camera?
Okay, my background is not in a proper condition, you know. So yeah, like I was there in the like GV study halls with you. I even like clarified some doubts from you. So yeah.
Yeah, I remember those days. Yeah.
Yeah, so those were really golden days of our lives. So yes.
Absolutely,
yeah. Thank you so much, Manada. And so bye. Yeah, bye. So by this we can take a break right now. We'll come back on 2:30 with some more interesting speakers. So see you on 2:30. And I'll just say one thing. If you guys have any questions, okay, you can always write it in the Teams chat. And also for those watching on YouTube, you have the live chat option open. So you can write those questions down there, and we'll be conveying it to you. We'll be conveying it to the speaker at the end of their respective speeches. So yeah, the conference resumes when it's 2:30. Okay, 2:30 p.m. So well, see you. Bye for now.
দেখ দাঁড়া ইউটিউবটা চেক কর একবার। চলছে? ও আচ্ছা দাঁড়া এসেছে ব্যাংক স্ক্রিন না, তোর টিমসের স্ক্রিনটা দেখাচ্ছে তো? দাঁড়া 1 মিনিট দেখছি।
হ্যাঁ এই তোর কথা শোনা যাচ্ছে, ভাই।
And eventually it cools down, and then the stars, galaxies form in the late universe. And what we are seeing right now is up to 13.1 billion years evolution of universe. So the hot Big Bang model is largely described by the Friedman-Lemaitre-Robertson-Walker metric, which is described by this metric: ds squared equals to minus dt squared plus a squared dx squared, where a is the scale factor and t is the cosmic time and eta is the conformal time. So our universe is, at least on the large scale, is homogeneous and isotropic in nature. So this is the evolution of universe when the Big Bang happened at the very early stage of the universe, and then we think about the inflation happened, then the particles form and the recombination happened, and then the dark ages, and then the galaxies form and evolution happened. So now the cosmic microwave background. Cosmic microwave background is the earlier snapshot of our universe. So it is the extremely important probe to learn the physics of the early universe. So at the redshift of 1100, photons started to stream freely through the universe. It decoupled from the baryons and electrons, and it started to stream freely through the universe. And it has been, after the various amount of observation from by W. Planck and other things. So it has been seen that the CMB gives a isotropic thermal spectrum that is around 2.72 Kelvin, and it also has a small anisotropies of the order of 10 to the minus 5. This image has been taken from Planck's 2018 latest observation. So now, so there are, as I said earlier, though there are some drawbacks in the hot Big Bang model. So I will discuss about the horizon problem only. So the horizon distance, what is also known as a particle horizon. So this is, you can think about the horizon distance as well. The observable universe, people can the observable universe at time. Okay, so in the in the horizon distance, 2 points can causally connected. They can share information. They can share the information. So and the horizon distance can be calculated by this expression. And if we just calculate the backward light cone to the time of recombination and draw the forward light cone from the Big Bang to the time of recombination, we see that at the time of Big Bang, the points are causally disconnected. So we can also calculate this thing by this. So there is a 70 lb. The forward light cone and backward light cone has a difference of 70. So this is known as a horizon problem. What inflation does that they connect this causally disconnected region, and so inflation solves this problem. Inflation is an epoch of accelerated expansion in a very early stage of universe. So if we think that inflation doesn't happen, so matter and radiation dominated era. So this is the Hubble radius, and these are the physical wavelengths of the modes. You can see that the early stage they are outside the Hubble radius, so they are causally disconnected. But the CMB shows it has a extremely isotropic index. So so that's why we need some solution. So inflation gives that. So uh, at the inflation, so modes come well inside the Hubble radius at the suburban scale. So, so another thing we can calculate that we need at least 60 poles of inflation to solve this horizon problem. So now, as I said earlier, the Friedmann-Lemaitre-Robertson-Walker metric describes our early universe. So if we solve the Einstein equation for this FLRW metric, we can get this two equation. This two equation is known as a Friedmann equation, where H is the Hubble parameter, and rho is the energy density, and P is the pressure density. And from the second Friedmann equation, we can get that to get the to get the accelerated expansion, we need rho plus Vp has to be less than 0. To satisfy this condition, ordinary matter or radiation cannot satisfy this condition. So we need a scalar field with a potential driven by potential d phi. So the action of the scalar field is written by this. So, so by varying this action, we can get to the equation of motion for the inflaton field. The scalar field is also known as the inflaton field. So this is the equation of motion for the inflaton field. Now, as I said earlier, we need roughly around 60 poles of inflation. So get this sufficient amount of inflation, we need a slow roll inflation model. That is, the kinetic term is dominated by the potential term. So to quantify this slow roll inflation model, we need some slow roll parameters. To quantify, we define some slow roll parameters. The first slow roll parameter is epsilon1 equals minus h dot by h square, and we can also calculate the higher order slow roll parameters. They all are very important. We will discuss in the later part. So and another thing, oh, okay, it's okay. So capital N is e-pole, number of e-poles. As I said earlier, we need 60 e-poles, roughly 60 e-poles. For different models, we get some other values. So we need roughly 60 e-poles of inflation. So, and to satisfy the condition for inflation, this all the slow roll parameters has to be less than 1. This is known as a slow roll condition. So now the perturbation. As I said, there is a small anisotropy at the order of 10 to the power minus 5. Inflation also describes this anisotropy also. So this is the Einstein equation. What we do to generate the perturbation is we perturb the metric, and to the metric perturbation can be decomposed in the scalar perturbation, vector perturbation, and tensor perturbation. We only discuss about the first order linear perturbation theory. And in the first order linear perturbation theory, scalar perturbation, vector perturbation, and tensor perturbation evolve independently. They do not couple. Okay. So I think the vector without a vector, in the absence of vector system, the vector perturbation vanishes. Okay. So vector perturbation vanishes. That's why we'll discuss only about the scalar perturbation and tensor perturbation. So now we will deal with the longitudinal gauge. So there are other gauge also, synchronous gauge and co-moving gauge and other gauges also. I will discuss only in the longitudinal gauge, and so and perturb the metric. And after perturbing the metric, this is the metric form. And similarly, we perturb the stress energy tensor also. So we can after calculating this term, we can get this Einstein equation, perturbed Einstein equations. So now we we define a quantity that is curvature perturbation, and with using this first and third equation, we will they can construct is generated by the quantum fluctuation. So the primary perturbations we need to quantify this R the curvature perturbation. We have to quantify this curvature perturbation. So we can write the curvature perturbations in a Fourier modes, where A and AK are the annihilation and creation operators, and by the calculation we can write the equation of motion in terms of Fourier modes. Okay. So now another thing is to simplify this equation, we will define a Mukhanov-Sasaki variable. This is a scalar Mukhanov-Sasaki variable. So Vk equals to Z Rk, and we can write the equation of motion in terms of Mukhanov-Sasaki variable. Now you can see that in the sub-Hubble scale, this term will dominate. So it is almost it is like a simple harmonic motion. So Vk double dash equals to k square Vk. So and super Hubble scale, this term will dominate. So in the de Sitter limit, we can get the solution very easily. But in the slow roll case, we will get a solution in a Henkel function, and we will discuss it later. So now I will discuss about the first order tensor perturbation. So the tensor perturbation, Friedman line element tensor perturbation is like this way. And similarly, we calculate the perturbed Einstein tensor and then quantify the Hij tensor modes and get the Mukhanov-Sasaki variable. This is the tensor Mukhanov-Sasaki variable, UK equals to AHK, and write the equation of motion in terms of Mukhanov-Sasaki variable. Now I will calculate about the power spectrum. What is power spectrum? Power spectrum is just a Fourier transform of a 2-point correlation function. Okay, so this is the power spectrum, and we can from the R we can calculate this power spectrum. This is scalar power spectrum, and this is the tensor power spectrum. This two arises for the two polarization set for the tensor modes. Now, from the PS and PP, we can calculate the scalar and tensor spectral indices, NS and NT. They are the observational things which we can compare with the claimed data. And this is the scalar and tensor to scalar ratio, that is PP by PS. Now, we will solve, as I said, for the slow roll inflation, we will try to solve the Mukhanov-Sasaki equation of motion. So the initial condition for the slow roll is in the sub-Hubble. We think that at the sub-Hubble region, the modes are in a Minkowski spacetime. The modes are in the Minkowski spacetime. So like this is a Barnes-Davis initial condition. So we think that the modes at the sub-Hubble region, it's in this way. So in the by slow roll inflation, we can write the Z in this style, AMPL and square root of 2 epsilon 1. And for this Z, we can solve the equation of motion, and it will be in a Henkel function. And if we expand that in Henkel function, and after the rigorous calculation, we can get the NS and NP. This is the scalar spectral index and tensor spectral index. So as I said earlier, this slow roll parameters has to be really small during the inflation. So for NS, it has to be for the slow roll inflation, NS has to be 1 and NT equals to 0. So it has to be a nearly scale invariant NS. We should have get the nearly scale invariant NS. So now I will show the scalar power spectrum for different kind of models. So there are lots of models, quadratic potential, Saravinsky model, and Saravinsky. I will discuss about only these two, and there are other models also. So the most of the models give a nearly scale invariant NS, but as you see here, there in the low multiples there are some error bars. So that's why we need different kind of models to get a better fit in these lower multiples also. And so yeah, so this is a quadratic Sarabinsky and loop Sarabinsky model. Okay, so this is a quadratic potential. So as I said, the potential will slowly rolls down, and at the end of the inflation, this is the end of the inflation, and you can see after 68 for the quadratic potential, inflation stops. Here also inflation, as soon as epsilon 1 goes to 1, inflation stops, and after the inflation stops, this is a reheating zone. The inflation field oscillates here, and as I said, this is the power spectrum what we got from the quadratic potential. Now this is the Sarabinsky one model. Similarly, quadratic potential it also gives same power spectrum, similar power spectrum. And at last, this is the Sarabinsky model. It shows some features in the power spectrum. These features are important because it gives a better fit to the Planck data. So so this is the Sarabinsky model, and you can see this is a deviation from slow roll. There is a one inflection point. So this is a deviation from slow roll. These are my summary. Inflation can provide an answer to the problems with the hot Big Bang model. We need roughly 60 folds of inflation to solve the horizon problem, and it can be achieved by considering a scalar field. Inflation also provides a mechanism for the generation of perturbations. For slow roll inflation, it merely gives a scale invariant power spectrum, which is consistent with the observational data. Now, the future scope. So far, we have detected only the scalar power spectrum. So the tensor power spectrum is still undetected. So, but the R, what we discussed earlier, the tensor to scalar ratio is less than 0.036. So future observation like Lightbird and CMB can enlighten this part shortly. And also, during the last few years, WMAP and Planck data found that there exists some non-Gaussianities in the CMB CMB data. So we have been able to constrain this non-Gaussianity parameters. So calculating higher order correlation can lead to this non-Gaussianities. And also, it has been seen that for various models, there has been the enhancement of power spectra, which can lead to the formation of primordial black holes and secondary gravitational waves. So the primordial black holes are one of the possible candidates of dark matter. So some references. Thank you.
Thank you very much, Olipriyada. We'll move on to the next. But before that, I don't think we have any questions. So thank you so much, Olipriyada. It's very nice seeing you after a long time.
Yes. Thank you for.
Yeah. So okay. So we'll move on to the next in some time. Ivan, are you ready for your thing? Okay.
Yeah.
Okay, so our next speaker is Mr. Ivan Dotto from Niger. He's presently doing his PhD in Niger. He's again another alumnus from RKM Narendrapur. Welcome, Ivanda here. He studies in the conducts research in the field of condensed matter physics, and the topic of the talk is quite interesting. It's topological Hall phenomena for weight babies. Okay, so I've seen books like that quantum mechanics for babies and all. So I guess the topic will be like that. Thank you, Ivanda, for coming to the thing. You're welcome. The stage is yours.
Slide or this is changing?
Yeah, testing. Yeah.
Yeah. Okay, so good afternoon, everyone. And today I will talk about topological Hall phenomena. And for babies in the sense that we all are babies in the realm of science and also in the field of research. And here, basically, I will talk about the birth of topological insulator, and that is the Hall effect, specifically quantum Hall effect. And to understand it, we will discuss what is topological about an insulator. So the question to answer this will be from the very scratch. First of all, what is topology? And the most basic question is, what is an insulator? So what I have planned, I will start from the very basic, and the first part is, what is an insulator? So the insulator is a material which don't conduct electric current freely. Why? Because the atoms of the insulator have tightly bound electrons, and the electrons can't readily move. So the question is, why they can't move? So to understand this, let's start from the atom, which is familiar to you from the school days, and you know that for the different electronic orbitals, they possess discrete energy levels. Now, if we stack different atoms to form lattice or kind of unit cell, the energy levels of the different atoms talk to each other. Any questions or anything? Hello?
No, Ivanda, I think there was some glitch from someone.
Okay. So now if we stack different atoms to form kind of unit cell, what we see that the energy level of different atoms talk to each other and they get modified. And the density of energy levels gradually increases. So think of any real material system where there are 10 to the power 23 number of atoms. And so the energy levels are so close and they are kind of continuous. And as a result of this, they form a continuous band. And this is the band theory of solids. Okay. So for a material, there is a maximum energy level, that is called the Fermi level, and up to which the electrons can stay in its ground state, and up the area is called the. So consider a 2D free electron. What will happen if we give a magnetic field? Magnetic field B shifts the momentum P as P plus EA, where this A is the vector potential W. And if you solve the Schrodinger equation, the energy becomes discrete in nature, you all know, and they are solutions of the harmonic oscillators, and they form discrete random levels which are highly degenerate in nature. Not only this, the electrons become localized in space. And if you think about it, semi-classically, due to the Lorentz force, the electrons move in circular motion, yet they can't move here and there. Okay, so they are localized. Now the question is, the 2D electron system with field random levels is an insulator or not? Suppose you have a crane 2D system, okay, and I am attaching a voltage difference in its longitudinal direction. And so the current as well as the electron flows and there will be a current, but when a magnetic field B is introduced, you can see that the electrons gets accumulated in one direction. When a magnetic field, you can see. And as a result of this, the positive charge is accumulated at the other side, okay? And the voltage difference is created in the transverse direction. You all, I think you are familiar with this. This is called the Hall voltage. And this is the classical picture. And also you see, if you plot the resistivity in transverse direction, this resistivity increases linearly with B. This is the transverse resistivity. Okay. So, but the fact is, this is not the full story of the Hall effect, because you have not noticed about the range of B. So what I am doing, I am increasing the B more and more and more. What happens after a certain time, the resistivity loses its linear nature, and what happens, this increases step by step, this kind of the different phase property of the system. And not only this, the longitudinal resistivity only gives a finite value when the transverse resistivity changes. One of the most interesting things you can notice, you all know that resistivity equals to 1 by conductivity, and the longitudinal resistivity is 0, and longitudinal conductivity is also 0. That means 0 equals to 1 by 0, and that can't happen. And this is a very surprising behavior of nature. And one of the why this is more interesting, because when this was performed in lab, the quantization gave nearly exact result, and the error things was nearly 1 part per billion. This is one of the exact results in physics, and this is called the quantum Hall effect. Due to this quantum Hall effect, Klaus von Klirzing got his Nobel Prize in 1985. Now the question is, how does these kind of insulating phases of matter differ from band insulator, or they are similar to the band insulator? We don't know. We need to investigate it. To understand this is band insulator or not, we first need to understand the classification of states of matter by the Landau symmetry breaking theory. What they tell that suppose you are within a liquid, that means the environment around you is symmetric every time. This is equal. But when you are on a crystal, the translational symmetry is broken. You can see the ant sees the same environment, but this ant does not see the same environment with this. That though there is a discrete translational symmetry, but the continuous translational symmetry is broken. That means when I am going from liquid to crystal, the translational symmetry is broken. So the symmetry breaking is associated with the change of phase. Not only this, for the magnet, you can see there is a broken rotational symmetry by the direction of the magnetization, and for a superconductor, there is a broken gauge symmetry. But what happens for our quantum Hall systems? Because for our quantum Hall systems, the system is fixed. The system is in its position. What we are doing, we are just only increasing the magnetic field, nothing more than that. So there is no obvious symmetry breaking, as there is no. So what is separating the quantum Hall phases? So this is one phase, this is one phase, this is one phase, and this how they are distinguished. The answer comes from topology. You already heard a lot of talks from topological quantum computations previously. The same thing is here. So what is topology? Topology means a continuous deformation of a geometrical object. That means you can't close any hole, you cannot open up any hole, you can't tear or glue or passing through itself. Okay. How? In the same way that the pizza can be easily deformed to a lemon or orange, but the pizza can't be deformed to a donut. Why? Because they are not topologically same, and you need to open up a hole in between these. So they are not topologically equivalent. In the same way, donut is equivalent to a coin, but donut is not topologically equivalent to a pizza or a scissors. So there is some kind of topological invariant which is same for the first column, which is same for the second column, but they're not same for the row-wise pattern. What is this? This is a genus. You can think about at the number of holes. So for the first case, the number of holes is 0. For the second case, number of holes is 1. For the third case, this is 2, and like in this way. This is called topological invariant. Now, how to calculate this topological invariant? Mathematically. So one of the important theorem in this contribution is the Gauss-Bonnet theorem. What Gauss-Bonnet theorem showed? They showed that if you, for any geometric object, if you just plot the Gaussian curvature and surface integrate it around the closed surface and equate it with the formula 2 into 1 minus g, where g is the genus of the surface, the g gives you the value. What is the Gaussian curvature? Gaussian curvature is nothing but just the inverse of the radius of curvature of the system. So if you calculate it for a sphere, for the sphere the Gaussian curvature is 1 by r square, and if you equate it with this, you can get g equals to 0. That means no hole is there. In the same way for the torus, if you calculate the Gaussian curvature and integrate it, then you get g equals to 1. The question is how to see about the topological invariant in the context of physics. To understand this in the context of physics, we first think about a Hamiltonian, that is H, and this Hamiltonian is dependent on some kind of variable, that is lambda. What I am doing, I am changing the variable lambda very slowly in adiabatic process, and the change is in such a way that the initial position will be equal to the final position. So for the different point of different lambda, you get different wave functions solving the Hamiltonians. But when you are returning back, the final wave function should be equal to a initial wave function. But there is some more considerations, because you all know that the phase ambiguity is allowed in quantum mechanics, and the un can be related with u1 by some kind of phases e to the power minus i5. We don't care about these phases in the wave function too much, because in physics, when we calculate the real observables, there is a bra and there is a ket, and as a result of this, e to the power i5 into e to the power minus i5 cancel out, and this does not give no contribution. This is kind of good for nothing for our interest. But is this really true? Pancharatnam and Berry thought that this is not true, and they told that these phases have some contribution in the physics of the system. Suppose I am on a sphere, I am starting from the North Pole and just going through the red line, and again I am returning back. The initial wave function was ux0, and after a certain time t, when again I am returning back via the adiabatic process, the wave function u is uxt. And you all know that they will be connected by, as there is a change in time, that will be connected by unitary time evolution operator e to the power minus iht. Okay, but they showed that no, there is an extra phase, that is e to the power I gamma nt, and this phase is called the Berry phase, where the gamma in is the line integral of the ak, where ak is the Berry connection defined as the gradient of the wave function via a ket and bra with the imaginary part. Now, how to understand this in a classical thing, though there is no classical analog of this, but to understand this classically, suppose when I am traversing the path, I am keeping a javelin in my hand, and at each and every time I am keeping the direction of the javelin fixed with respect to my body, and when I am returning back again, you see the javelin is not in the same direction, but there is a kind of change in angle in the javelin, and that's why a phase is introduced. This is kind of things you can think about in classical analog of the Berry phase. Now, Pancharatnam is the first Indian scientist who pointed out that in 1956 in the context of optics, and later Mitchell Berry modified it in 1984, and after that these concept of phases became popular in the physics community. So how to incorporate it? Why I have told this story? You all know what's the quantized Hall conductance we have showed in 2D periodic potential. So when I were talking about a 2D system, you all know that now the energy distribution has a kx and a ky, and Brillouin is now a square seat. And already you have learned from Hiranmoy's talk that for this Brillouin, in the kx direction, minus pi by a and plus pi by a, the green things are identical. In the same way, the upper in the ky direction, pi by a and minus pi by a is identical. That means we can wrap up, we can glue this side with this side and this side with this side, and as a result of this, the square sheet is now transformed to a torus. Thouses showed in 1982 that if you do this, the full energy band of the 2D system can be characterized by a topological invariant, and that is called the TKNN invariant. And they showed when you can deform the Brillouin to a torus, I can easily write the topological invariant AKDK, which I have mentioned before, as Fk into D2K via the Stokes theorem, and where the Fk is nothing but the curl of Ak. And why this quantity is important? Because when we are taking the curl, what happens? The gauge does not matter. It does not matter is it Coulomb gauge, symmetric gauge, Landau gauge, anything, because in each and every gauges, the value of the Fk is same, and the full thing gives a topological invariant of the system. So this invariant is the connected with the Berry phase or the phase change of the electrons in the bulk of the 2D system. Now, talk about the age state. You have already seen that the after the Fermi level, if the Fermi level is in between the energy levels of 2, then there is insulating, because the Fermi level, the bands don't crosses the Fermi energy. But as the 2D system is finite, that means the confining potential at the edges pushes up the Landau levels at the edges of the sample, and as a result of this, the Fermi level crosses the Landau level. Fermi energy crosses the Landau levels at the edges, and that means there is a current in edge, though there is no current in the bulk. If you think about it in semi-classical language, you can see that in the bulk the electron motion is circular, but in the edges the electronic motion is half circular, and as a result of this, an electron can start from here, and by this skipping orbits, they can move along through the full edges. And as a result of this, there is a 1D edge current. This is chiral in nature because the direction is always same, and if you put some disorder within this, the electrons will not backscatter and will remain fixed in its direction just to cross the disorder. That means for the system, if you perturb the system slightly, the property of the material is not changed, and that's why it is classified in topological sense. That is robustness. This property is called the robustness. Now I am going to the A-state picture. 1989, Landau showed that a number of Fermi levels crossed in here that is associated with the conductance of the wire, and this conductance is mu, that is the number of chiral edge modes. So what we have seen that the system is gapped in bulk, but the gapless states exists in the interface, and you can see here that the surface energy band is gapless and it is going from valence band to conduction band here in the graph. So to classify the current in the conductance here, this is Landau showed that this is equals to the number of the chiral modes, the number of energy bands crossing the Fermi energy, and this is also equal to the TKNN invariant. So what we see that the bulk invariant is equal to the topological invariant or chiral edge modes, and this is called the bulk edge correspondence. That means if you hit some light or anything or perturb the bulk, the effect of the perturbation will be shown by the edges of the system. It will not be seen in the bulk. Now, a different scenario. What we have talked till now, everything is in presence of some kind of magnetic field. Now, I am asking, is there any other scenario where nature herself takes care of the responsibility of the applied magnetic field? Why people are interested in this? Because creating huge magnetic field of quantum Hall is quite difficult. And most of the labs in world, it is always expensive also in industrially to create high magnetic fields. Okay, so who take care about this creating a magnetic field via nature is spin orbit coupling. And here the role of the magnetic field B is played by it. You all know that the electrons move around a proton. Now, if you think about the situation with respect to the electron's point of view, what happens? Electron sees that it is in rest frame and proton is moving around it, and as a result of this, the proton is creating a magnetic field B around it, and this magnetic field is interacting with the magnetic moment of the electron. And as a result of this, there is an interaction energy, spin orbit interaction energy is required, that is L dot S. You know that this S can be positive or negative depending on the sign. The direction of the B changes when spin changes. What is meant by that? Suppose I have a 2D system. In 2D system, there's up spin, and this up spin, due to the spin orbit coupling, feels an effective magnetic field in upward direction, and this moves around the edges in anti-clockwise manner. In the same way, the down spin will feel an effective magnetic field in downward direction, and it will move in clockwise manner. And when we are punching these two together, what happens for a 2D system? The spin up is going one direction, spin down is going another direction. This is called the spin Hall effect. So you have already seen that for the integer quantum Hall state, there is one chiral edge modes, but for the spin Hall state, where the spin up is going one direction, spin down is going another direction, there is a helical edge modes. And this is gapless in nature, that means there is a current is carrying via the edges. So, and these things are called the helical. And one of the interesting things which I have already mentioned, that the topologically protected and they are immune to the impurities or geometric perturbation. And the things I have not mentioned and kept for you to study, just want to mention here that this system is symmetric in the time reversal symmetry. And the helical states form the Kramer's doublet, and even if the trajectory is changes for the geometric perturbations or the impurities, there is no change in the motion of the electron, they don't backscatter. And if the trajectory itself changes near obstacles, they still remain time reversal partner of each other. This scenario is not seen in the conventional 1D superconductor, because in conventional 1D conductor, if any disorder is present, the electrons become localized, and this phenomena is called the Anderson localization. But this does not happen in topological insulator. That's why there is dissipation is very less here. So this is the end of the story. Now just I want to mention very shortly what we people do in analytically. We calculate some kind of, we construct some kind of momentum space Hamiltonian HK, and the Hamiltonian is kind of the form of decay dot sigma. You can think of that the decay contains the orbital part and sigma is the spin part. That means the Hamiltonian is spin orbit coupling Hamiltonian, and we construct decay in such a way that it depends on the symmetry of the system. And not only this, but this is also realizable in real system. You can't put anything in the expression of decay. It should be some logic there. And then what we do, we check the fate of the edge state or the surface state. This is gapless or not gapless. So for some situation, for some situation, the edges are gapless. In some situation, the surface is not gapless, but the hinges are gapless. And there are also some situations where only the corners are gapless. They can conduct current. And this is called the higher order topological insulator. and then we find the topological invariant, and lastly we see the effect of the invariant on the physical observables the system possesses. So why I have shouted this much for the topological insulator? Because the industrial thing is we want to do more with our phone, because the demand of computation is growing 70% per annum annually, and we need to minimize the loss due to the Joule heating. And not only this, we have already reached to a point where silicon transistors can do matter. This is the report from the Economist journal. You see that the speed is already converging, but the demand is increasing gradually, and we need to cope up with this gap. So our solution, we need a new switch that is vastly lower energy per computation. And how we can do that? Via superconductor or new material. How via superconductor? You all know that superconductor needs low temperature, because high temperature superconductor is yet to be explored, and so this is not commercially very efficient. So we need to search for the new material. And one of the interesting things is quantum computation. Already we have learned about this from morning. There are also some kind of graphene-based transistors which is efficient, some kind of DNA data storage, optical computing where the photons are used as a memory, and also the neuromorphic technology where science study. The take-home message is that topological insulator is insulator in bulk but conducts current through the edges. They are robust under small perturbations.
And here you see the redshift space distortion you find for large value of S perpendicular, like towards the bottom, when the S perpendicular is around 20 to 25, you see that overdense region get squashed, like what we find in this Kaiser effect. So this gets squashed, and and as you go to more to the S perpendicular, to the smaller value of S perpendicular, that overdense region gets elongated along your line of sight, right, towards the center. This overdense region gets elongated in redshift space. That is what is called finger of God effect. So yes, so these are the two effects. So what we see in small scale and large scale simultaneously, and the correlation function is one estimator to understand the redshift space distortion. Okay, so this is my end of my talk. Are there any questions? Any silly questions you may ask? Hello.
Yes.
Yes.
Actually, I mean, I don't think there are any questions, like not in the chat, nor in the YouTube section. So I guess if they have any questions, they can mail it to you. So
okay.
Is it okay? Okay.
Yeah, it's fine for me.
Thank you. Thank you for the talk. I guess it will inspire a lot of people who are looking to work into cosmology in the future. So thank you for making some time for us. Thanks a lot. So we'll move on to our next speaker. Our next speaker is Mr. Shubhayan Mukherjee. He is presently working at the National Chengku University. I don't know whether I am pronouncing it right. So it's a university in Taiwan. He works in the realm of condensed matter physics, and he'll speak about the materials in the battlefield of instruments. The topic surely sounds interesting. So Mr. Shubhayan, you can take the stage.
So am I
Thank
audible
you.
to you?
Yeah, sure, you're audible.
I am sharing my screen. So this is visible, right?
Yes, it's visible. Thank you.
Okay, so hello everyone. And at first, I would like to say thank you for inviting me. I am very young in this field, and This is my third year going on as a PhD student. At first, I would like to say something that few years ago, actually, my position just as the audience of this kind of webinar, and the important part that actually I realized, that is the bore. I mean, I feel the boring. Sometimes the topic is going on, and the lot of lectures are going far away from my head. So whenever I am giving the presentation nowadays, except my exact research presentation, so I always try to make it easy, and always try to engage the audience, so that at least they will not sleep during my presentation. So this is the main intention. And also for today's presentation, this presentation is mainly focusing on the undergrad and master students, uh, because the students, those who are doing PhD, they already have a fixed direction that on which they are working, or what's their intention. So they already know about it. But my target audience is only the undergrad and the masters. I am working on the experimental condensed matter physics in the material science department, and in Cheng Kung University, National Cheng Kung University, in Taiwan. So here is my details. So I also provided my email ID. So if anyone wish to contact with me, you can contact. I am very active in Facebook and LinkedIn, anywhere. So the title has already mentioned, that is do and observe the materials in the battlefield of the instruments. So I am not entering in my exact research. So very shortly I will mention my research, but I will try to introduce that what exactly the experiments I am doing, and how you can relate it with your present theoretical study, whatever you are writing in the exams or something. So this is the main target of this presentation. Okay, so at first I would like to introduce myself, that you guys maybe don't know who I am. So I did my undergrad from Barakpur Rashtraguru Surendranath College, Barakpur, and after that I did my masters from West Bengal State University in Barashat. And during my masters, actually in my third semester of my masters, I did my masters project from Taiwan, that is from other university, Cheng Kung University. So I was there for 6 months during my masters, and after that I finished my master and joined my PhD in National Cheng Kung University in 2020 September, during the COVID. Okay, so the first thing I would like to say, that I am very simple student. So just my passion to do research push me wherever I am today. So I request all the students, just do whatever you want to do, and you will get the result. So this is my self introduction. Okay, now I just set outline for today's presentation. So this is very common thing which I need to give, that is the background of the experimental condensed matter physics, then what you know to what I know. That means my target audience, I already mentioned, that the undergrad and master students. So I am asking you that how much you know, and now I will explain that how much I know. And after that, what should I discuss? Condensed matter physics? So maybe not. And after that, the solid state physics from your viewpoint, that what do you think about solid state physics? And now solid state physics from my viewpoint, and then the hi hello to the laboratory work, that what the laboratory work is going on. And at last I very little part of my research I would like to share. Okay, so the background of experimental condensed matter physics. Actually the physics is very fast. This is, I am no one to say it. This is very known to everyone. And now the term condensed matter physics, that is also a very vast topic. So if I consider the entire blocks, the right side image, this is the condensed matter physics. So now I am working on a single block. So this is the single block of condensed matter physics on which I am working on. So this is the so you can understand that what is what is the basic structure of condensed matter physics and how much things I know exactly on condensed matter physics. So after that, that this is very common thing not only for condensed matter physics but also for the physics student, that which one is important, that is experiment or theory. So this is a very common controversial question, that experimental physics or theoretical physics. So I am not putting my leg into this controversy. So I am an experimentalist. I am working on experiment. So I just want to say that if there is no theory, then we are nothing. And same as that if there is no experiment, you can't establish your theory. Okay, so that's why as a student I will suggest, don't take entry into this controversy, just love your physics and do your physics. So I am working on experiment. So there is, whenever you are talking about the condensed matter physics or the material science, because if you are going outside of India, where I am not talking anything related to the present situation of industry in India. So just in general, if you are going outside of India, there are a lot of industry. Mainly after COVID situation, Taiwan is one of the hub of industry. So in Taiwan, the very common thing is that you cannot separate condensed matter physics and material science. So material science, here mostly the people are working on material science. So in material science, the condensed matter physics is automatically involved. So now you are talking about condensed matter physics or material science. The first question that is raising, that how do electrons organize themselves and flow on the nanoscale? So the question, so another question that will come in your mind, that is it necessary to be the nanoscale? Is it not possible for the micro scale or normal scale that is more than the micro scale? Yeah, everything is okay. So the nanoscale actually we are considering just because to say, wow, it is nanoscale, so it is so interesting. So no need to think like that. I am measuring my sample, maybe but the sample dimension is around 1 centimeter or 2 centimeter. I am also measuring it by using the slide calipers. And when my sample size is around 10 micron or less than 10 micron, then I am going to measure this sample by using some instruments. So the main concern is that how do electrons organize themselves and flow on the nanoscale? So whenever I am working on the condensed matter physics or material science, the main part is the fabrication. So I am working on experiment. So I have to create my sample. So that means we need to do the we need to fabricate the sample. Now it is the material phase stability, or I can say the material phase. So there are actually the very common and known phase, that is the physical phase, that is solid, liquid, gaseous, and blah blah blah. There are fourth state, fifth state. But I am working on the crystallographic phase. And then I am going to the quantum phase transition. So putting the word quantum with the phase transition, it is more like a hot cake. Like, wow, this is quantum. So that means it is physics. So I am not talking like that. So quantum phase transition means, so when you cannot predict or when you cannot visualize the phase, when you need to consider the wave functions, when you need to consider the probabilistic approach, so then that phase or that phase transition we can consider the quantum phase transition. And many other topics are there, that is high temperature superconductivity, metal insulator transition. My friend actually in my department, he is working on the superconductivity. So whatever. And what are the instruments we need to use to do these things? That is the XRD. There are actually 2 or 3 instruments that is very common for all the experimental material scientists. That is XRD, that is X-ray diffraction, the TEM, that is transmission electron microscopy, ACM, scanning electron microscopy, OM, optical microscopy. So these 4 instruments are very common, and I'm quite sure that all the master students who already finished the bachelor's, they already know about the term, that what is XRD. They already knew it. This is not unknown. Maybe they did not use it, but they know the term. Now, if you are considering some mechanical aspects, there comes the EPMA, now DSC. So these things are also there. So I am also working on the nano indentation. So nano indentation, this is not so common. Recently, I was talking with one of my collaborator in VEC in Kolkata. So he is working on micro indenter. So the main purpose of this instrument is like, if you use this instrument, you can do the electromechanical treatment of the sample. So now I am doing in the nano range. So that is the name of the instrument is nano intender, and the professor in Kolkata working on micro range. So that is the micro indenter. And another interesting thing, actually, I am involved with my research, that is synchrotron radiation. This is very rare in the world. In Asia, Japan has a very good synchrotron, and after Japan, Taiwan is the second best as the synchrotron center, and Stanford is the best one for the synchrotron. In India, actually, we have also synchrotron, I think in Odisha or somewhere, but it is not so high range. The beamline number is, I think, 1 or 2. Okay. So now the point is what you know to what I know. So I am pointing out a very common things like solid state physics. So solid state physics, actually, when I was in college, so in the 3rd year, the solid state physics was there. And so the point is that one undergrad student, I am considering he is in 3rd year. He also know about solid state physics, and I also know about solid state physics. Now the crystallography. So if you are starting the starting to read the solid state physics, then the first part is crystallography. So obviously you know, and I also know. Now the point is, do you saw it? Have you ever seen it? So the answer will come yes, because he can say, yeah, I saw some pictures in my book or in the video, YouTube videos. So okay, but for me, yes, I saw the crystallographic structure. So if you say, wow, so you just see it in the in laboratory, I said no, it is not in the laboratory. I can say a cubic structure or something, but after whenever I will go to finish my presentation, you can understand that how I can saw it. So this is some simulating pictures, but yes, this is the real image. I mean, I can imagine the real image. Now the Bragg's law. Yeah, if you are studying the solid state physics, the Bragg's law is very common thing. So we both will say yes. Applied yet? So he said yes, I applied it. When the questions came in my exam, I used the Bragg's law and I solved the question and I get the marks. So okay, so he also applied, and I am also applying in my experiment. Now the XRD. So if you are considering the Bragg's law, the X-ray diffraction is also there. So both say yes. Did it? So he said no. So here is the first term that maybe some student will say no, and I am doing XRD. ACM or TM. So maybe they will say yes. If he is very much interested in solid state physics, so he said yes, that yeah, I know what is scanning electron microscopy or transmission. I am doing yes. And did it? So the same thing is that maybe he will say no, but I am doing it. I am doing it. Now the synchrotron. So I am actually, this is a very interesting story in my life, that when the first time I got opportunity to visit synchrotron center, that is in 2021 March. after joining PhD. That was my second semester. So I was so much excited because I first studied the synchrotron, cyclotron, this kind of particle accelerator in the particle physics in the third year. So I was said, wow, so this is the time when I am going to experience that kind of things, which was the dream to be there, because we only know about CERN, CERN, when the God particle we studied in when I was in school or college. So from that time, to observe the particle accelerator was really wow moment. So so you guys can say yes, in book we already studied the cyclotron, synchrotron, everything. But now I can say that okay, I am staying there for maybe 2 to 3 days for a month. So I am going there every month for my research. So this is the things that, so you know and I know. So you can observe that we don't have a much of difference. There are only 2 or 3 things. I am just ahead of you just because of my age. I already passed B.Sc and M.Sc, and you are now studying. So whenever you will finish it, you will join Ph.D, you guys will experience it. Now the thing is, what I will discuss today. I will discuss condensed matter physics. I can say no. I can say no. Don't be afraid or don't be so excited. You guys have so much time to understand condensed matter physics. Today I am not putting you a pressure to understand condensed matter physics. I will give an essence of condensed matter physics or experimental approach of condensed matter physics, what I am working on. So here you can see a quote, that is, the condensed matter physics is a study of the substances in their solid state. This introduces the investigation of both crystalline solid in which the atoms are positioned on a repeating 3-dimensional lattice such as diamond, and amorphous materials in which atomic position is more irregular like in glass. So after listening this statement, you guys can understand, oh, this is not so much difficult, because we know what is crystalline, what is amorphous. We already studied it in the third year of solid state physics. I said yes. So if you combine these terms, that is solid state physics, crystallography, n-dimensional, why I put n-dimensional? Because now if you are interested on astrophysics or cosmology, these things, then the dimension is the limitless. So, but for me, it is limited, but it is 1, 2, 3 dimension for me. So that is why I say that is n-dimensional. Now the phase, now the space group, now the lattice, now the probabilistic distribution. So if you just put all these words in a mixer grinder and mixing it, then the outcome will be the condensed matter physics. For me, whatever I am working on. So this is the condensed matter physics, what I am working on, and maybe in the few slides I will discuss maybe on it. Now the solid state physics from your viewpoint, what you know. So you guys will know you already know the lattice, what is lattice, what is unit cell, what is crystal structure, what is Bragg's law. So these all the things you guys know. So I just presented some pictures. So Bragg's law, that is very interesting, that is D is equal to n lambda by 2 sine theta, or n lambda is equal to 2d sine theta, whatever the form you guys present. So I am not a lecturer or professor to explain that how the Bragg's law works or something. So I am just mentioning that you know it, or if you are considering solid state physics in the initial stage, these things will come in your mind. After that, you will do some EK diagram or something. So I am not so much talented to go into that part. So I am in the very basic part, that is these things you know already. Now the thing is that if I consider the XRD, the ACM, the synchrotron, so I already mentioned that if you consider the XRD, so don't be afraid by looking this image. So this is just considering the 360 degree. The range of the scanning is 360 degree. So as I mentioned in the Bragg's law, that formula is 2d sine theta is equal to n lambda. So the theta, so how you consider the theta? So that's the presentation. If you consider the same line is here, that is here it should be theta. So if you add both the theta, it should be 2 theta. So this is just a geometrical representation that how you will consider the theta. So there are actually 3 kind of XRD. That is the stage is actually fixed, and you can move both the source and the detector. The second part is that you can fix the source, you can move the stage and the detector, and the third part is you can fix the detector, you can move the stage and the source. So for all the possibilities, you can find the 2 theta with respect to the intensity. I will show that the few of the results outcome of the XRT. Now the synchrotron, this is very interesting image, if I am not wrong, that you can think that, wow, this is the some particle accelerator, something happening. So this is a synchrotron. You already see the same kind of picture in your book, and this is the scanning electron microscopy. This is also the function. This is also the very basic schematic of the function of the ACM, that the electron is coming and it is hitting the sample, and after that the signal is captured by the detector, and you will see what is happening after the ACM. Now, for me, what is solid state physics now? So this 2 image is basically the simulating image. I use the VASP or molecular dynamics. VASP is the software, so I use the DFT. Don't think about discrete Fourier transform. The DFT means density functional theory. So by using the DFT, molecular dynamics, and the software is VASP, we can create some structure like that. This is the copper structure for a specific purpose. So this is the simulating image. So this is not real. This is also not real. So you just you can see this kind of images in the 2D page of your books, and I created in the also the 2D screen, but in the 3D rotation. So this is the difference. So this is the simulating image. So I did it in my internship time, this kind of thing. So after that, now I am introducing you the real XRD, which I am using now. So this is the real image of the XRT, X-ray diffractometer. So this is in my lab. I am using the XRD. So what are these things? So this is very common. Just there are 3 parts. The left part, that is the source, the X-ray source. The right part, this is the detector, and the middle part, this is the stage of the sample stage. Okay. And if I zoom in of this portion, so you can see here the stage. So here you can see the shutter. So this is actually the cancelling all the scattered rays. Like when the X-rays is coming out from the source, it is going to the sample, and after going there, it is diffracting and it is captured by the detector. So during these times, actually some signals are scattered. So to reduce the scattering, we are using some shutter, and there is a very small gap in between the source and the stage and the source path. So we are using this to cancel the scattering, and here is a sample. You can see it is not, I don't know it is visible or not. Here is a sample and sample. This is things. So this is the actually real image of the XRT, and it can move up to 180. So entire 2 theta is 360 degree. And after that, this is the ACM, scanning electron microscope. So what is that? This is also very interesting, very cute image. I because my maximum time I am spending here. So this is the ACM. This is the from the outside you can see the ACM. You just forget about the 2 computers. In this computer screen, we can see the image. You can see the signals. So here you can see actually in our ACM we have actually 3 detectors. So here is the 3 detector, and this is the electron gun. So if you are going to the inside of the ACM, so here is the 3 detector. You can see the 3 detector, and this is the electron gun from here I think the electrons are coming. I don't know, because when the electron is coming, I can't see this because it should be in vacuum stage. So maybe from here the electron is coming, and this is the stage holders, same as that. So my sample is looking like this. So this is the actually molded sample. By using the epoxy, I actually molding the sample, and the sample is very tiny. I don't know it is visible. Okay. So this is the stage holder. So I just close the gate and put it in vacuum, and then I can use the ACM. Okay, and then this is the National Synchrotron Radiation Research Center. Oh, so where I am going every time. This is the NSRRC in Taiwan. So here actually they have two rings. That is one is TPS and one is TLS, the photon source and light source. This is really very big, and this is really very famous in the world. So okay, this is from, so I can take image. I can take this image like this without using the drone. So I just downloaded this image from so this is the NSRRC Synchrotron Radiation Center. So what is the insight in the Synchrotron Radiation Center? So TLS and TPS. So the source, the power, the energy for the TLS is 1.5 GeV, and for the TPS this is 3. This is really big. This is really big, and the number of beam lines, that is number of beam line 29 and 18. For the TLS 29, for the TPS it is 18. So what is the beam line? So when this is in operation mode, so there are a lot of beam lines. There is a lot of windows. From that window you can use the ray, you can use the for TLS the light, for the TPS the photon, you can use the ray. So there are a lot of windows you can use. So by using that source, you can do maybe scattering, maybe a chemical for some chemical some chemical purpose. They also used chemistry person. For biology also they can use for some analysis. I don't know because I know about for my work. I am mainly working the scattering part there, and also some residual strays and something I actually do in TPS. And for the for the TPS also there are 18 beam lines. So in the next image I will see the inside. So this is the inside of the beam line. Like this is one of the beam lines. So you can see the first image, the upper image. This is one of the beam line. So the beam line is like a small room. And the gigantic instruments. So you can see here in the down image, this is another beam line. So you can see the pipeline through which the electrons is running, is doing the athlete. So by using the rays, so this is actually 2D XRD. This is the 2D XRD detector. So this is the inside view of the NSRRC. So why I am going there? Why I use the NSRRC? This is a very interesting question. That is this necessary? Yeah, is it necessary? Why necessary? Because I also can do XRD in my lab, right? I already presented the image of the XRD which is in my lab. But the very interesting thing is that the energy. So here you can see the energy is around 1.5 GeV. So this is really huge. I can just give you an example that if I will do the XRD in my lab, the intensity, the maximum intensity I can get around 50K, 50,000. But when I am doing the same experiment in NSRRC, the intensity should maybe around 50 million. So I observe around 50 million, and more than 50 million. So you can understand the difference between the peak. So now what is the difference? If there is anyone who is working on this field, so they can understand the XRD. Okay. I will explain it in the next slide where I present the output. Okay. So don't be worried. So there is some differences. The XRD I am doing in my lab and XRD I am doing in NSRRC. I will mention it. So here I mentioned few things, that the peak intensity, the FWHM, full wave half minima, and the steps count and the peak to noise ratio. So these all the things does matter when I am considering this NSRRC. Okay. So now the laboratory work, what I am doing in my laboratory. Always I am using computer screens. So what I am doing? So actually we whoever do the research for the experiment, I am not talking about the theoretical part. The experiment, we have actually 4 stage. to do the research. First stage is the theoretical background. The name of this stage is called the literature review or the literature survey. So you have to collect the literature, you have to gather information as much as possible. So that is the theoretical background. After that, you need to prepare the sample on which you do the experiment. So you need to do the sample preparation, and after that the experimental work. So yeah, experimental work, and then the analysis of the result. So now okay, theoretical background, this is very understanding. Now the sample preparation. So sample preparation, actually there are two types of sample preparation. That is, you can buy the sample from the market, and the second part is you can prepare the sample. So for me, my professor always suggests for the PhD students, you guys need to prepare the sample. So I am preparing sample. To prepare the sample, there are actually three stages: conventional heat treatment, electropulsing treatment, and the chemical treatment. So I am actually using the electropulsing treatment. So if you guys don't know about electropulsing treatment, so I think you know, okay, maybe you don't know. Actually, I published one paper when I was in masters about the comparison between the conventional heat treatment and electropulsing treatment. For the conventional heat treatment, that is, you can directly use the heat to melt the sample and make the sample as you want. But for the electropulsing treatment, this is not like you are putting the temperature directly. It is like you are using the high voltage in the argon atmosphere, and then that voltage will using the Joule heating effect, it will create some heat, and from there you can do the sample preparation by using EPT. And the experimental work, there are a lot of experimental work like heat treatment, electrical treatment, mechanical stressing, microstructure analysis, crystal structure analysis, phase detection. So all these things you can do. So I am doing these things. And for the analysis, there are a lot of softwares. So we can use the softwares to simulate the results, to get the output. And finally, we need to do some math, that I am getting some results. So that's why I said that without theory, we can't establish our experiment. The same thing, that without experiment, some theorists cannot establish their theory. So we need to do some math by getting some help from theoretical scientists. Okay. So now I am showing you a very initial part of the experiment. That is, this is actually the EPT machine. This is called arc melting furnace. So you can see the zoom in image. That is the inside is actually argon, filled by argon. And this is the tungsten probe actually, and this is the copper plate. So we are creating some voltage differences, and then and then it will create the heat, the fire. And why we are using the argon? Just because of avoiding some reaction of the materials. So that's why we are using argon. And this is looking like the stage. So I actually very long ago, I actually used some copper balls to make like this. This is not my work, but actually I did it. I don't know why. Okay. Now how do we? Okay. So after preparing the sample, we have a few stages. That is, we need to make the sample okay, I forgot to put some images. Actually, we need to make it a very thin plate. The dimension is around 50 micron. The thickness is around 50 micron, and the radius is around maybe 200. Sorry, radius, not diameter, is around 200 micron. So we are making the sample like this. We need to make the sample too much smooth, that no contamination is there. So we need to do some polishing, vibratory polishing. So few steps are there. So I did not put it here. Okay. Now how do we analyze the output? This is also very interesting. So now the ACM. So what kind of images we can find from the ACM? So here you can see. So this is the scaling is around 10 micron. This is the scaling. The magnification is around 4K. So here you can see a different contrast. So this kind of contrast from this kind of contrast you can predict that there are multiple phases. there are multiple phases. Okay, so now when you received this kind of SEM image, you will put your sample in the EDX. That is also the EDX detector also in the SEM instrument. So from the EDX, what you can do the point analysis. Like you can select some points from this phase or some this phase or some this phase and do the analysis, and you can get the atomic percentage of the material. So by getting the atomic percentage, you can understand, oh okay, so this phase are present there. So this is the work of EDX, and after doing EDX, you also do the EBSD. So EBSD is actually to analyze the grains, the crystalline planes by using the backscattered electron. So the EBSD mapping image is looking like this. That you can understand that which grains are presented there. This is not related to my exact work, but I did it to show this presentation. Okay, now we can do the XRD. So yeah, so here is the XRD peaks. It is looking like this. So the x-axis is the 2 theta and y-axis is the intensity. So intensity I was talking about that in the lab the intensity is around 50,000. Okay, but whenever I am doing in the NSRRC, the intensity should be around 50 million or 60 million. So you can differentiate the intensity. So why I am doing that? Because for my personal work, actually I need to observe the weak peaks. Weak peak means this kind of peaks. Okay, so if the highest intensity is around 50K and the weak peaks around maybe these small peaks around 10K or 5K, so how I can say that this is the weak peak and this is the strong peak? Because the difference is very low. So that's why we need to do XRD in synchrotron, and from there we can understand, oh okay, so this is the actual weak peaks we can see. So to observe the weak peaks, we need to do a very ultra fine XRD, which can give you a more detailed result. So that is why we do the XRD in SRC. Okay, and this is the TEM image. So TEM image, so transmission electron microscopy. So from TEM image we can get the HKL spot. So these are the HKL peaks and these are the HKL spots. So from this HKL spots you can derive the d-spacing of the samples. So now you guys can imagine that you have the HKL peaks, you have the crystalline planes, you have the d-spacing. So can you make a crystalline something structure in your imagination? Or if you will put all these values in some software, the software will give you the crystalline structure. So that's why I said that yes, I can observe the crystallographic structure. Okay, so I am not seeing the exact crystallographic something structure in my eyes, but yes, I have all the values to make a structure. Okay, so here I mentioned that which image helps us to do which, that SEM morphology, predict the phase. So all the things, EDX, EBSD. Yeah, hello.
Yeah, I'm really sorry to interrupt, but then like we have a shortage of time, so can you please wrap this up within 5 to 7 minutes?
Yeah, sure.
Okay, thank you.
Yeah, okay. So this is my last slide actually. So the last slide is that I am introducing a very small part of in my research. So here actually you can see that I analyzed the eutectic phase transition and phase stability. So now another question is that what is the eutectic phase transition? So eutectic phase transition is something that if you are preparing some alloy, so the melting point of that compound material, it should be lower than the exact materials you used. So, and what kind of treatment I am doing, that is electromechanical, thermomechanical, and electrothermal. So these kind of things I am doing. What kind of sample I am using, that is a lead-free alloy. I am using. And what is the main observation? That is the electromigration and electroplasticity. These two are the defect mechanism. So if you guys, if you want to know, or if you already knew it, so this is good. So you can ask me that what is electromigration and electroplasticity. These are the defect mechanism. And I have two phases, that is the hexagonal phase and the monoclinic structure. So yeah, I need to observe that what is happening, why it is happening, which can stable the structure, and these things. So I am using this phase space. So I need to transform the phase space, and so I will not reveal the exact things what I am doing, but this is the outline what about my research. Okay, so yeah, so I finished. So maybe I am not so late. Okay.
Thanks a lot, Shubhananda, for your, very friendly and very fundamental, your talk at a very fundamental level. We all could understand most parts of it. So I had a basic question from this.
Yeah.
And that is like, say, theoretical condensed matter physicists, they use a few tools quite rapidly. The tools of quantum mechanics, statistical mechanics, and maybe coding. So like how much of it is used in experimental condensed matter, like material science and all? Like what you're doing.
This actually I did the theoretical work in my internship. So actually you are telling that the tools and coding, it is nothing. It is actually the DFT. Most of the theoretical condensed matter researchers, they are working on DFT, density functional theory. So this is one of the important tools to do the condensed matter research. So this is important. So as I mentioned that I need to do these things, right? So what exactly they are doing? So these things, all the experimental approaches I am doing in real, but whenever I am doing it real, it is costly. It is costly experiment. So before doing these things, we need to have some references that what is going on or what should be the expected result. So for these things, we also need to do the theoretical part. So sometimes actually experimental researchers are getting help from theoretical researchers, but in my lab, actually my lab is the collaboration. There are two professors, theoretical group and experimental group, both are staying together in my lab. So that is why it is very easy for us to handle both the things. But yes, before doing experimental, we need support of computational. Otherwise, it will take a long time. It will waste a huge money.
Oh, okay. Thank you so much. Thank you for the insight.
Okay.
Hello, sir. Sir, I'm Shreya, and I have a question.
Taking out your time.
Okay, you can ask the question firstly.
Yes, sir. You already told that the research you're doing, it's very useful in the industrial development that's happening in Japan. But I want to know the exact application of it in the industrial era.
Okay. Yeah, it's a very good. I am telling you the answer very shortly. Yeah, actually, my work is not directly involved with industry, but we have the industrial connection. That is, I said the defect mechanism, right? So the defect mechanism means whenever you are going to fabricate some semiconductor chips or some interconnects, so these kind of things, so you need to, whenever you will sell the product, you need to mention that how long the product will sustain. So before telling that, you should need to have the results, that how much current it can sustain, how long it can sustain. So for these things, you need to analyze the electromigration and electroplasticity, that how much current it can sustain, how long it can sustain. So there is a term that is MTTF, mean time to failure or median time to failure. So you need to understand the electromigration for this case. And the phase stability, I also mentioned the phase stability means that which phase will be stable for the long time. So this is whenever I have the result of these things, then I will give my result to the industrialist or the industrial researchers. They will analyze my result and they will use it in their direct industrial research.
Okay, sir. So thank you, sir. So it was one of the best sessions I had today.
Oh, thank you. Thank you so much.
Thank you, sir, for giving your time. So we'll move on to the our next speaker. I'm welcoming Mr. Niladri Modak. He's a PhD student at ISER Kolkata. He is presently working in the field of optics, and the topic of the talk today shall be partial reflection of a light beam and its implications. Niladri, you can start.
Yeah. So, am I audible?
Yeah, you are audible.
Okay. And one thing. So, are my slides visible?
Yeah. We can see yours.
Okay. Just give me. So yeah. So I made it full screen, but here it is showing that sharing is paused. So maybe 1 second. So can you see my slides?
Yeah, we can see your slides.
Okay. So yeah. Are you telling something?
No, it's fine.
Okay.
Fine.
Okay. So yeah, hi. I am Niladri. I'll be talking about this partial reflection of a light beam. So this here light beam is actually important term, and there yeah. Hello.
थकावट तो है भी पानी पीजिए खूब सर.
Some mic is on, I guess. Okay, so so it is a partial reflection of a light beam. So this light beam term is important here. Yeah. Okay, and I would say that it is really nice to get invited in this kind of a physicists meet, and it is also a nice initiative. I thank you, the organizers. Okay. So yeah, so I am from BioNap laboratory of Department of Physical Sciences from IISER Kolkata. Okay, so if you want to visit IISER Kolkata, you just drop a mail. So here is my mail ID, as you can see in the right bottom corner. So you can drop a mail. So yeah, I'll be happy to host you. Okay, so here is the outline of my talk. So mainly I will go into a qualitative manner. So I will skip this rigorous mathematical parts. So firstly, I will introduce you this partial reflection of an optical beam, and then I will go to optical beam shifts, and then I will show you these types of optical beam shifts, like longitudinal and transverse optical beam shifts, and what are those and how are this coming. But yeah, in a physical sense, not in a mathematical rigor. Okay, and then I will briefly mention our work, what we are working on right now. It is to show the non-separability of longitudinal and transverse optical beam shifts. Okay. So as probably you all know that light is a electromagnetic field, and which is a vector field. So these E0 e to the power I omega t minus kz. So assuming that light, this electromagnetic field is propagating in the z direction. So this term is actually this term is actually a scalar term. It is actually amplitude and phase of the field, and then this EX/EY column vector is actually a vector of the is polarization of the electric field. So yeah, so it is, although it is an electromagnetic wave, I am just taking for the sake of simplicity and the electric part of it. Okay, so it is this column vector is called the polarization. Okay, so what happens for when this light or electromagnetic field reflects from any interface? So in our probably in 10th, we all heard 10th or 12th, we all heard about this Snell's law. So when this light is yes.
Probably your slide. Have you moved on from your first slide yet?
Yes.
Okay, so your next slides are invisible. I mean, they haven't come up here.
Oh, sorry. So now is it visible or not?
Yeah, now.
Yes, it's visible now. Thank you.
Okay. I'm really sorry because, yeah. Okay, so, yeah, I was in this slide. So the animation will not be visible then. So if I cannot do the full screen, I think full screen is not working. Okay, so I was in this slide only. So where I was talking about this partial reflection of a plane of a electromagnetic field or light. So we all know the Snell's law when this angle of reflection and angle of incidence. So angle of incidence is theta, and the light is falling from like this is white line is white arrow is actually the incident light, and green light is reflected light. Green arrow is reflected light, and this red arrow is refraction. So we all know that this theta incident is actually equal to theta reflected, and there is a sine theta rule given by Snell's. So these Snell's law is actually includes only the scalar part of the electric field or of the light. But in the Fresnel's law, Fresnel actually included the vector part. So vector part is so what he did, like, so he gave you some he gave us some formula. So if you so by using this you can actually get the polarization of the reflected beam and polarization of the refracted beam if you know the polarization of the input beam. So it will depend on this N1, which is the refractive index of the first medium, and N2 of the second medium, and in the angle of incidence theta. So these all things you can find in any standard optics book like Born and Wolf or Griffiths maybe. Okay, so going to the next slide. Now. So as I mentioned in the previous slide, that this polarization is modified when it is reflected or refracted, and these modifications are basically your Fresnel's law. So to get a simpler algebra how this polarization is polarization modifies. The Jones proposed an algebra which is called Jones algebra. So where this electric field or polarization of the light, polarization of any field is written in terms of a 2x1 column vector, and there is a 2, so it is called Jones vector, and there is a 2x2 matrix which is called Jones matrix. So in case of partial reflection that I discussed in the previous slide, so partial reflection, this Fresnel's this Jones matrix of the reflection, which solely modifies the polarization part of the input signal, which is given by F, and it is like RP0, 0, and RS. Here RP and RS are actually called this Fresnel reflection coefficient, and the exact form I am not mentioning here. It depends on this N1, N2, and theta. These are the refractive indices and angle of incidence. Okay, so this form you can find it in Wikipedia also. Okay, so these, as you can see that as RP and RS, sorry, it is typo there will be RS. So RP and RS both are dependent on the incident angle. So this Fresnel matrix is also dependent on the incident angle. Okay, okay. So now going to the next slide. So for a plane wave. So as you can see, this all wave vectors are coming in the same direction. So your angle of incidence for all wave vectors are same actually. So here, so after reflection, this Fresnel matrix is operated on the incident field, and you will get the reflected one, and it is actually easy. So this beam actually so the reflected wave is actually like this, and refracted wave is like this, and the polarization is modified by F. But this plane wave is actually an ideal approximation, like from sun. Sun actually gives kind of a spherical wave, and when the sunlight reaches to Earth, like suppose here is where we are, like on Earth. So when it reaches, it becomes like it can be approximately like a plane wave. But it is not. So plane wave is not means easy to, or it cannot be handled in in what I can say in any instrument, by any instrument, like in our lab, or like you, whenever you are doing any presentation, or so you use laser pointer, right? So this laser pointer is not a plane wave. So in our lab also you used to do experiments using these similar kind of lasers or light sources. So these are not plane waves. So for plane waves, this reflection or refraction transformation is easier to handle, but for these real life light sources, it is not that easy. So plane wave is an ideal case. But what is real? Real is the light beam. So like a Gaussian light beam, or like, so I will discuss this. But we'll see that when we deal with a light beam, even partial reflection gives you some important implications of the light beam. We'll discuss in the next few slides. As these plane wave are really hectic to handle with, and this light beam are actually easy to get, so we will proceed with the light beam. What will happen for a light beam? Okay, so as you can see, this light, for the light beam, this electric field is slightly modified. So where these amplitude part is actually now dependent on the x and y. So it is called a amplitude distribution or envelope. Okay, what it physically means, like it has a finite transverse extent, and it has some specific distribution of wave vectors like in x and y direction, and basically using these electric field and tuning these E0, XY and some other parameters also, people have structured light in various ways. Like Gauss, they achieved Gaussian beam, they achieved Lager-Gauss beam, they achieved Hermite-Gauss beam. So you can go to this website. There is a lab in the South Africa. You can go and you can see how this means. There are some articles, some videos. You can go to that to get a flavor that what is structured light, and it is actually means a completely a different field of studies, like research field. So people have used this structured light in many applications. Okay, so next slide. Okay, so for a structured light, so as I mentioned that there is a specific distribution of the wave vector. So the each wave vector experiences different angle of incidence. So now, if angle of incidence are different for different wave vector, the polarization transformation is also different. Like as I mentioned, this Fresnel matrix is dependent on the incidence angle of incidence, right? So all together, if you see the reflected beam or refracted beam, you will see a completely different kind of spatial structure or polarization structure. So what happens when? So I am skipping the mathematical parts. If you go to this reference, this Journal of Optics paper, you can find that the algorithm that I mentioned, that if you have a distribution of k vector, you have different polarization of different of the different k vector of the reflected or refracted beam. You take all the contributions and you integrate. You will find actually in this article, it is all they have mentioned all these details. So basically, in summary, you will find the beam, reflected beam and refracted beam will shift. Shift means it will shift in x or y direction. So I'll give you some more physically tangible picture. So it will shift in x and y direction, and these beam shifts are extremely polarization dependent. Like you choose one input polarization, you see beam is shifting like this, and you choose one input polarization, you see beam is shifting like this. Okay, so these beam shifts have been extensively studied for last 2 decades, and there is some convention. So longitudinal shift is named as Gauss-Hansen shift, and as I mentioned, that it is basically dispersion of the generation. Means the reason behind this Gauss-Hansen shift occurs is like dispersion of RP and RS, like Fresnel, like theta dependence of the Fresnel matrices. And what I've not mentioned is there is also transverse shift, which is called invert-Fedorov shift or spin-Hall shift, that basically appears due to momentum gradient of the geometric phase. So it is actually little more hectic to describe in a pictorial format. So yeah, I'm skipping this part. So take this. This is also happening when a light gets reflects or refracts from any interface. Okay. So so now, as I mentioned, it's optical beam shifts. So it can be in longitudinal direction. It can be in transverse direction. So like you can see this picture where our conceptual understanding will say that, so this left red one is the incident beam. So we can assume means we can expect that this blue one should be the reflected beam or reflected one, but actually this red one is the real reflected beam. But in our naked eye, we cannot see this kind of beam shifts, right? Whenever we shine a laser light or laser pointer in a mirror, we cannot see this kind of beam shift because this shift is of the order of wavelength, like nanometer. Like you are dealing with a 632.8 red laser, and it is like 600 nanometers. So you cannot see this, right? So that is why we in our daily life we cannot observe this kind of beam shifts. And as I mentioned in the previous slide, it can also happen in the transverse direction. So it all depends on the input polarization. Okay, so now I am reading this. So these beam shifts observed in diverse optical systems like partial reflection. Here in the bottom, it is written that the systems which shows this kind of beam shifts in partial reflection, refraction, or total internal reflection, or transmission through a tilted anisotropic medium. Okay, these kind of systems usually show these beam shifts. So yeah, okay. So here I have mentioned that these beam shifts are not only fundamentally interesting, but it has many potential applications in metrology. Okay. Okay. So as I mentioned that these beam shifts are of the order of wavelength or very small. So detection of these optical beam shifts are really a challenge. So here I'm showing a setup. This we usually perform in our lab. So there is a setup using which you can see the beam shift. Okay. So here is a laser light coming, and it is a pre-selection. It is basically a polarizer which determines the input polarization of the beam, and then it reflects from a prism, which is an air glass interface, and this interface gives you the beam shift. To see the beam shifts, you post-select, means you put another polarizer and you select the specific polarization of the beam shift of the reflected beam to get the beam shift in the camera. As you can see that here, okay. So let me explain this one first, this graph first. So here, average of x determines the centroid shift in x direction or longitudinal direction. Y is the same for y direction. And as I mentioned, that controlling pre-selection and post-selection, which are basically polarization state of the input and output beam, you can basically detect and tune the shift. So there are some cases where you can see only longitudinal shift. Again, by tuning the pre-selection and post-selection, there are some cases you can find only transverse shift, and you can excite both shifts simultaneously. Okay, like here, you can see that for some particular input and output polarization, we have seen this kind of shifts. We are changing the post-selection parameter, or like we are rotating this post-selecting polarizer. You can see this beam is going like this, and then this. So in a camera, what we can see is like this. So first when for figure A, you can see this when there is both shift present, like longitudinal and transverse shift. Actually, you can see a diagonal shift of the beam. You can see that after post-selection, after passing through this second polarizer, you can see this beam is diagonally shifted. And then if you have a vertical or transverse shift, so it is actually, or Y shift, you can see this beam is going upward or downward. Okay, so here is the reference I have mentioned. So I have taken a screenshot of this paper. So it is the paper from our group only. So it is like simultaneous Whitfield amplification of angular Gauss-Hansen and invert Fedorov shift in partial reflection. Like I have mentioned this Gauss-Hansen it is actually longitudinal shift. Invert Fedorov, it is transverse shift, and partial reflection also I have mentioned. And I have mentioned that there are some cases, there are some scenarios where simultaneously both the shifts can be excited. And the technique I have mentioned in the previous slide is actually called weak value amplification. Okay, so it is actually inspired from a quantum mechanical weak measurement phenomena. I am not going into the details of it. You can go to this paper to get some references. Okay, so going to next slide. So now I am going to my work. So now it is okay 5:10 by 5. Okay, so my work is, we have experimentally demonstrated the non-separability of longitudinal and transverse beam shift. So what does this mean? Like specifically, so what it means, like specifically when we are showing that whenever there is a shift in longitudinal direction, there will also be a shift in the transverse direction or vice versa. And importantly, this non-separability is manifested as a position-position classically entangled state. Okay, so as I mentioned in the previous slides, that this GH shift or this longitudinal shift appears due to the dispersion of Fresnel matrix. So dispersion of Fresnel matrix. Okay, and on the other hand, this IF shift or this transfer shift originates from the, as I mentioned, this momentum gradient of the geometric phase. So there are some other terms which is I am avoiding, so because it needs some background. Okay, so you take only this part, this momentum gradient of the geometric phase. Okay, so due to this fundamentally different origin, these beam shifts have treated completely separable manner. Actually, I should say that people have not thought about they can be non-separable in nature. And in this paper also you can find that they have treated it in a build up a treatment on which this further work has been done. So this treatment is actually assuming these beam shifts are separable. But in contrast, what we are proposing is these beam shifts are actually inherently non-separable in most of the experimental parametric region. But this non-separability is so small that you cannot detect this non-separability, and you can assume what this paper has assumed. But some region, you cannot neglect this non-separability. Okay, so here is our experimental system. Okay, hope you can see this, that there is a laser over here and it is passing. It is the same system that I have mentioned previously. So here is a polarizer and a lens is kept for a purpose. Okay, so there is a polarizer and it is a prism and prism, and it gives you this partial reflection or the beam shift, and then it is P2. You analyze the output polarization, and then there is a camera. You detect the beam. Okay, so yeah, so you know everything. So this last point I should mention that this post selection parameter is given by epsilon. So this epsilon I will use in my couple of next slides. Okay, so this post selection parameter is epsilon. So what is epsilon? Epsilon is basically, so you are giving, suppose this polarization means input polarization is horizontal like this, and your output polarization is vertical. So epsilon is overlap between input and output polarization, like overlap between P1 and P2. Suppose P1 is horizontal and P2 is vertical, the overlap becomes 0. Okay, like this. So yeah, so here are two schemes. We have done the experiments. First scheme is minus 45 degree input polarization. So I am skipping the mathematics. So this mathematics can be found in this reference. You can go to this reference. Okay, so for the first scheme, we have intentionally chosen for the particular input polarization where we can get both longitudinal and transverse shift, like both GH and IF shift. Here we saw that the non-separability increases at epsilon tends to 0 from the mathematical calculation. Okay, we saw that around epsilon tends to 0, like when your pre-selection and post-selection are exactly orthogonal, in this region, you can see this non-separability to be enhanced. And the second case is horizontal input state. For horizontal input state, your only means in the literature it is written that this for horizontal input state, as I mentioned that for specific input polarization state, you will see some specific beam shift, right? For horizontal input state, you should see a transverse beam shift. But we have seen that around Brewster's angle of incidence, you can also see this horizontal beam shift. Okay. So that actually demonstrates these beam shifts are non-separable, and this non-separability is detectable at some parametric region. Like here, epsilon tends to 0, and here this incident angle to be around Brewster's angle. Okay. So as I mentioned, the position of the centroid in x direction is given by x. This average of x, and position of the centroid in y direction is average of y. And to measure the non-separability, we have used this Pearson correlation coefficient given by rho. Okay. Okay. So next slide. Okay. Here are the results. You can see that. So for minus 45 degree input polarization, you can see this both shifts are present. Like your red solid line is your x shift in x direction, and your magenta solid line is shift in y direction. And you can see this non-separability, or this rho or Pearson correlation coefficient, is almost 0 everywhere except around epsilon tends to 0. And it is a theoretical prediction. So it is not quantitatively matching with theory, but it is, you can say that it is a qualitative match. And for horizontal input polarization, you can see there's so as I mentioned that for horizontal input polarization, only transverse shift is present and you can see the non-separability around Brewster's angle of incidence only, right? So you can see that when angle of incidence is 50 degree, you can see this rho is actually 0 in most of the post-selection angle. But when you approach Brewster's angle is for a glass prism, Brewster's angle is 56.31. So as you can see, for 56.1 degree, you can see there is sudden jump in your non-separability parameter or rho, and it is a theoretical prediction. You can see that for when I'm reaching from 50 degree to 56.2 degree, your non-separability is enhancing. Yeah, so it is proved now that the beam shifts are actually non-separable. Now implications. So from the non-separable beam shifts, we achieved the tunable position classical entangled state. So I'll briefly mention what is this. So for minus 40, so like now I am concentrating on the first case where input polarization is minus 45 degree. Okay. So your theory predicts this kind of beam structure, and experimentally also we achieve similar kind of beam structure. Okay. Now suppose this beam structure I am schematically representing in the right figure. Okay. So suppose I am changing my coordinate system from xy to a 2 qubit representation. Like your first qubit is right and left, R and L, which is in x direction, and second qubit is up and down, which is in y direction. Okay. So if any beam structure, any beam in this RULD coordinate system can be written like RU plus LU, some coefficient into, sorry, I have missed the coefficient here, RU, some coefficient into LU, some coefficient into LD, and some coefficient into RD. Now, if the beam lies in diagonally opposite direction, you can get this thing like RU plus LD, and this is actually a maximally entangled state. Okay. So as you can see, there's so as I mentioned here, so for epsilon tends to 0 or epsilon equals to exactly 0 degree, you get a two-lobe beam structure. Now you change the angle of incidence, your beam structure, this two-lobe will rotate like this. Okay. So as you can see, when this two-lobe is like vertical, then you lost the maximum, you lost the entanglement at all. And when this two-lobe is exactly diagonally opposite direction, so these two lobes represent a classical entangled state. So we achieved a tunable position classical entangled state. Like why position? Because it is all in the position coordinate, and there is no quantum nature here. So there is no non-locality here. It is only classical entangled state. Like like you have only the non-separability, no non-locality here. Okay, so what is the implications of it? Like I found a group in the same group that I mentioned earlier. So you can go to this web page. So they have recently patented, as you can see this patent, the name of the patent is Method and System for Hybrid Classical Quantum Communication. You can follow the papers by this group. You can see this classical entanglement is actually very much needed or very much useful for the communication purpose. Like they call it classical quantum communication. There are a series of papers on this from, I guess, 2013 and 14 or so. Okay, so what I've discussed. So in a nutshell, we have discussed like optical beams refracting from any interface experiences tiny beam deflection. Okay, like these beam deflections can be in longitudinal direction and in the transverse direction. And we have demonstrated this longitudinal transverse beam deflections are actually non-separable. Okay, and this non-separability generates tunable position non-separable state or position classically entangled state. Okay, these are all. I have tried to give you a flavor in a qualitative manner. Okay, hope you have understood. So they understood. So these are the contributors. He's my guide. He's my collaborator from IIT Hyderabad, and then Priyanuj, Asutosh, Sayon, and Sayantan. Okay, yeah. So there are some relevant articles. You can look into it. So yeah. Okay, thank you, and you can contact me anytime. So here my mail ID is given. Okay, thank you.
Thank you very much for your talk, Niladrida. I don't see any questions. So yeah, I guess you have left your email ID. So if anybody has any questions, they can contact you there. Thank you for this talk, Niladrida. I mean, you have taken us through the basics and explained it really well. So thanks about that. Thank you for sparing your time for this. Thank you for sparing your time. So yeah, that's it. Thank you. I request our audience to wait for some time, be patient, because our next speaker is taking some time. So I'll request everyone to just wait for some time. Okay, hello. So we are back again. So our next speaker on this list is Miss Tanya Tripti from Niger. She works in the field of cosmology, and the topic that she'll be presenting today is galaxy formation with the 21 centimeter line of neutral hydrogen. Miss Tanya, you can take the stage. Miss Tripti, are you there? I guess there was some miscommunication. So, Miss Tanya Tripti, so will you be able to start now? I'm just asking this for clarification.
Yes, I can start now.
Okay.
Is my voice clear?
Yeah, your voice is clear, but then I guess there was some gap, so I'm introducing you again so that the speakers might know. So our next speaker is Miss Tanya Tripti. She is from Niger and she works in the field of cosmology. The topic that she'll be presenting today shall be galaxy formation with the 21 centimeter line of neutral hydrogen. Ms. Tripti, you can speak now. Thank you.
Yeah. Hello, everyone. First of all, I would like to thank the speaker for this intro. And also, I would like to thank the organizers for putting their effort in this meet. Okay, so now back to the talk. So can you see the slides?
Yeah, we can.
Yes, we can.
Oh, okay. So as I came to know that most of the audience are basic PhD students, so I try to keep my talk a little on the fundamental level. But if at some point any of you feel that I'm going a little overboard, so you can stop me. Okay, so the topic is here, study of galaxy formation with 21 centimeter H1 line. H1 is atomic neutral hydrogen, which in scientific term is written H1. So here is the overview of the talk which I am going to give. First of all, I will explain how the neutral hydrogen is present in our universe, life history. Then how we get 21 centimeter hydrogen line. I will briefly explain Kenket-Smith law and dark matter halos, and then the survey which I am going to work on is alpha-alpha survey, and so on. The H1 mass function, H1 velocity wave function. Those we will go through if I will have some time, but mostly I will focus on these 5 topics. So okay, let's start. So I'm pretty sure most of you have seen these images, like how the Big Bang happens and then how we got to the present day of the universe. But in this talk, I'm going to focus mostly on atomic hydrogen, how we got then where the atomic hydrogen is present in present day. So okay, so at the redshift of approximately 1100, when we have epoch of recombination, where the ionized baryons and electrons combine, so it reaches CMB, as most of you know, and then the universe became neutral. So that is referred as cosmic dark ages. Then under the influence of gravitational forces, the atom starts to collapse. So we find the first stars, which form approximately at a redshift of 30. Then there is a formation of galaxies, which is approximately at the redshift of 20. Here I want to emphasize on the fact that these data are not accurate. We are still discussing over these numbers, but the formation is like this. First we formed stars due to gravitational instability. Then because it's a hierarchical process, we formed galaxies. And then when these galaxies form, due to collapse, the UV radiation reached out. So that radiation interacted with the atoms which are present in the outside the galaxy, and that ionizes them. That is termed as reionization. So now most of the atoms which are present outside the galaxy became reionized. But what about the gases which are inside the galaxy, which are gravitationally bound inside the galaxy? Because they are self-filled, they will not be ionized. And now in the present day, we can only find neutral hydrogen in these galaxies. It's not to say that we don't have neutral hydrogen outside the galaxy. We do have, because atoms always recombine, like they get ionized, then they recombine. But because it's very less in numbers, we don't detect that many of gases outside the galaxy. Now, how are we going to detect these hydrogen atoms? So one is 21 centimeter hydrogen line. Now, how the 21 centimeter line formed? So you all know that hydrogen is made up of one proton and one electron. Both have their spins, and because of their spin, they have their magnetic moments. When these magnetic moments interact, they give rise to a hyperfine splitting. So that energy difference is very small, approximately 10 to the power minus 6 electron volt. Because of that, their wavelength is very large, like lambda equal to 21 centimeter. So from here we get 21 centimeter hydrogen line. One thing which should be kept in mind is this 21 centimeter is in the rest frame. Like the observer and the source from which we are obtaining this radiation, if both are in the rift, then only we get 21 centimeter. In real world, it's not possible. Mostly galaxies are moving away from us. Some of the galaxies may come towards us. But anyway, so that these lines will be shifted depending on the relative velocity between the source and the observer. So we will have to keep that in mind also. Now, like, why are we so focused on neutral atomic hydrogen? So we have if we are going to describe a galaxy, we have three features by which we can describe a galaxy. We have cold gases. Cold gases are mostly atomic and molecular hydrogen. Then we have stellar masses, and we have star formation rate. Star formation rate is basically the amount of cold gases which are converted to stars per year. So that is star formation rate. So we have a relation between star formation rate and cold gases. It's a power law relation which was first suggested by Smith and then later observationally proved by Kennicutt. So here I have shown a plot from Kennicutt's first paper where he has shown the relation between the star formation rate, the surface star formation rate, and the surface molecular gas in the log-log plot. And here you can clearly see that there is a linear relation between these two quantities. These dots, here we have three different data. First is a filled circle, which is a normal spiral galaxy. Then we have square filled data, which is starburst galaxy. Starburst galaxy are those galaxies where the star formation rate is greater than usual. Greater, like how much greater? So for understanding, you can understand that our Milky Way galaxy is a normal spiral galaxy where the star formation rate is 3 solar mass per year, approximately. In the starburst galaxies, it may go up to 100 solar mass per year. So those galaxies basically die out very fast. But to show the range, like the star, you can see that the cold gases, the mass of cold gas and the star formation rate is pretty high in these starburst samples. So to get the full range, he has plotted these two. And then we have these open circles. So this open circles, because These field circles and the squares are looking at it as a disjointed field. So to make a smooth transition, we will use these open circles. The open circles are the center of the spiral galaxies. So here we see that we have a relation between star formation rate and cold gases. Again, I want to point it out that this relation, although it's a power law relation, but this factor 1.4 depends on the sample which we want to choose. So we know that there is a relation between these two, but this law is a little different for different sample and people are still working on it. Okay, so this is one aspect of studying neutral atomic hydrogen. The second is dark matter halos. I don't know if some of the people have heard maybe of this dark matter. Like how do we first came to know that there is something called dark matter inside the galaxy. So here I have shown a plot of these are the rotation curves where I have shown the rotational velocity in the y-axis corresponding to the radius in the x-axis. The radius is distance from the center of the galaxy. So this galaxy is NGC 1090, which I have taken from Spark catalog. It's a spiral galaxy. These field circles are the rotational velocity which are observed from our observation. At high radius, at larger radius, we won't be able to detect it in optical spectra because most of the stellar mass are concentrated at the center, whereas the H1 disk is more extended out. So if we want to make measurements at larger radius in a galaxy, we want to measure the H1 content. So here what we see that even if we account for the amount of cold gases present in the galaxy and the amount of stellar mass present in the galaxy, we cannot account for this behavior. So there must be a third term which is adding, which when added up to these two components will give me this rotation curve. So that component is termed as the dark matter halo. So from here, what is important for us is that from H1, we can also detect the dark matter in the galaxy. So what we have gleaned from this far, that 21 centimeter line is a good probe of galaxy formation, large scale structure, and dark matter halos. And now I will use this line to study different aspects of galaxy formation. Now this is the survey which I am working on. This is the alpha-alpha survey. Alpha-alpha is a blind radio survey. Blind in the sense that when in the process of taking data, it just scans the sky and they take the data. Opposite of it is a targeted survey where we spend some time on a particular patch of the galaxy. Both have their usage. Radio in the sense that it take data in the radio region, which is 1 centimeter, 1 kilometer approximately. Now I am working with 100% catalog. The alpha-alpha has also reached the 40% and 70% of its intended area catalog in the past. But 4 years prior, it has released the 100% catalog, and now people are working with the 100% one. So for any survey, the first thing which anyone want to know is where are the galaxies, where are the sky, which part of the sky is it taking its values from. So here we have two different parts of the sky. First one is we can categorize it as a northern hemisphere or the fall region, and the second is the southern hemisphere or the sky or the spring region. So and the figure 5 is the sky distribution of this galaxy, where I have plotted the declination and right acceleration of these galaxies in degrees, just to get initial feature of what these galaxies, where these galaxies are present on the sky. For those of you who don't know what right acceleration and declination is, it's just a proxy for theta and phi, the theta and phi which we use in spherical polar coordinates. Also some distribution is there, but it's like you can understand it by comparing these two. From there we have the angular area. Angular area is the solid angle which is substance. sinusoid angle cos theta, d theta, d phi. Then there is a redshift bound, like up to this redshift, we are taking this survey sample. Then you know that if there are any observation, there is always some noise associated with it. So if we have a quantity called signal to noise ratio, and if its quantity is greater, the observation is more reliable, the data is more reliable. So here also we try to put a cut on signal to noise ratio. And then after doing that, we have 24,713 galaxies. So these galaxies are enough in numbers to detect, to give any information about how the sample is distributed. In the figure 6, I have done the same survey sample, but here the distribution is between RA and the redshift. So now I'm going to show you a galaxy, a spiral galaxy, in 3 different observations. One is the galaxy's name is UGC 07849. It's a spiral galaxy, which is the figure 11. We have the optical image of this galaxy, and you can clearly see that there is a bulge in the middle, and at large distance you can see that it has its arms. The same galaxy, which when looked on in optical spectra, you can see that this is the flux versus wavelength for this galaxy, and you can see we have different emission and absorption line. These are the similar like 21 centimeter hydrogen line. So these are for different elements, and from here you can know about which elements are present in a galaxy. But here most of my talk is focused on the alpha spectra. So now I am going to talk about this alpha spectra. So here you see this emission. This emission is what I have told, the 21 centimeter hydrogen emission. So you see that there is clearly a peak here, which is at a velocity of 6,000 kilometers per second. So from what else can we know from this spectra? The first is this peak is approximately at 6,000 kilometers per second. So you, I don't know if you people know or not, but if we have a velocity, then from there you can calculate the redshift of the galaxy via the relation V equal to C into Z, where V is the velocity, C is the speed of light, and Z is the redshift. So from redshift we can also calculate the distance at which the galaxy is situated. The flux can also be calculated after integrating this spectra. Then we have a quantity known as W50, which is basically full maximum, half width at full maximum. So here this is the maximum limit of maximum flux. So if we take half of it, and then we calculate this region, this line, this horizontal distance, that is W50. From here we can also calculate the H1 mass, which is inside the galaxy, via this formula which I have written here. So it is derived from Einstein coefficients, which I am not going to talk about, but from here we can also derive the MH1, which will be very beneficial for us. Here are some of the number distribution of these quantities, just to get a feel of the range of these values, these quantities, and also how they are distributed. Like in the first plot, you can see that the different galaxies don't have any like dependence, but we can see that the CZ is limited to 15,000 kilometers per second, which is to be expected because our redshift cut is 0.05. In W50, we see that the more for low W50, we have more number of galaxies. For the flux, it's a Gaussian distribution where we have for 0.0 to 0.5, we have large number of galaxies. In the signal to noise ratio, we can see that most of the galaxies have low signal to noise ratio, and as we go at high signal to noise ratio, we get very few number of galaxies. The most interesting of these plots are the fifth one, where I have plotted MH1, like H1 mass, and the number distribution H1 mass. So here what you see that most of the H1 mass is in the between 8 to 10, 10 to 8 to 10. But what about this low mass region? So here we are seeing that we are not able to detect this low mass region. So, but it is not possible that because we should have more number of galaxies which have low mass compared to the galaxy which have higher masses. So the one explanation is that our survey, our detection is mass sensitive, and it is not able to detect the galaxy which have a low H1 mass. So then we have to imply some method such that we correct our sample so that we can account for this low mass galaxy, which right now we are not able to detect. Speaker, can I know, sorry, can someone tell me how much time do I have left?
You have 5 minutes.
Okay. Okay, so I'm just going to go over 2 galaxy and 2 more slides, and then maybe I can stop for the question round. Okay. So now these are just the plots to summarize like what is going on in this survey. First of all, we see if we have a plot between signal to noise ratio and the profile width, we see that there is not any visible correspondence between these two quantities. On the other hand, when we see about the H1 mass and distance, what we see is that if we move at higher distance, there is a lower bound on the MH1 which we can still detect. And as we go at larger distance, we see that this lower bound increased rapidly. So at a high distance, we are not able to detect low mass H1 galaxies. What does that mean? That means that our sample is a flux limited sample where the detection of the galaxy with low H1 mass depends on the distance. So the first thing is, if we have a galaxy which has low H1 mass, if it is far away from us, then there is very less probability that it will be detected by our survey. Now, and we know that the MH1 is dependent on the flux from the previous relation. So that means that if a galaxy has high flux, then that can be detected. But for low fluxes galaxies, they have less chance of being detected. That's one thing. Now, if we have a plot between the flux and W50, we are seeing that this detection not only depend on the flux but also on W50, because you can clearly see that at larger W50, you cannot detect all the fluxes. Like for the same flux, if we have low W50, then that flux can be detected. But at high W50, we can't detect the same flux. So that means the detection of an object depends on both flux and W50. Okay, so I think I will stop my talk here. And yeah, now I am open to questions. Hello.
Hello, I don't see any questions, neither in the Teams nor in the YouTube, I guess. Okay, there's a question, I guess.
Okay.
Okay, I wanted to know, like, you're saying that you collect samples. So I want to know, like, how you collect the samples. What instruments do you use?
Oh, okay. Actually, this sample is not collected by me. This is like it's a very different thing. Like for one team is that collect sample, and the second team is which interpret the results from that sample. So I belong to the team which interpret the results which we get from the sample. But from what I know, I can tell you that it's you can go on Alpha Alpha site if you are interested in this. They have a big radio telescope. You know that because the radio telescope it detects very large wavelength, like 21 centimeter. So if it if it detects that wavelength, then it has to be a very large in length. So in Alpha Alpha, it's a very large radio telescope, which is.
Okay, I'll make sure I'll go through that website.
Okay, I think you should. Okay. Okay. Any other question?
Actually, I'm really sorry to say this, but probably we made a mistake in calculating time. You actually have some more time left, so if you want to continue, you can.
Yeah, I actually have some slides left, but I thought that it's better to. Okay, then
Also,
maybe I
we
can
probably have a question. We probably have a question as well from Ravi Shankarji, something like that.
Okay.
Am I audible?
Yeah.
Yeah, sure. Yeah.
Ma'am, I had a short question actually. That you have used the Kennigan-Schmidt law, right? So I had a doubt that is it only for spiral galaxies or it can be applicable to elliptical and galaxies as well?
From what papers I have read, it is applicable to all the galaxies. They have, although they have pointed it out that the dependence is more on the molecular hydrogen, that correlation is more tightly bounded in comparison to the atomic hydrogen. So that is one thing, but regardless of that, it is valid for all the galaxies. But for a spiral galaxy, it is easy for us to detect and make measurements. Like in rotation curve, also you can see that we have for a spiral galaxy. So yeah, that's why they have shown it the spiral galaxy. But I think in some of the papers we will also find this relation valid for the elliptical galaxy, and they have plotted it out. So yeah.
Okay, ma'am. Thanks, ma'am. Actually, I was going through the papers of Kennigan and I was just observing all he has discussed is about the spiral galaxies.
Yeah, actually, Kennigan has done
observations.
Yeah, because Kennigan has done his work at I think 1989, and then he has some papers on 2 years later. But currently, I don't remember the author's name, but they are doing it in 5 different galaxies. So now, because we have more number of data at the time of Kennigan, when Kennigan had done it, he has very less amount of data because we didn't have that sophisticated instruments which we now have. We can now probe inside the galaxies as well. So yeah, now I'm sorry, I don't remember the name of the papers, but they have now working on different other type of galaxies as well. So you can look that up if you want. It's valid for all the galaxies. That is true.
Okay, ma'am. Thanks, ma'am.
Thank you. Okay.
Okay, ma'am. You can. Sorry for the inconvenience. Please carry on.
Okay. Okay. So now I will come to what I am working on. So I have pointed it out here in this eighth figure that we are not able to detect galaxies which have low mass, low H1 mass. So we want to have some method from there we can account for this. So this is a H1 mass function. H1 mass function is basically the number density of object with H1 mass range between MH1 and MH1 plus DMH1. So here I have divided this bin in logarithmic bins. And this is just the numerical formula of what I have described. Now this H1 mass function can be fitted with a 3-parameter vector function. So what are the 3 parameters? This is the 5 star, which is an amplitude. M star is the knee mass and alpha is the slope. So these are the three parameters which describes a vector function. Now, if you see in this relation, there is two different dependence. One is this power law, and the second is the exponential one. So if you see at low h1 mass end, you see that the power law term dominates. So we have a systematically increase in the h1 mass function. But at high mass, this exponential term dominates, and we see that it's rapidly declining. So which I'm going to show in the next slide. So now we have two parameters for accounting this h1 mass function. First is this 1 by Vmax method. Why we are using this? Because what I have previously told you, that we are not able to detect low h1 mass galaxies in our sample. So we have to give some weights to those low mass galaxies such that at some point all of them are at the same situation, and then we can be able to detect it. So how are we going to do that? In the 1 by Vmax method, we are saying that let's take a galaxy and put it at a distance up to which we can still see that galaxy. If we are getting that Dmax, so now we are calculating the volume corresponding to that distance, and we are weighing it, we are giving it weight according to that volume. So that method is known as 1 by Vmax method, where we have assumed that the distribution of the galaxies is homogeneous, which we all know that it is not true. Some of the places will be dense, some of the places will be not that dense, like there will be some voids there. So we have a different method, which is stepwise maximum likelihood method, where we are assuming that the distribution of galaxy is a bivariate distribution. I have shown in this plot that the detection will depend on both the flux and the profile width. The flux is directly proportional to the mass. So this distribution, we will say, is a bivariate distribution of MH1 and W50. And we try to maximize it on all the galaxies, and then we are going to find this h1 mass function. So here you have in the figure 13, we have the h1 mass function, where in the x-axis we have MH1, and in the y-axis we have h1 mass function. And here you are seeing that these field circles are what we get from the 1 by Vmax method, and the open circles are what we get from the 2D stepwise maximum likelihood method. This is just to show you that both these methods are mostly, the result of these two methods are mostly equal, but at low mass it shows significant difference. Some in high mass as well, but mostly in the middle region it's same. So we have to decide what we want to use, because in a stepwise likelihood method, because if you have more number of galaxies, the calculation will be more, and then you have to see account for that calculation as well. So right now people are using the combination of 1 by Vmax method and 2D stepwise maximum likelihood method to get a better sample. So now then similarly we also have h1 velocity width function. Here it has the same concept. The h1 velocity width function is the underlying density of objects with velocity width range W50 to W50 plus dW50. But here the fitted vector function is little modified. So in the previous one, this exponential term is not any power, but in the velocity width function, we see that this exponential is a power of a beta quantity. So now we have 4 parameters to fit this function. What we can do from this, that is the question, like why are we describing this h1 mass function, h1 width function? We basically try to see if there will be some variation if we are computing this mass function at different regions or on different galaxies. So here is an example of Oman's work, where he has plotted the h1 width function for different sky regions like I have told you previously, that alpha alpha survey is on two regions. One is sky region and the second is the fall region. So in the first plot, he had H1 width function, and in the right one, he has shown for the spring and the fall region, where the green one is for the spring region and the orange one is for the fall region. So this yellow line is a little shifted to show you the variation clearly. So here we see that even though we have two different regions, the H1 width function doesn't vary much. Like it has the same form, just the normalization factor is a little different. But in the bottom plot, it is doing the same thing with the H1 mass function, where you can clearly see that this yellow and the green line overlaps at the high mass range, but at the low mass range, it has significant difference. So from here, it is clear that the H1 mass function is different for different region, but the H1 velocity weight function is same for the two regions. So from here, you can also say that the H1 weight function, because it's related with the halo, and the halo is the same for the galaxies. So that's why we are seeing that this region dependence is more on H1 mass function, where it's not present for the H1 width function. Okay, the same work can also be done when we divide our galaxies on the basis of blue and red galaxies. So blue and red are their optical magnitudes. So where we have said that after we have put a cut on the galaxy, and we said that after this galaxy we are categorized as a red galaxy, and it has more magnitude, it is called blue galaxy. So here also Datta has done the same thing, where she has distributed this galaxy in the blue and the red ones. So in the first plot, where we have the H1 mass function, you see that at high mass end, the red galaxy dominate, where in the low mass range, the blue galaxy dominate. The same feature can also be seen in the H1 width function. But here, at high mass end, the difference between the red and the blue one are not that pronounced, whereas in the H1 width function, this difference is more pronounced. So from here, you can also see the dependence of different galaxies. You can also relate the H1 property with the optical property of a galaxy. So right now we are moving towards these terms. So I have not included all those works because then the talk will be too large. But yeah, so we are working in that direction to relate the radio properties with optical properties. Okay, so that's the end of my talk. And now maybe if someone has any query, so they can ask it.
Okay, so I don't think there is any query yet. The queries have been asked, I guess. So thank you, Tanyadi. Thanks a lot for your engaging talk. I saw questions being raised, so that's a thing. So thank you for sparing your time for this. Wish you the best of luck.
Yeah, thank you for inviting me.
Yeah, you're always welcome. Thank you for showing up, and thank you for accepting our invitation. So yeah. Okay, so we'll move on to our next speaker. He is a student at NISA. His name is Rajdeep Ta, and he's presently working on quantum walks. The topic that he'll be presenting on shall be quantum walks and controllability on graph structures. So Mr. Rajdeep Ta, you can speak now.
Am I on?
Your audio is breaking actually. Can you please speak again?
So, am I audible now?
Yeah, it's audible.
So, the slides are visible, right?
Yeah, we
Yes, it's visible.
Okay, so thank you for giving me the chance to present talk on the topic quantum works and controllability on regular graph structures. I am an integrated master student at NISER. So I will very briefly go through what are the contents which we will discuss in this talk. So the main topics will be Markov chain, countable spaces, stochastic generator. Then we will define the graph structure and we will work on our problem. And then the properties of random walk and quantum walk for a general graph, the analogy between classical and quantum walks, point quantum walks on general graphs, controllability of the graph and theorem for controllability. Then we will discuss about the topics of orbits of permutation. Then we will give some algorithms and example, and then the final part will be discussing the future scope of this work along with the references. So before I go into the topic, I will just discuss very briefly a few of the important portions which are necessary for understanding quantum works and general graph structures. So before that, we need to understand what is a Markov chain. So I have briefly written down all the definitions in the slides, so it will be very easy to go through. So a random walk, which we define, is basically like a succession of moves, which are like generated in a very random manner. So we use the specific term called stochastic. So they are generated in a stochastic manner in a given state space omega that generally has a more complex structure than linear chain. Like most of us have done random walks, or we have already performed problems, solved problems which dealt with probability, like probability of finding a walker in a moving in a one-dimensional line, and all those stuffs. But random walk in general case is defined for a much more complex structures, much more complex system. So then we can say that they are like mainly memoryless. Either that is they are uncorrelated in time, and if the stochastic moves or the random moves are correlated with time, then we use the term called walk with memories, and then they result in non-Markovian walks. So now we need to point here that this thing which I've written, that they're uncorrelated in time, that doesn't necessarily means that they're uncorrelated with the position of the walker. Like these walks can depend on the position of the walker, but they need to be independent of time for depicting Markovian characteristics. So we consider a stochastic generator which are uncorrelated in time but are position dependent, and hence they result in a Markov chain. And then we can also say we consider an evolution of distribution of the state space omega on the stairs for random walker or an ensemble of walkers. So next we define for our problem what is a countable space. Like this is a very basic definition. Like for each point x which is there in the state space or the each state space which we have defined in the previous slide. So for each point x there exists a countable neighborhood basis. That is the collection of all neighborhoods of x, and that we say as a first countable space omega. So we define our state space as a first countable space. Now for a Markovian walk in that state space, we define a distribution which is of the form of P, which is given here as like P1, P2, or to Pn, which basically defines which is basically the probability of finding the walker in the position with index I, and those satisfy the condition. That's all of this sum up to 1. So it's a very basic definition of how we are defining our system. So as you can see from the previous slide, you can follow it easily that this describes a single step evolution. Like our walker can move through at one place at a time with probabilities which are given with these values P1, P2, Pn, and the directions. So the single step evolution of the distribution function or the matrix P which we have defined in the previous slide is known as, and it is given as a stochastic matrix M. So the characteristics of stochastic matrix is it's first of all a real matrix which all the columns summing up to 1, as we have seen in the previous slide that all the P's are summing up to 1, which preserves the probability measure actually, and the elements are positive and smaller than 1. They cannot be less than 0. So for an initial state P0, the distribution after m steps is given as Pm, which is given as m to the power m P0, capital M to the power small m P0. So this is like capital M describes one step. So if we perform m steps, capital M will act m number of times, small m number of times on the initial probability distribution. So we define the system using this probability distribution form. So now we look at the transitions conditions. So we define allowed transitions of the random walker from any position I. I and J here are basically the indices of the positions. So the allowed transitions of the random walker from position I to position J are reflected within M by the condition M I going to J is not equals to 0. Like if this one was equals to 0, then this indicates that the Mij component of that M matrix would be 0. So that thing is not possible. Then the walker will not go from position I to position J. Whereas the forbidden transitions correspond to Mi comma J, which is equivalent to Mj comma I going to 0. So like I discussed, this condition cannot be taken into consideration. Only this we need to consider. And this why we are writing Mi to J and Mj to I is equal to 0 for forbidden transition. This is basically a very basic principle of symmetry. So we can assume this means property. So now we define a graph structure. A graph structure is defined basically like on the set of vertices along with the indices pairs. So this is a graph structure G, which is defined as V, which is defined on V, which is the set of vertices or the states which are spanned across this state space, and E is basically the ordered pair of vertices which corresponds to transitions from J to I. Means J comma I means from J to I. These transitions are corresponded in this E. So the graph structure basically defines, now we have defined the graph structure, so it basically defines the transitions which are possible. And the coefficients of M are the transition probabilities to different states. Like I described in the previous slide, that Mij, that shouldn't be equal to 0 because that would signify that the walker is not going from position I to position J. So basically I have written that as a statement in this slide. And in this manner, we reproduce the behavior of the stochastic generator or the random generator as a coin. Like this is defined as, means this is given a term which is called coin. An unbiased coin treats all directions equally. Like if I am suppose at coordinate 0, 0, then I can move to coordinates 1, 1, coordinate 0, 1 or coordinate 0, -1 or 0, -1, 0 or -1, 1, 0 with equal probability. So that is basically defined as an unbiased coin. Now I give the example for a 2-dimensional space, but you can consider it for an n-dimensional space. So the unbiased coin treats all directions equally. Either that the coefficients M, I should have defined at Mij are defined as Mi going to J as 1 by Di, where Di is a degree of vertex I. This is basically like if I suppose stand at a point which has 6 neighbors, so the degree would be 6. So I can define that the Mij component of that M matrix would be 1 by 6, and if this transition doesn't take place, then it is 0. And if this whole property or this whole condition is not satisfied, then we say that the coin is biased. So using this, you can actually construct and understand very basic and algorithms on how quantum walks are generally understood. So for the unbiased one-dimensional case, all the roots go from position 0 because it's a one-dimensional case. So suppose if I'm standing at the origin and I'm going to positive x or at negative x after performing m number of steps, are composed of, this is basically a notation which I'm keeping as n plus is equals to m plus x by 2, and this is n minus is defined as m minus x by 2, and this signifies the number of steps I've taken towards the positive direction and number of steps I've taken towards the negative direction of the origin. So this condition, this I'm just defining like this because this leads to us a property which is known as modularity, and we can define modularity like that after an even number of steps, the probability to find the walker on odd position is always 0. Or we can frame it like the probability that after an odd number of steps, the probability of finding the walker on an even position is 0. So this ensures that if this is even, this is odd, then we can always write this m plus x as an even. Or this both conditions, this also ensures that we can write m plus x as an even, so that we can divide it by 2. And here we considered a bipartite graph. Like in this whole topic we will discuss, we will consider bipartite graph. Now what is a bipartite graph? It is basically a graph like if we form two sets of the vertices of that all the vertices in that graph, then no two elements which are present in the same set would have a relation between them. Like they can have relation with other vertices on the opposite set, but not within the same set. So this is very basic mathematics which we can easily see that why do we need to understand both classical as well as quantum random walks. Like I've defined that n plus minus. So the number of paths which you can take is basically means combination problem. Like you can define n plus is equals to m factorial by this. But this combination, I think I missed some part here. So it is better to consider this capital N comma x is a combination of MC n minus or MC n plus. This will lead to same equation. So the number of possible paths of n is m. M is basically like the number of what I've defined here is this m steps are the number of steps. So from here we can go like 2 to the power m. You can easily see like from it, since it's a one-dimensional problem, like I can go either to the right or to the left. So there are two options. And for m steps, then there will be 2 to the power m options, right? So the probability of finding the Walker at position x is given by this expression. Now we utilize what is called Stirling's approximation. Stirling's approximation is basically given by this expression, like ln n factorial is n ln n minus m plus order of ln n. And if we change the basis to 2, then we can means if we write it in the basis of 2, then we can write log n factorial base 2 is equal to n log n base 2 minus n log e base 2 plus order of log n base 2. This basically simplifies to this form, root 2 pi n m by e to the power n. Now, if we just basically place in this expression, equation 10, this expression, if we place in this equation 6, the equation 7, then we basically can cancel and get a reduced form, which is this one, where we have assumed that the number of steps is much more than the position which we are trying to attain. Like if I'm going from, suppose I consider a one-dimensional line, if I want to go from x equals to 0 to x equals to 3, then I should take more number of steps. Like I should take probably like 10 steps or 12 steps to reach that x equals to, so that we can ensure that it's a random walk. Otherwise, if I take 2 steps, that is not possible, because with 2 steps I cannot go to x equals to 3. If I take like if one step corresponds to 1 units of movement, like if I'm going from x equals to 0 to x equals to 1, that corresponds to 1 walk. So I need to take minimum of 3 steps to go at x equals to 3. But if I take 3 steps, then that will not correspond to a random walk. That will correspond to a conditional walk. So we need to take steps which are much more than the position which you are trying to attain. And if this condition is satisfied, then the last 2 terms, basically these 2 terms in equation 12 approaches 1. So we can further reduce this expression to this form. Now keep in mind that this thing is not normalized. So this is not a probability distribution. For this probability distribution, we should have this mod square, mod p square equals to 1. So this is a normalized, right? So if we assume modularity, which I've explained that we are taking m plus x is always even, then we can write equation 14 as this. I have given a means I have defined the probability like this, the 1 by root 2. Now this is normalized. So this is the probability distribution function where we have multiplied a factor of half to PMS because of modularity condition. Like both the conditions, m plus x gives like odd and even and odd combinations give us odd number of chances. M plus x is always even. Now if I calculate the average of x square, I get this as proportional to m is equals to m, and this which I calculate the standard deviation, this is root m. Now root this term is the standard deviation of the Walker is proportional to root m is for classical random walks. But for quantum walks, if perform the similar calculations, we will find that the standard deviation is proportional to m. Now, if the standard deviation is more, then we can say that the walk is getting more more random. It is not getting uniformly distributed. So we can say that for a walk to be more random, the better option is to study quantum walks. So we are generally the graphs are non-bipartite, but we consider the bipartite graph. But we can consider both cases. Now, random walks can be used to search for a marked item, and this is very important to understand why do we need controllability and for understanding random walks on graphs. On a graph of size n, and knowing the structure can help us in finding the efficient deterministic solution. So now we will discuss the analogy between classical and quantum walks, and then we will move into our main topic. In the classical case where we consider a linear chain over the set of integers. Like I said, we can consider that real line to be a line of integers, and like I was going from 0 to 1 to 2 to 3 like that. So here we consider a Hilbert space which is defined over Z. Either H is defined as L square, where X, this symbolizes the orthonormal basis, where X spans the whole integer set, means integer space. So now we can add another degree of freedom, that is a coin space, because we defined as the controlling factor as the coin. So for that we also need a coin, means to define that operator, we also need a coin space on which we can define that coin operator. So this basically describes the direction of the walker, and this space is a set of, I am defining this set as going to the left or going to the right by one step. So if this if this operator acts on this, on the walker which is present in this Hilbert space of Z, means this Hilbert space over Z, then only the random walk will take place. So I need to define this coin space. So this describes the state of the particle by the tuple x comma c which belongs to Z cross what means, I don't know what this term called. So I am just so Z cross this, and then we can expand the Hilbert space to a tensor product HP, which is basically the position space, and HC, which is the Hilbert space of the coin space of the coin, Hilbert space of the coin and Hilbert space of the position. So where HP is basically this thing defined over the position of the worker, and HC defines the coin space. So now we have H spanned by the orthonormal basis X, where X belongs to the position space and C is the orthonormal basis of the coin space. And then we can define every single unitary evolution operator U as S I tensor product C. Now you can consider it is like S C, but I kept this as I tensor product C because the coin space, like I defined here, is one dimensional, right? So if I need to make the coin operator act on n-dimensional space, then I need to apply a negative tensor product it with n number of identities, so that I can get the corresponding, means I can match the dimension of both the state space as well as the coin space. So C is the control qubit corresponding to the coin flip, and S denotes the spatial translation on the whole Hilbert space where the walker is actually present. So the conditional position shift operator acts on the Hilbert space H, and depending on the state of the coin, it shifts the position of the particle by one place either to the right or to the left. And in this case, a linear graph, the allowed transitions are to the nearest neighbors. You can easily understand that if my coin flips to the right, then I can move from X to X plus 1. And if my coin flips to the left, I can move from X to X minus 1. This is basic. If you consider just this part, this is basically like a projection operator, and this is also a projection operator. So it depends on the condition on what our coin is flipping. Then it will correspond to the movement of the walker either to the left or to the right. And okay, so the coin operator I tensor product C acts only on the coin space, which is given by the Hilbert space of the coin HC, and corresponds to the flip of the coin. The coin is unbiased if the states, the right side and the left side, are evenly distributed into their equal superposition to a phase factor. Now, up to a phase factor is, I have written this statement mainly because this phase factor doesn't have a main role in the determining on which side the walker will go. Because when we, like in case of while we described block sphere, there we had, while we are calculating the mixed state and the pure states, there we had a condition where we had one of the exponential coming out as a common, where we define like 0 means a superimposed state as cos theta by 2 of 0 plus sin theta by 2 e to the power I phi 1. Then we had a minus e to the power I theta outside as a common, and then we can easily deduct by doing normalization and taking it out as a factor. So that same logic applies here. So we can take up to a phase factor, but this will correspond to the same operator as a whole. So now we call this a discrete time quantum walk as a coin quantum walk. So our state psi, which is spread across its whole space Z cross this, so we took the coin operator as I tensor product C instead of C to match the dimensions, and a single step of a coin quantum walk is described by the operator U in equation 18, which is basically this equation. It's the unitary single step unitary evolution operator, and the state after n steps will thus be described by the vector from H as u to the power n psi 0. This psi n will be described as u to the power n psi 0, where psi 0 corresponds to my Walker state at time t equals to 0, and psi n as is like after n number of steps. So we can generalize the previous definitions to more general graph structures. We saw that by using the coin degree of freedom, even though the linear graph on which the Walker moved was not directed, the edges can be interpreted as a set of two oppositely directed edges. Like in the linear chains where we are having a, suppose the integer line, then if I can go from x equals to 0 to x equals to 1, it was equally probable that I can move from x equals to 1 to x equals to 0 also. So it was like a bidirectional move of the Walker. So from now we will work with unidirected graphs, where the edges are bidirectional, unlike directed graphs where the edges point in a specific direction. Now directed graphs means if I move from x equals to 0 to x equals to 1, I cannot move from x equals to 1 to x equals to 0 in a single step. That means I have to move either to the right or to the left, but I cannot go from from left to right or right to left. But yes, that is possible if I take a significant number of steps, then I can come back from x equals to 1 to x equals to 0. But for undirected graphs, what can happen is like if I go from x equals to 0 to x equals to 1, with a single step, I can eventually come back from x equals to 1 to x equals to 0. That's the main logic which we are using here. So we consider the d-dimensional regular undirected graphs. Regular graphs means each vertex of the graph has an equal number of neighbors. G, which is defined as the same graph structure n comma u, where n denotes the set of vertices, and E is n cross n because it's a set of edges defining the graph. And a regular graph has the same number of neighbors for each of its vertex. So we can take each edge as two oppositely directed edges, and we assign a colored number from 1 to D to each of the directed edges, such that each vertex has exactly one outgoing and one incident edge which are given color. Now this term basically signifies like each edge which I'm defining on each vertex which I'm defining on the graph. Suppose that vertex has 3 edges. Then suppose edge number 1 can be defined with different probabilities, edge number 2 can be defined with different probabilities, edge number 3 can be defined with different probabilities. So that thing is basically we use the term color to distinguish it from to distinguish a particular edge from other edges which are connecting one vertex to different other vertices. So for the edge, we have the translation operator S, which depends on the state of the coin, and then correspondingly it moves from X to either X addition. This is basically direct sum to C, or it can move like from left to right or right to left in our case. The X plus X addition X direct sum C is the vertex accessible from X by the edge with color C. This symbol basically defines that. Now, why I have written here direct sum? That is because here we are not. These two are different spaces, Hilbert spaces, right? This is X is from HP and C is from HC. So if I join two conditions, then I cannot directly sum them and write as X plus C. I need to use a direct sum to consider is as a conditional state once when I get the value, once when I determine at what C our coin is flipping at. So for a d-dimensional coin space, the coin tossing operation, which we can take to be position dependent, but we need to take it time independent, is given as this. This basically introduces the position dependency, and these are basically coefficients of a D cross D matrix which is defined for different vertices X. So this D basically is used to signify that it's a D cross D matrix, and X is for each vertices we define a different coin operator. So we have the two-step unitary operator as U equals to S C prime, and by comparing C prime to the position independent coin operator I cross I direct sum C, because this C do not have any X dependency, like position dependency, this position independent is given in equationality. We can find that this term and this term is same. So to equate both of this, we need to have these both terms as same. Like if this is equals to this, then this indicates that this X dependency is not there. This is only these both are D cross D matrices. So this is basically the same thing which I have just basically written it once again for a brief revision, like where V is a set of vertices, cardinality N and E is a set of edges. So G is basically a regular graph of degree D, and G is connected without self loops. Okay, so self loops means suppose I have a vertex which I am naming as suppose vertex 1. There shouldn't be any edge which connects vertex 1 to vertex 1 itself. This is called self loop conditions. So I will not consider self loop conditions. I will just say that D is connected and without self loops. The Walker state varies in the n-dimensional state space W, and the coin system varies in a d-dimensional space C. And these basically, like I have defined X and C, these are basically the orthonormal bases. Small x, small c, which I have defined, they are basically the orthonormal bases which span the whole Hilbert space of the Walker space and Hilbert space of the Walker as well as the coin. So these are n number of states and these are small d number of states. And J means if we measure the position of the Walker, we find the position with certainty J. So similarly, Cj indicates that the d-dimensional coin space is given as a result of J. So okay. So we define the coin tossing operation on C cross W, C tensor product W as C this expression Qj tensor product J comma J Jj, which is basically of this form. Now, if you consider this case, then you can basically replace as C, and that is basically Q, which we have defined here. And this is known as a decentralized model because the coin evolution depends on J. Like here, it depends on J. J is basically like the dimension. J is basically like the dimension value with the orthonormal basis taking place, like that from the n-dimensional state space, n-dimensional space of the Walker. So here it is going. J is going from 0 to n-1. So with increasing number of dimensions, our C coin tossing operation will also change. Like I said at the beginning, that if I am having a linear chain or a linear walk, then in that case the coin tossing operation will either depend. It will be J equals to 0 and J equals to 1. So either it will be Q1, Q0 and Q1. For 2 dimensional, it will be 0, 1, 2, 3. It will be Q0, Q1, Q2, Q3. Like that. For n dimensions, it will go from 0 to n-1. And this is similar to the expression discussed in equation 22, as it depends on the current Walker state. And this is a decentralized model. On J, we have the conditional shift operator. This form, you can recall, is basically this expression which I've written in the previous slides. One of the previous slides, this one, equation 21. Yes, this one as well as this one. This is basically a short form, is compact form of the previous equation. So using this, we can. Okay, so this is an important statement. That this applies a state psi which is belonging to the Walker space, a permutation pk. Now pk, why you are applying a permutation? Because the Walker is not changing. So we can consider it to be like an identical particle at each of the vertices. So for that case, we are applying a permutation pk, which depends on the current value of the coin system. Now, if you have some idea about identical particles, you will know that while we define for many particles like for bosons and fermions, we introduce the concept of symmetrizer and anti-symmetrizer. In that case, we introduce the permutation operator. So similarly here, since we are dealing with the same Walker at different vertices, they are basically like identical particles, and for that we introduce the permutation operator pk. And if we expand the basis, this J is basically the Walker's basis of the Walker state, and this is basically the coin state, and this will correspond to delta kj, where k belongs from 1 to d, which basically depends on the dimension of the coin space, and j from 0 to n-1. And we have the matrix representation of S as this. This is a diagonal matrix where P1 corresponds to the every permutation, like from permutations we where P1, P2, PD are like, if it considers as Pi, then for every I belonging to 1 to D, we have Pij is equals to L, which basically means that there exists an edge in E connecting the vertices J to L. So this basically means the Walker is getting transferred from this vertex to this vertex via this permutation operator. So now we will discuss, we'll also see that for I not equals to K, we have Pij is not equals to Pkj. This is obviously understandable how we can claim this statement. That is for all J where different coin results induce different transitions. Okay, so this is basically, so remember this formula C K tensor product days delta Kj. So this permutation matrix basically defines the adjacency matrix of the graph. Permutation operator basically defines the adjacency matrix of the graph. And in the vector space C tensor product W, by expanding in the basis, we can basically write C delta Kj is equals to this form, because if I place the operator C, then from here I can easily check for Q, I will get the value Qj here, and for if you place the transition operator S, I will get the value Pk here. So this is basic calculation. And for any state C tensor product W, which we can define on the basis, we can write the state while expanding on the orthonormal basis as alpha kj ck tensor product J, where alpha kj is basically the probability amplitude. So the probability of finding the Walker in position J is basically the summation over all of k alpha kj mod square, modulus alpha kj square. And at every step, the state psi evolves as psi going from SC. This is basically the unitary operator. This is basically U equals to SC acting on psi. For two operations, it will be SC, which is acting another on SC psi, like that. So now we can now we can have this question that how to get the set of states. Means how can we get the set of states in which our Walker is present? So that is why basically by varying the coin operator, because the coin, we are having control over the coin operator, but we do not, and that further determines the state in which the Walker will be present in the position space. So the possible set of evolutions are given as this is a product of SCK. S basically depends on C, and for each steps the C will be different because they are arbitrary coin tossing operations. And from equation 23, which is this expression, this equation, we can have that for equiprobable cases, Qj, which was defined in the previous equation, are all same. So I will go into a little bit calculations, which you can just follow. That why do we need to do them? And I will just basically after that I will just give the main motive why we introduce such concepts. So we've defined the permutation matrix P as a matrix which represents the permutation of m elements and has one entry of 1 in each row and each column and 0 elsewhere. We have S as a permutation matrix of Pk, which depends on the current value of the coin system. Okay, so this point I think will be understandable from the previous discussions. Then we can say that we know that identity matrix is an example of a permutation matrix. Obviously, it's true because identity matrix has 1 at each column and the other terms are 0. Only 1 at each column and the other terms are 0. So now, suppose if I define a set of matrices, which is like A, these are not power. These are just like indices which you can consider the relevant S's which we are having. Like we are having SR, which are for some order R. We have different SR. Like from for R equals suppose 5, we are having S0, S1, S2, S3, S4, like that S5. So I define a set of matrices like this, where A basically symbolizes S index to R, A, SR. And now see this term which I've written here, and SR, suppose if I consider SR to be identity, like if I suppose fix that SR, suppose S5 for our case when R equals to 5, I suppose I fix that as an identity. So identity will basically give me identity, that is basically this term which I'm having here. So I'm just basically writing it like S1, A, SR minus 1. Then A, then it is still going to SR minus 1, A, S1, like that. So this is basically a set of matrices. So we know that the product of two permutation matrix is also a permutation matrix. This is a very basic definition of permutation matrices which we know. And from that we can define this form where AJ belongs to UD. UD is basically the unitary operator depending on the dimension of the coin space. And this A is basically a Lie algebra. And for two Lie algebras, we know that for two Lie algebras R and R prime, their direct sum Lie algebra is a vector space R direct sum R prime consisting of all pairs of X and X prime, where X belongs to R and X prime belongs to R prime. Now, remember we wrote a term called X direct sum C. So X belonging to that X and C belonging and X prime belonging to C. This get direct summed and then we can have another Lie algebra. So L is a Lie algebra, or we can consider as a loose term like vector space generated over F, and it is the smallest Lie algebra containing F. Then we have for a given Lie algebra matrices L, the connected Lie group as e to the power L, EA1, EA2 like this, where A and A2 belongs to L. And these are connected, like all the connecting components including I. The connected Lie group E to the EL is basically local Euclidean. Either it satisfies binary operations, and this type of mapping is known as exponential mapping.
Excuse me, Rajdeep.
And we are, in fact,
Hello.
yes.
Yeah, I'm very sorry to interrupt you, but then can you please wrap it up within 10 minutes, okay? Because
Yeah,
you might
yes,
be starting from different. Okay. Okay. Thank you.
Okay.
Please go on.
So this formula we all have learned previously in quantum mechanics courses, Baker-Campbell-Hausdorff formula, like where we define like e to the power summation sum of two operators a plus b is given e to the power a, e to the power b, then e to the power means bracket a comma b by 2, like that we expanded. So this basically involves this concept of Lie groups and Lie algebras. So now we define another Lie group G generated by EL and S, and we keep the propositions that G is the Lie group generated by EL and S, and K be a set defined as this. This is basically the union of all different combinations of S. So this is EL, SJ is basically X, SJ, where X belongs to EL. So basically, this is a very lengthy proof which I have written here. So the main proposal of this proof, this is a disjoint union. So you can just see if you can understand this proof as a whole. But the main concept of this proof is no matter whatever graph structure we choose, whatever different combinations we choose, the properties or the algorithms which will define next for the random walk, they remain same for different all type of graph structures or different types of combinations of the same graph. So this slide is basically a continuation of the previous slide. So if you understand the previous point, then it is over. Then it's okay. So the theorem which basically defines, which is main for introducing controllability, is that for every epsilon, which is defined as a set of possible evolutions of the quantum walk, we have epsilon equals to G, and this is in fact equals to K is equals to C. Like for all cases, it will be same. This is that same proof there. So that another theorem is the quantum walk. This is one of the most major theorem, that the quantum walk is completely controllable. Either every unitary operation is possible if and only if L, which we have defined in the previous slide, is given as U dn as a unitary operator of dn. The dn is a for n-dimensional space. For each walk, it should depend on the U should be dependent on that. So this involves the concepts like of dynamical Lie algebra, which further involves these permutations. But these two theorems are mainly important for devising algorithms and other things. Like these two slides are mainly the same thing, so I might skip them because they just propose that the different permutation operators basically lead to the same results, means same properties. So yes, that same theorem is here also, and the proposition is the quantum walk is completely controllable if small d is greater than n by 2, and it becomes uncontrollable even when d is equals to n by 2. So the product of two controllable quantum walks is always controllable, and I will discuss it very briefly in the next slide. So using these theorems, we devise the algorithms. So the first algorithm is that for each permutation which belongs to this set of permutations characterizing the walk, we consider for every pair L less than M, the permutations which I've defined here, like K is moving to right, and suppose K is moving towards the right and minus K is moving towards the left. It is the cycle notation, and we connect all the vertices in a graph that pairwise belong to the same cycle, at least in one instance. This is a reduced connectivity graph of the system. And this algorithm too is basically the very basic proposition which I kept at one of the previous slides, that for k number of unitary operators, we basically apply SCs like that, means individually on the initial state. Okay, so this slide basically like algorithms we always keep since we already said that small d must be greater than n by 2, we always have n greater than 2, and we define the bound on the length k of the needed control sequence. For a given node which belongs to n-1, we define the set of all nodes which one can reach using the edges of the graph in a given number of steps as this: n0j is basically j, n k plus 1j is basically reaching L from j by taking the number of different probabilities. So where nkj is a set of vertices connected to j by a path of length k, and we understand from the connected nature of the graph that there exists a sequence of permutations R1, R2, Rk in the set P1, P2, P2 such that L, this number of permutations acting on J, we can reach from vertex L we can reach to vertex L from vertex J using some path. Now this lemma is basically that same thing which I have written there, but this is like slightly advanced version, so I am just skipping this part. So this both slides are same. So now let me go to example which will help you clear the means why do we need such algorithms. So we work on a 3 regular 6 vertex. Why it is a 3 regular? Because from each vertex we can reach to 3 other vertices, and 6 vertices because there are 6 vertices. So there are 6 nodes and degree d equals to 3. So the quantum walk has a state space of dimension 6 cross 3 because this defines the state space and this defines the coin space. So like we did 6 cross 3 equals 13, 18, sorry. So now, like I defined in this slide, try to remember this expression a little bit, but it will be much more clear in this example. Like if I suppose that j equals to 0, then by taking one step, I can reach from j equals to 0 to 1, 3, or 5. We have written here 1, 3, 5. From j equals to 0, if I take 2 steps, I can reach 1, 2, here, 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 like all steps except 3, which you can see here. Now, if I take 3 steps, like from j n equals to 0, suppose if I take 1 step, 2 step, and 3 step like this, then I can reach all the defined vertices. So basically, n3 is j equals to 0, I will get all the defined vertices. And this plus minus which are written as plus minus c, these are basically like 3 different terms. This basically corresponds to the probability at that direction. Like p plus is basically like probability of going from 5 along this direction to 0. PC5 is going from this direction to 1. Probability of going from this direction to 1. P minus 5 is going from probability of going from 5 to 4 and this direction like that. So these are basically as same as this thing. So we can write that the quantum walk on this graph is completely controllable. And also we can see here why, because here d is 3. And there we have told, there we have stated that d must be greater than n by 2. Right? So if here d is 3, so this is always greater than n by 2. Right? So that's the case why we can always steer to the we can always completely control this graph structure, or rather we can control the motion of the motion of the walker, and then we can go from an initial state acting on suppose j equals to 0, and then suppose if I have c equals to plus at j equals to 0, its final state can get uniformly distributed. Okay, so these are the main things that basically that the coin operator corresponds to the same thing. So okay, so to go from initial state to a final state of the form given in equation 51, you can apply an appropriate coin transformation followed by a conditional state. Now, what can we further work with in this topic? Like we described as a countable state, right? So we can also, or we described as a first countable space. So we can further study this for uncountable spaces, but I think that will be a little bit complicated. So that we can further study on. Then we can study quantum walks for graphs with self-loop conditions. Like here in this case, there was no self-loop. Otherwise, there was no probability of going from here to 3 again. These cases we didn't consider. And for a general d-regular graph, which is not symmetric, we need to take the directional information condition while defining the coin operator. So we can try to study for graphs that are not regular, but to define a coin operator in that case, that would be difficult. So these are the few features, future scopes which you can work on. And here are the few references which I took while preparing the slides. So there's a book by this author Domenico Di Alessandro on quantum controls and dynamics. So you can also yes, this book only. And there's a paper also. Like sorry, I was studying book, but there's a paper also by this author which you can consider while for understanding this topic much more better, in a much better manner. So okay, so I am done. So any questions if you have, then.
I don't think there are any questions. So I guess we'll end it here. Thanks a lot for your very detailed speech, Rajdeep. I wish you the best of luck in your future endeavors. So yeah, thank you so much.
Thank you.
Okay. Then we are moving to the last speech of the day. Remember, disclaimer that the conference is for 2 days, so it'll be there tomorrow as well. So stay tuned for that. So today's last speech shall be by Tridev Sheet. He used to be our classmate at RKM Narendrapur. So he is presently doing his integrated M.Sc PhD at IISc Bangalore. He works on photonic lattices, and the topic of his talk shall be waveguide arrays and the emergence of condensed matter physics from there. So, Sridev, are you in? Hello?
Yes, am I audible?
Yes, you're audible. Please take center stage.
Okay, let me say. Okay, is my screen visible? Hello?
It's black. Is your screen black right now? Your screen, I mean, it's black. I don't know. Maybe change something. I don't know whether it's my problem or is the screen black? Others?
Presentation is not visible.
Yeah, your presentation is invisible. That's the thing.
I think.
Sure, take your time.
Hello?
Yes. Yeah, you're not seeing your screen.
I don't know how it's not working.
Maybe start again. I don't know.
Okay, well, let me try. Okay, I think Rajdeep is still presenting.
I don't think Rajdeep's present.
I think Rajdeep is still there. I mean, say screen black here.
Okay. Let's.
Fine, but you know, present.
I'm sorry to the audience for
Yeah, probably that's your screen. And now can you start your slides or the screen?
Now I think it's visible.
No, it isn't. It is black right now.
Okay. Oh, it's not this.
What did you do? Like, did you do this share screen or share window? What did you do? The share screen or share window from this like share option?
Okay, I can.
Hello?
I can see share window option.
No. Like there is this option now in Teams, the share option. So there are two options, screen and window. So which one are you going for? Which one are you selecting? Screen or window?
Yes.
Your audio is breaking up. There's a problem. Problem is it's a network issue, I guess, or what?
I think
because we can't hear you properly. Your voice is breaking up. That's the thing. It's black. Whatever you have shared is black.
Let me
Actually, you can send me the slides email so I can present.
within 2 minutes.
Trideb, you can share your presentation with Sanjan. He can present on behalf of you.
There might be synchronization issues. Also, Tridev, yeah, I think your voice is also breaking up. Is there a network issue on your end? Because what you are saying is not clear at all. We can do something like the first talk tomorrow starts from 10:30. So we can start it a little early and you can begin the talk tomorrow morning. Okay, we can't hear you at all.
Yeah, that will be a solution. Probably.
Tomorrow, na? What do you say, Sanjay?
Yeah.
Okay then, Tridev, we'll accommodate for you tomorrow, okay? And make sure like you have a proper network issue because network connection because like we can't even hear you properly. Probably that's the reason your screen is not showing up. So yes, I guess this is quite unexpected. So we have to end the talk here today. Tridev would have spoken today. We will accommodate for Tridev tomorrow morning. So thank you all for coming, for attending this conference. I hope that you will also be present tomorrow. You can always like say if there's any issue or something in this. You have this YouTube channel as well. Also, you probably know some of our members. So if you have any issue with anything, you can report that. Tomorrow we'll be starting at 10:30, I guess. Yeah, 10:30. So
the network. Okay, I guess it's presenting.
You think you can present?
Is it presenting?
It's still black. It's still black. I'm so sorry. It's not. It's not your day, man. You we'll talk and maybe select a time for you tomorrow. Okay, don't worry about this. Okay. You know that's what research is like. Some days you won't be able to do anything. You have to leave it and move on, right?
Yeah.
No, I see. I really appreciate your problem, your ability to like stick to a problem and not leave it. But then you have to leave it for now. Okay, we'll see to you tomorrow. Okay. And I think there is a network issue from your end because it's not only the problem of sharing screen because when your audio is breaking up, like we can't hear you. None of your words are clear.
Sure. Okay. We'll accommodate for you.
Okay.
Then see you tomorrow.
Yeah, see you tomorrow. That's good. Yeah.
I might record my presentation and wait tomorrow.
We'll look for alternatives. Don't worry about that.
Bye.
Okay. Yeah. Bye.
I can. Okay.
Okay. So that's how it unfortunately ends for us today. I hope I really expect your overwhelming presence tomorrow as well. Our presentation is supposed to start at 10:30 tomorrow, but then we might need to accommodate Tridev somewhere before or at the end. So there might be a little change in schedule. You will all be notified via mail. So I hope you liked today's presentation. This was a small initiative from our end, and so please turn up tomorrow as well. We were really pleased to have your presence with us. Okay, so I think we have come to the bare end. I guess we can end now. Okay, thanks all for coming and for making this even a little bit of success. If this was some success, we owe it to you guys. Okay, then this is not the perfect time for saying good night. So, but yeah, good night. See you tomorrow. Bye.
Thanks, Alekho, for being an outstanding coordinator. Thanks. Thank you.
You can reserve this for tomorrow, Sanchar.
Yeah, sure.
Okay. Thank you. Thank you, people. Bye.
you.